firstly, my talk will be short because I planned for a blackboard talk, and at the last moment I made it this, so it's not yet complete. So I just first give this apology. So this is the title of my talk.
Sir, you can use the whiteboard. We'll get you something. You can.
But let So this is the motivation. So Einstein's general theory of relativity is I'll denote it GTR henceforth, is a classical theory of gravity. Here metric is the basic variable with maximum 2 spacetime derivatives. But any UV complete quantization of gravity would typically lead to higher derivative corrections to GTR at low energy and classical limit. In absence of a completely satisfactory UV complete theory of gravity, we still do not know what these higher derivative corrections are. So it would be nice if we could constrain the structures of these higher derivative corrections purely from low energy considerations. For example, maintaining causality in graviton scattering or maintaining thermodynamic laws in thermal state of gravity, which are black holes. So the final goal of our project is, this is the grand final goal, we are nowhere near to it. Can we use black hole thermodynamics to put any constraint on higher derivative theories of gravity? And everything is classical, no quantum, nothing entangled and so on. So first, black holes in two derivative theory. So in two derivative theory, this we all know, black holes are singular solutions of Einstein's equation. The space-time curvature diverges at some points, and the singularity is causally separated from outside world by a null surface, which is called event horizon. And the geometric properties of black holes could be identified with thermodynamic properties. Some components of Einstein's equations could be rearranged and interpreted as zeroth, first and second law of thermodynamics for two derivative gravity. So black hole thermodynamics implies that black hole is an ensemble of many quantum microstates of gravity. That's why there is in thermodynamics. And therefore, black hole thermodynamics must hold in presence of higher derivative corrections, which are actually generated in the low energy limit to ensure UV complete quantum theory. So we expect the same thermodynamics must hold. So black holes and higher derivative corrections. In two derivative theories, Einstein equations are heavily used to prove black hole thermodynamics. So therefore, higher derivative corrections will modify Einstein's equation, and so the previous proofs will not work. Now there are two possibilities. Just a minute. Now there are two possibilities. First, modify the proofs and identification of geometric and thermodynamic properties in such a way so that black hole thermodynamics work for arbitrary higher derivative corrections. And the second possibility is find counter examples where we can show that black hole thermodynamics will not work, and therefore it will lead to higher derivative corrections that could be called unphysical. So these are the two possibilities for higher derivative black holes. Now we shall discuss the present status of this problem, and we shall not give any proof for this. We just give the statements. The first is zeroth law. So zeroth law in general thermodynamics, zeroth law is the constancy of temperature on equilibrium situation. And in the context of black hole, it translates to that black hole has constant, stationary black holes will have constant temperature, which is computed by the surface gravity of the black hole everywhere on the horizon. And it was not, for higher derivative theory, arbitrary higher derivative theory, it was not known explicitly whether zeroth law holds or not. But you could recently show that if the black hole solution, I am not giving the proof itself is one talk then. If the black hole solution admits the power series expansion in the higher derivative coupling, if we call the higher derivative coupling as lambda, and there exists a smooth lambda going to zero limit to black holes in Einstein's gravity, then the temperature is constant to all orders in lambda expansion. Lambda is the higher derivative coupling. Okay, if you just take the standard black holes where you have one single, no discrete to multi-horizon kind of thing, one single horizon, and lambda has a expansion, then you could prove that it is true. But in higher derivative theory, previously there was no proof.
I'm asking, like, beyond this limit, are there any known counters? Because it sounds very counterintuitive that you should have a black hole where you have a varying temperature.
Okay, it depends on what you call the temperature. There are situations where I don't know the details, something called Hordensky theories, which once we wrote the paper that was communicated to us, in those, someone wrote to us that in those theories, there are possibilities that there are two kind of sound velocities, and therefore two kind of temperature one could associate with the same black holes. So those are special cases in special higher derivative theory, and this is just generically it's a thing. Whenever there is a single horizon, not 2, 3 horizons and those kind of thing, then it's true.
So I have a related question. So is there some extra assumption that is put in here? For example, we know that now there can be black hole horizons with less scaling vectors. So they are by, there could be only raised few Killing vector. Maybe suppose I don't know if such a thing exists. Suppose there are some black hole solutions with no Killing symmetry.
Okay.
Only time that Killing symmetry of course has to exist.
So the way we define the stationary black hole is, we shouldn't say stationary black hole, it's a black hole with a killing horizon. That's the assumption that has gone in. There's at least one killing vector which generates the horizon, like which becomes null on the horizon and becomes a generator of the horizon. So if that happens, then this is true. So that much is needed. And lambda expansion is needed. So the proof is iterative by induction. So for 2 derivative gravity it works, therefore it will work for 3 derivative gravity, 4 derivative gravity, and so on. So order by order it works.
So just, I know you don't want to give details. So for the two derivative theories, the proof goes using Rayleigh equation, for example.
Using?
Proof uses Rayleigh equation and some identities for the Riemann.
We don't use any identities. In general proof it uses identities, and there are many such proofs for specific theories like Lovelock theories, Gauss-Bonnet theories. Everywhere you have to use very specific identities compared to what happens. It's kind of the Ti component of the Einstein equation is proportional to partial derivative of the temperature, variation of temperature. It turns out if you just explicitly then you this is at 0th order, like 2 derivative order. Let's say 2 derivative order, the theory is proved. So in 2 derivative order, we know that del I of kappa or del I of temperature is equal to 0. Now you go to 4 derivative order. 4 derivative order you do perturbatively. So the 4 derivative order, the Ti component of equation of motion, is still have del I of kappa, and the right hand side there will be a source term, which is some covariant tensor tau I component. And then you can show if the previous order, that this source term will be completely computed on the previous order solution. And if you have shown that previous order any tau I component is 0, so therefore this order it will be 0. Therefore second order del I kappa is 0. Then you go for the next order. So it goes on like this. So that's the proof.
So with temperature here, you mean surface gravity?
I mean surface gravity. Just simply surface gravity.
But it's not easy to clear that this would be the temperature and the first law?
I think World's proof actually says that. So if you take world entropy to be the entropy, and then the surface gravity is the temperature that appears in the first law. So now coming to the first law. So this is the first line is the general statement of first law. If there are 2 nearby equilibrium configurations of energy E and E plus dE, charges Qi and Qi plus dQi, and entropy S and S plus ds, then this is the this dE is equal to mu I. This is the general statement of the first law, and everything is total entropy, total charge here. Now for black hole in 2 derivatives, so this is the general expression for the first law, and for black holes what you have to do, you have to identify some geometric property with this first law total thing. So for black hole in two derivative theories, the E goes to the mass parameter of the black hole, Qi goes to if you have charges, the charges or angular momentum, S is the horizon area, T is the surface gravity, and then it turns out that they also satisfy this relation. But in higher derivative theory in 1994, I think, it's Iyer World paper, they identify as E, Q, S, etc. in a slightly different way, not exactly the way, like for example, area is no longer entropy, but something else, some correction, but in a different, slightly different way, so that the first law holds. So the first law is the key identifying feature here, like the key criterion here, which actually tells world how to select S. So S should be such that the first law is satisfied, and then he has shown that such re-identification is always possible in every arbitrary theory without any expansion and so on. So therefore, first law is also proved. Now the second law. Now second law is something that is not proof, and it can have many versions, what exactly we mean by second law. So if an equilibrium configuration with entropy S initial, SIN, perturbed and then settles to another equilibrium configuration with entropy S final, then the second law says that S final is greater than S initial. Okay. And both the cases S final and S initial are computed in equilibrium solution, but in between there are dynamics. In two derivative theory, it holds as a consequence of this famous black hole horizon area increase theorem, and it's proved like extremely non-perturbatively, no expansion, nothing, always true. But we still do not know of any such theorem for world entropy in higher derivative theory.
So you want to make the statement only in pure gravity, or for present two derivative gravity, you need also the null energy conditions of the classical matter?
If you have matter, then you need null energy condition, but if you don't have matter, without that also it works.
It should work, right?
So
Making the statement only in pure gravity.
the statements are true even for without like even with matter, but that has more subtlety in higher derivative theory, particularly figuring out what is matter stress tensor. Because in two derivative theory, metric and matter is completely decoupled. So you can define matter stress tensor is the matter part of Lagrangian and variation with respect to G. In higher derivative theory, what is matter stress tensor, at least classically, is ambiguous. So you can explicitly show that in higher derivative theory, you can have matter stress tensor which violates null energy condition. And then you can absorb it in the current and can do something so that it's still possible to be valid. So with matter also it works, but whatever I'll be stating, let's say without matter, that's much more unambiguous and correct. So as I said, in higher derivative theory, we still don't have a completely satisfactory proof. Zeroth law, I think satisfactorily proved, some might disagree. First law is, everyone knows that's very satisfactorily proved by world. Now what we know for second law in higher derivative theory, HD means higher derivative. So one way to show the second law would be to construct out of the metric component, let's say we are considering only pure gravity, so out of metric component, construct some JV, some scalar type of quantity JV, not exactly scalar, and a JI, such that on any dynamical solution, this relation is satisfied, del V JV plus del I JI is greater than or equal to 0, locally at every point on the horizon, where V is the parameter along the null generator and I the indices along the spatial slices of the horizon. Then if I integrate this equation, and the second condition is that suppose if I integrate this JV on spatial slice in equilibrium, say this JV reduces to world entropy. So if I can extend this world entropy in such a way that this above inequality is true, then we could, then this will solve, like this will give a proof to second law. Because two equilibrium solutions are dynamically connected by this JV and JI, and they always in dynamics satisfies that inequality. And on top of that, whenever it reaches an equilibrium, final or initial, it will reduce to the final world entropy and initial world entropy. So since it is always produced and it is reducing to final and initial world entropy, so it will always increase, the world entropy will increase. So if I can construct a JV and JI like this, we are done. So we could show that now what we could show is that such a JV and JI could always be constructed on any dynamical horizon, provided the amplitude of the dynamics is small and therefore treated only linearly. So when it is treated linearly, we could always construct. There will be many, there's no unique construction. There will be many ambiguities. On the horizon, it will reduce to, on the equilibrium solution, it is reduced to world entropy along with those. So the only issue for me is to satisfy first law and second law. So all those ambiguities are there in the world entropy, but still they satisfy first law. So if it reduces to any candidate of them, we are happy. So, and
If you construct this, how does that show that the second law?
because if you integrate that equation, so del I ji will go along the spatial slices of the horizon. So you get del v of jv along the spatial slices of the horizon is always positive. And del v at initial point is initial entropy, del v at final point is final entropy. So final entropy minus initial entropy always positive because you are adding something.
I is only
On the transverse direction, this is the spatial slices of the horizon. And v is the null generator direction, which is like time. So if you can construct this, we are done. So we have shown that this could be constructed everywhere linearly. I'll give a very, very brief outline of the proof. So there may be many questions. The proof is, I'm just giving this proof just to set up the notations in some sense, not really the proof. So any metric around the horizon could be brought to this gauge, where r equal to 0 is the horizon and del v is the affinely parameterized null generator of the horizon. Now, do you all agree with this, or there are objections? There is a double 0 in the dv square, so del v is null. So therefore, there should be a single 0, it's true at r equal to 0. But if del v is further affinely parameterized, that single 0 becomes a double 0. So you get r square. And the r is another null coordinate, is effectively like this binormal on the horizon. V is the null generator, r is another null coordinate going out of the horizon. And the gauge is fixed by the angle of r with v and rest of the alpha I directions. What is the definition of a dynamical horizon? I don't know whether I have it here. I might have it. Oh, it's there. I'll come to it. Just in the end, it is there.
It's not apparent or event or anything. It's a very uniquely defined.
What we are doing, you are looking for this global thing. So all our analysis will be local at a killing horizon. So whenever there is a killing horizon, this is happening. There is a killing vector.
Because I thought this depends on all coordinates.
No, outside it is not killing. So whenever there is a killing horizon, there is a stationary black hole, and on top of which we are doing a small perturbation. So killing horizon added with small perturbation, that's the only thing used. Now globally, whether it's finally going to the event horizon or not, that part is never used because we are doing some, information is not needed because we are doing a very local analysis and we'll get a local point. Small perturbation, local analysis, that's it. So therefore that information for this proof is not needed. Okay, but the first one is, the first line is saying that this is the full, I don't know when it is coming here, it's not visible.
It will never show up on the screen on the TV.
Acha. Oh, I see. Acha.
That's
So,
why you use the mouse. Yeah.
okay, I can use the mouse. Oh, the mouse on that. So this is the general any metric around the horizon could be brought to this gauge. I'm not giving a proof of it. You can geometrically construct, and even for very complicated metric, you can find a mathematical algorithm to bring it to this gauge around the horizon. So it's possible. Now the structure, now note that the structure of this metric will remain same under the boost transformation. This is called boost transformation. R going to C times R, C is a constant, and V going to V by C. So whenever there is an R square, there is a dV square. So they will cancel each other if C is a constant. Now boost transformation will be an isometry if R and V dependence of the metric in all the metric functions x, omega I and hij, they are like product RV. Then it will just be an isometry. So in other words, the stationary metric in these coordinates is the one that is written. X is a function of RV. Now this is another statement I'll make, I'll claim and I'll not prove, is that any stationary metric, whenever there is a killing horizon, could be brought to this form. And in any stationary metric, this will be this RV, this is basically this killing generator. The infinitesimal version of this R going to CR and V going to V by C is the killing generator of that stationary metric. If you are interested, or if I have time in the end, then I might go to the details of it.
So if you have like Jordan flow metric, dually Jordan flow, it's a boost invariant metric. It's a boost invariant flow, so it has a similar kind of scaling variable or some combination of R and V, and the full solution can be written like this only in terms of the scaling.
Full metric.
The R dependence always comes from R.
Okay.
Of course,
This is not.
a separate tau dependence from that you have this one, there is some similar.
So see, whenever there is, it is independent. See, whenever there is an R and V dependence separately written, you can write it's RV and V.
Yeah, so you say that this origin is from this.
So whenever this boost invariant things are written in RV and V, it's basically RV part is characterizing the stationary part, and then there is a separate V dependence which you take care. So that dynamics is very cleanly separated. That's the reason you do it like this way. So now, here I have again just written the metric, and this is a symmetry so that we remember all the thing. Now small amplitude dynamics, whenever we are saying small amplitude dynamics, we mean the following. This metric functions x, omega I and hij could be expanded like this, and they have an epsilon multiplying these fluctuations. And x equilibrium is value in equilibrium, which is a function of RV, and therefore has the isometry, and the epsilon thing is the correction. And this linearized perturbation could be viewed as an excitation around a boost invariant background, and therefore could be neatly classified in terms of boost weight. So it's like a symmetry in the background, therefore.
Suppose we start from this Bondi gauge metric, and so can we arrive at this from there?
Actually, you have to tell me what exactly is the Bondi gauge metric.
I don't remember like that form, but it's like
What I checked is that you start with some arbitrary gauge metric, like Gij, G mu nu, all components are non-zero. And then you can order by order in R expansion, let's say R equal to 0 is the horizon you impose, therefore GVV component or tau tau component vanishing at R equal to 0, that much you impose. Then after that you can do an R expansion. And order by order you can impose these gauge conditions and bring it to that. So there may be global issues like finally this R coordinate is caustic or something, but locally around R equal to 0 you can always bring it to this form. So that could be, you can even set up a code where you just put in the metric, it will keep on doing it. At the moment it's just a near horizon metric in an R expansion. These are, I have been told these are Gaussian L coordinates. So since this could be, so it's like the perturbation, epsilon perturbation is a linearized perturbation around a background which has a symmetry. So therefore excitations could be classified, and then boost analysis, boost weight analysis, that will constrain the structure of any tensor component in terms of the metric functions and derivatives on the horizon, derivatives on horizon R equal to 0. So I'll not give this is a really detailed way of change, how many number of derivatives could be there, how they could be put to this side, that side. It's a very detailed kind of analysis, but in the end it is this. In the end I think there is a background which has a symmetry, therefore the linearized excitations are all classified according to the background symmetry. And I also should note we have not yet done it, so the whole symmetry is actually much larger than just a constant C scaling. C itself could be a function of xi without affecting the affineness. Boundary, so far we have not solved any equations. It's like this is the metric and that's it.
So, but I'm saying that people have found that you can, like I think there is this analysis by Daniel Bromiller and all, like near horizon symmetries, and depending on like how you, what kind of boundary conditions you put, what kind of terms you allow or not allow near the horizon, you can have different kind of symmetry. So you can have a Heisenberg symmetry versus something else. I think that's
Okay, I will be able to
you
comment
also
on that.
classified, I think, some of this, all of these symmetries are
Many of the symmetries are classified in this BMS symmetries on null surfaces, and they are classified according to that. I think it's a subgroup of that whole big class of symmetries, but I can't see how it will depend on boundary conditions because I have not solved any differential equations and just the metric around the horizon we are using.
allow
So if you constrain your perturbation in some way, that it depends on that, doesn't depend on that, it might lead to some further symmetries because you are constraining. But otherwise at the stage, there is no equation, so no boundary condition at the moment. But the actual symmetry is much larger than just this, just a constant scaling, I think. So therefore, I think there will be a much larger class of constraints than what we have imposed. But just imposing this much, we could get a lot. So, the other symmetries, okay, I have no slides on this, but let me still, since you have asked.
Now we have a board and a pen.
Okay, now, but then I have to go there. If I needed, I'll go, but let me finish here. So this C could be a function of xi's, but still it will remain a remain an affine parameter V. It will not affect the affineness. But C, if C is a function of xi in the coordinate transformation, it will generate a lot of terms. So you have to again tune xi's, tune R, everything, so that it again comes back to this form. So it will give a non-trivial mixing, but in the end it's still a symmetry. So it will, I think that will give many non-trivial constraints on everything, but we have not yet analyzed it. Okay. That I don't know what it is.
If you have some null surface and these two manifolds across this null surface, then there is a freedom in how much you can stitch, and that is it's roughly similar to what you have, where R goes to some C, some function of the transverse coordinate times R, and B going to some
Okay.
function of the transverse, one over that.
Okay. The moment we have only one null surface, not two, but maybe that symmetry is somehow interpreted with this symmetry. I don't know. Now, in particular, it says that the VV component of the equation of motion, full higher derivative equation of motion, that has this following structure on R equal to 0. It could be written as this, del V of this whole quantity, where JV and JI are something constructed out of those X, omega I, Hij, their derivatives and everything. But this will have this a total derivative and this kind of structure, and then order epsilon square correction, which we have not looked at. So any higher derivative theory, this is very non-trivial. The showing of this, even it takes a lot of time. We took a lot of time. First, there's a paper by Aaron Wall where he did this thing up to del V JV, but few terms were not working. We explored them, and we saw that this becomes like a current. And then the whole, whenever there is an VV like this, it turns out to be this kind of a form at order epsilon. Let's say at the moment just gravity. So let's say pure gravity. So this statement is for pure gravity. So Riemann tensor, all derivatives, everything. Yeah.
But then you use you evaluate with respect to the method, you get some equations that depend on the functions, and then you process those.
Process with this symmetry, it turns out to be this. And you don't need any details of, like, for any higher derivative theory, this will happen. So that's the
J would be a function of
Ji is a function of this X, omega Ij, all this metric and their derivatives. It's also of the Lagrangian of that. Depending on which theory you are doing, it will have different forms. The number of derivatives in JV also will depend on, see, there are two derivatives are already exhausted. So if you are an n derivative theory, JV and JI will have n minus 2 number of derivatives, because they have already taken two derivatives. Only at the linear order.
One question is, can you see that this entropy current is similar to, like, if I take AB component, is similar to the wall entropy times some mu or something?
It has to be, right? That's one of the conditions. If you just get this, that doesn't say that you have proved entropy increase. JV also should reduce to world entropy in equilibrium. U mu if you have a velocity, at the moment no velocity, but JV will, integration of JV will also reduce to world entropy. That's also built in the proof, even if we start from world entropy and then correct it in epsilon. Okay. That's a starting point. World entropy is somehow the starting point. Actually, we have done it order epsilon, this epsilon square correction. After that, Harvey, Real, Kovac, and Holland, they wrote one more paper, a big one, where they calculated the order epsilon square piece also. Using the same, then you have to do some Clebsch gardening because there are two Boost-Choate terms taking product of them, something like that. So they did that, and the same painstaking analysis they did, and what they found is that along with this structure, you also get another spatial total derivative, which actually bothering, which is kind of saying that this way it will not work till the end. But
They take, say, let's say n number of derivatives in the Lagrangian at a time, and then they need to analyze this. And recursively
they did another recursion, which is this, and this EVV, this one is completely true for all order in coupling constant. There is no expansion. They have done an effective theory kind of thing, so they kept on substituting. But we also would have done effective theory had we not got this form without effective theory. So using effective theory is fine, I think.
whether at the end of the day, when you consider all possible derivatives, would it, that extra term that they're getting, would it reduce to zero or something?
I don't think so. That is not possible. That I don't think will happen. By the way, in the, like with Loga, we did it for Gauss-Bonnet before Harvey-Riel to all order in this coupling constant. We got extra term to all orders. It never goes to zero. It's there.
One line question, so up to order epsilon, that relation that you have, that's an exact equation relation, right?
Up to order epsilon, this is exact. Up to order epsilon square correction, this is just exact. So you take an equation and rearrange. It's a rearrangement of order epsilon terms in the equation. That's it. Okay. Now further, by explicit calculation, one could see that at two derivative level, we can do explicit calculation. We can see that the order epsilon p square term has a positive sign. So assuming that in a generic situation, an higher derivative term cannot change the sign of this order epsilon square piece term, which is coming from two derivative term, then it will neatly say that this particular thing, EVV equal to 0, will tell me that this del V of this thing is actually negative definite. So just getting this EVV is not enough to show that we are getting entropy positivity. We need some more things. So the first thing is that using Boost-Choate, we could rearrange EVV in this form. Second part is that this order epsilon square piece in two derivative we could explicitly compute, and we have seen that it's always positive definite. So therefore, this thing is negative definite. The thing that we got is negative definite. This one is negative definite.
Could we have just like given some physics reason, like without doing the explicit calculation, why the epsilon order term should be 0? You got it to be exactly 0, and then only the next order finite term is the
Okay, that's not written, but I'll say that why epsilon order term in the end turned out to be 0. So what we have got is this, that this term is negative definite. Okay. Now the final argument is like this. Let's consider something that is there inside the bracket, this part as curly r. And what we have got is del V of curly r is negative. So curly r is a monotonically decreasing function of V. And also at V equal to infinity, when the black hole will settle to some final equilibrium, we could show that this curly r will vanish. Ji will vanish. That's also again using some Boost-Choate analysis. You can show that then it will reach a boost invariant situation, and therefore Ji and Jv, which will have non-trivial Boost-Choate, will vanish on the thing. So this will vanish at V equal to infinity and monotonically decreasing for all V. So therefore it is positive for all finite V. So that's the argument. Now the thing that you were asking, what we have found that the order epsilon piece has to be positive for all finite V. But you see, epsilon is something I am perturbing outside. It's an amplitude that external agent is giving. So we can always change the sign of it. And therefore, if for positive, if there is a structure, if we compute it in a theory and we got something here, and we say that this is always positive, it will multiply it by an epsilon. So therefore, if I change the epsilon, it will be negative. And therefore, it will be violated, whatever we have proved. So it could only be valid if the structure that we are considering is identically vanishing. So the order epsilon term, if you write it in this form, is actually 0. It turns out. But that will not use it. For our proof, it's not needed. If it is positive, negative, negative, definitely doesn't matter.
the last equation that you wrote, I thought, the red equation in the second one, so you have to integrate GV in order to get the answer.
Sorry. We have to integrate GeV over the spatial sizes to get the entropy. or is this the world entropy density in that sense if you have a non-compact horizon. So we could interpret the first line, there should be an entropy density. So we could interpret JV as entropy density and JI as spatial entropy current on the horizon because JV reduces to world entropy and is positive definite satisfying second law. So if such structure continues to all orders in amplitude, it makes the gravitational second law ultra-local, that is entropy is produced at every point on the dynamical horizon. So it's locally being produced. However, note that this is a sufficient condition for the second law, not necessary. So if we say that second law is something that will produce entropy from one equilibrium to another equilibrium which are dynamically connected, it would be nice to have something which is locally increasing, therefore is always possible. But it can happen that it is not locally increasing, or let's say this del V of R is not monotonically decreasing, but still R could be positive. So therefore, the way we have proved it, it's a sufficient condition. If it happens, then second law is saved. But if it doesn't happen, it doesn't say anything. So in other words, if for some higher derivative theory, we could not show del V R to be monotonically decreasing at higher order in amplitude, it does not rule out the theory. But you remember our original grand goal was to use this to rule out theories. Or some, in a higher derivative theory, say these are the basic physical theories, these are not physical theories or something like that. So if this is the method we are using, we will never be able to rule out any theory. So it's,
Suppose you take a fluid like approximation. If there's such an approximation, which should exist based on those. So will the entropy current be local in the fluid approximation?
that's what I'll be doing. That's the main thing of the talk. That's why I'm not giving the proofs. But that'll be. Okay. So summary so far. So zeroth and first law have been proved for black holes in arbitrary higher derivative theories of gravity. The second law has been proved only for dynamics of small amplitude. And in fact, the thing that I said, the real have extended this method to higher orders in amplitude and shown that del VR could have terms that violate this monotonicity. So that doesn't say anything. Like it could have terms, but as I said, that it's being a sufficient condition, it's not working, doesn't say anything. So now, can we use holography to improve the situation? So usually we use holography to learn something about field theory. So here we will do the opposite. We would use it to learn something about gravity. So now we shall explore whether fluid gravity duality and our knowledge about entropy currents in fluids give some insight into the construction of gravitational entropy current. So fluids, I'll just give a brief description of what I mean by fluids. So fluid describes slowly varying near equilibrium dynamics of some large thermodynamic system. And we'll consider uncharged fluid, but so variable of the fluid in our case is the 4 velocity u mu, temperature T and other conserved charges, but we will not be considering here. And the equation in absence of any conserved charges is just the stress tensor conservation equation. Input is the constitutive relation and transport coefficients. So T mu nu expressed as a function of u mu temperature and derivatives. That's the input in the fluid dynamics, and then you process the equation. And the approximation used is slowly varying, which roughly means that temperature is much, the more derivatives you have on temperature and velocities in the construction, the terms will be more suppressed. That's the regime when we are in we can use fluid description. So one can use derivative expansion. So derivatives are the expansion parameter. Now entropy current in fluids. In dynamical fluids, we could always construct a covariant entropy current S mu such that S0 is S time, the time component, reduces to the entropy density in equilibrium. Del mu S mu in every dynamical situation, del mu S mu is positive, always entropy is being produced in every dynamical situation, provided the transport coefficient satisfies certain relations and inequalities. So there exists an algorithm to construct S mu order by order in derivative expansion. So if the appropriate constraints are satisfied, we can just construct the S mu in fluid. And the construction is not, but the construction is not unique beyond the equilibrium. Any such conservation kind of equation, you can add something to it without affecting the, you can add identically conserved currents to S mu without affecting del mu S mu being positive. So those kind of ambiguities are anyway there. But it could not be extended but it could be extended to all orders in derivative. It's not unique, but it could be extended to all orders in derivative expansion, and no amplitude expansion is needed. So, this thing we know in fluid dynamics how to do it. Now, fluid gravity duality. So, black brains with slowly varying dynamical horizons in ADA space could be mapped to holographic non-gravitational fluids on the boundary. Holographic fluids have a very specific constitutive relations, which is dual, which is derived from the gravity calculation in the bulk. And metric dual to a fluid with velocity u mu could be conveniently written in this following gauge, where this horizon is at rho equal to 0, u mu at the coordinates along the boundary, and constant u mu lines are null geodesics shoot into the bulk, making an angle u lower mu, it should be making an angle u lower mu with the surface at rho equal to infinity, and finally penetrating the horizon at rho equal to 0. So, the constant u mu lines map every point on the boundary to a unique point on the horizon. In other words, y mu could also be used as coordinates on the horizon rho equal to 0 surface. But none of the y mu's are affine parameter along the null generator of the horizon in general. So, y mu could not be the same as the coordinate Vx that we used to construct Jv and Ji before. However, the physical quantity defined on the horizon could be re-expressed in terms of boundary coordinates u mu, y mu. So, we expect that the horizon entropy current could be translated to fluid entropy current and vice versa using this map of constant y mu lines, which is coming from boundary to the horizon. Is the picture roughly clear? I have no picture here, but just the lines are coming. Now, how to use it to construct gravitational entropy current? So, horizon entropy current work only up to linear order in epsilon, that is what we have seen. We will map it to fluid entropy current at the boundary using those maps which are invertible, which will still work only up to linear order in epsilon. But then we will use techniques of fluid dynamics, and fluid entropy current will be completed up to nonlinear order in amplitude. We might get some constraints at this stage, because we have got some constraints in the previous constraints in fluid at this stage when we constitutive relations are constructed. Yeah, because the claim was initially any dynamical metric could be brought to RV coordinates. This is also a dynamical. This is also a nice local expansionist derivative. It could be brought.
Because this connection is going from, usually when you do a connection from boundary to bulk and things like that, what is local becomes.
It will not be local, that's the issue. But you can map it.
Yeah, but it has a local.
Here it will be a local expansion. Let me tell you what will not be local. The main locality breaking is happening because, but I will not come here. Main locality breaking is happening because V is affinely parameterized. These x mu's are not. So, affine parameter and non-affine parameter, they are related by a overall scaling along the null. That scaling function is not local.
But does it even have a local expansion?
It turns out, I'll say these things in the blackboard because they are not there in the talk, but these are the crucial thing which I could not finish. The main thing is that the n dot, I'll come to it once we're there. It's not, you cannot say exactly non-local, but some issues are there. It's, okay, this has not worked. It's in some sense, though the paper is put out, it's incomplete in my opinion. So, anyway, I'll tell you, if I get some feedback, I'll be very happy on this. So, techniques of fluid dynamics. So, fluid entropy current is completed up to nonlinear order in amplitude. Then again, it will be mapped back to, that is the proposal, mapped back to the horizon. Then we will get a gravitational entropy current without any constraint on the amplitude, because fluid entropy current does not have any constraint on the amplitude, we will map it back.
So when you say non-linear, so it's still to some derivative order.
To some derivative order. And that derivative is not this derivative, that derivative is not, bulk derivatives are not that.
But the horizon entropy current that you have, we also have in the bulk derivative expansion.
No, horizon entropy current, no bulk derivative expansion. And there we have derivative expansion. No, horizon entropy current is in amplitude expansion, there it is derivative expansion, so there will be some interplay. And so,
the comparison should be made in the overlap of these two.
Overlap of these two expansion. Like fluid entropy current is in derivative expansion, but on top of that you can do amplitude expansion. There is no harm in doing it. So you can always exactly. But we have not gone up to that much, that point. Before that itself we could see. So you should note that this method of mapping back and forth works nicely in case of two derivative gravity. So this we have worked out in two derivative with Loga and my advisor during my PhD. So in two derivative gravity, the horizon area is the gravitational entropy, and it works non-perturbatively, no expansion. It could be mapped to the boundary, and we get one candidate of fluid entropy automatically satisfying these conditions. So this is just automatically happens in two derivative gravity. So now the algorithm in detail. So there are two coordinates at play. One is this metric in horizon adapted coordinate systems, and the metric in fluid adapted coordinate system. So there, one is this RVXI and another is rho y mu. But they are just two coordinates for the bulk metric. So we should be able to transform one to the other. So what we did, we transformed rho y mu to RVXI in an R expansion around the horizon. So once we do that, we can substitute this expansion in the fluid adapted coordinate metric, and we can read off this x omega I hij in terms of u mu, temperature and del mu, because the fluid adapted metric is completely in terms of u mu and temperature. The chi mu nu, we said that's also u mu, temperature and their derivatives. It depends on that. So we could read it off, and therefore we could rewrite jv and ji in terms of u mu and t. Then we have to use some tricks which I have not explained here to make sure that this quantity finally reduces to the expansion to an expression of the form of del mu s mu on the boundary. 5 minutes, okay, good. So this is the almost end. So then we have to use some tricks to make sure that this quantity is not is really a divergence of a current in the boundary. You can substitute everything, you will get an expression in terms of fluid variables, but that need not be del mu s mu, some divergence of an s mu. Note that this is not a divergence because H is only the spatial metric. The determinant of the full horizon metric is not defined, horizon being null. So this is not a expression of a divergence, though it looks like a divergence kind of expression. So we have to convert it into a divergence kind of expression in the boundary. The naive steps we said that just substituting it, it will give me some expression, not necessarily divergence. So we have to do some tricks, and which we did, and we're not describing. If you are interested, I can tell it later. But in the end, we get this this expression. So applying this method for any JV and JI, we get this following S mu current. And these epsilons are just Levi-Civita tensor with plus minus 1 being there. But the only thing is that this n hat in this expression, this T mu and L mu I, these are this mapping function. How x mu is varying with V and how x mu is varying with alpha. Sorry, it should be xi, the horizon coordinates. That part is already there here, and which is making this whole expression of S mu non-fluid like. It has velocities, temperature, and also the mapping functions. How we are mapping the x mu's in terms of V and alpha i's. Sorry, it should be xi. I forgot to write it. So there's no alpha I. So have we solved the problem? Not yet. This is the last. From the perspective of boundary fluid, the mapping functions T mu, which is del x mu, del V, and L mu I, as alpha I is again xi, are not fluid variables. They are like vectors, there are I plus, like n plus 1 number of vectors, but they are not fluid variables. But they are something external, we are giving from outside. So S mu we got this, so is not a legitimate fluid entropy current. And more precisely, the technique of completing the fluid entropy current to nonlinear orders in amplitude will not work if there are external variables present. It works only for purely fluid things. So the future direction, so at this stage there are many possibilities. There might be some special choice of mapping functions that would work. This statement needs some more explanation, but I'm leaving it here. If you are interested, I can say later. No, mapping was not unique because so there are this alpha i's and v's, and you have the only constraint that v is affinely parametrized. So you can choose alpha i's and v's on the horizon. Xi's will go to a point, but what is v and alpha i's? V are xi, sorry. What a V is and xi is. So y mu coordinate will, see there are also mapping ambiguities there, but anyway, so let's say this ingoing null geodesic from boundary to horizon giving me a unique boundary to horizon map y mu point. But on the horizon we have another coordinate system which is this xi's and v. This xi's and v could be, the only constraint on it is that v is the affine parameter along the null geodesic. Apart from that, you can slice this v in many different ways, and you can choose the xi's in many different ways. Expression, this is important. Expression is invariant under the coordinate redefinition within xi, but not within the different slicing of v. So you have these v coordinates, and you can choose, v's are affinely parameterized, but you can choose different slicing of v and call them to be, you can shift the origin of v and you can call them to be spatial sections. So spatial sections can give different slicings of v. So xi coordinates will depend on how you are differently slicing this congruence of v coordinates.
That looks like a differomorphism. I can do a differomorphism and change one slicing to another.
It's not that, this whole construction is not invariant under that diffeomorphism. That slicing is effectively equal to this c going to c times x kind of thing. So that thing is not, the global entropy production is invariant, that we have checked. But JV and JI individually are not. They mix us. It's equivalent to Lorentz transformation, but not really Lorentz transformation. It's like different T if you are in a Minkowski space, you have different T. You can slice it in different way. Writing it in appropriate four vector language will make your whole analysis invariant under that different slicing. But here also you can slice it different way, but we don't know what should be that appropriate four vector language. Because it's a null surface, it's not Lorentz transformation, it's some other transformation that it is doing. So that ambiguity actually, so there may be a very particular kind of slicing which will make this L mu I is also expressible in terms of fluid variables and local, and it might work. So that's what is the first statement.
So in the two derivative theory, this ambiguity just goes away.
Goes away.
Because the area of
Area is, this two derivative theory, this ambiguity is not there. So this issue doesn't appear, everything gets cancelled. All this L mu I function, if you put the details of two derivative theory and Hij, they just get cancelled. We initially thought maybe in actually in Gauss-Bonnet also it will get cancelled, but it doesn't. It's there. We explicitly computed.
So why is not there with
Two derivative theory, this Hij, the determinant of the spatial slicing of the metric, that is invariant under reslicing. Because it's a null, the other direction is null. So if you change Hij, it will not, this determinant will not change.
why are you using the proof equation? I thought this was a geometric construction.
The boundary of a local entropy which you can have unambiguously construct. So you basically can pull it back,
I didn't, the last question I missed.
I mean, with the two derivatives, the distinctions between two derivatives are high derivatives and the form of the proof equation. But I thought the issues we're discussing now are geometric issues. They will not depend on the proof equation.
It's okay, it is a geometric issue in some sense, it is how you were slicing. It makes it feel very unphysical, of course, this whole construction. But you know, JV and JI can mix among themselves under different slicing. Where I'm using, I have a fluid equation. Oh, where I'm using, I have a fluid, this. Here I am using it. Actually, I didn't. This metric we are using, where there is an U mu, this is a particular gauge tuned to fluid. U mu, this gauge is possible provided you have a fluid and there is an U mu.
I mean, that case you can also always trace. I don't think it's specific to
No, this is a very specific metric. It's not a general structure. So, but if it's a very specific metric that satisfies Einstein equation order by order in derivative expansion, then you calculate its Einstein or higher derivative equations.
If I understand correctly, what one crucial point of the construction is that there exists a local entropy current at the boundary from fluid mechanics, which you can pull all the way back to the horizon, and for that you use some geometric techniques, but you have to first have that local entropy current at the boundary in the first place.
But at the moment, I am not pulling back from boundary to horizon. I am just taking it up from horizon to boundary and trying to see whether I am getting a local fluid entropy current there. In the whole construction as such, I have not used this. This is just a structure of the metric. But this is a very specific metric. Chi mu nu has a very specific form.
So even if you're out of the fluid gravity approximation, you're away from fluid approximation, you will still give a local boundary current at the local entropy current at the boundary?
No, that it will. Okay, let me just rephrase. That's not what I'm saying. Let me rephrase it. So this is, there is a, if this kind of a metric is there, whatever I have discussed in the talk, all the process will go through. No more details. You just have some mu, let's say. Nothing more than that has been used here. Now that thing, so if you have done this, you have taken up the, first say the equilibrium horizon entropy current, pulled it up to the boundary. Then you are saying that that boundary current or whatever you have got in the boundary is an entropy current for a fluid. That will happen provided this metric satisfies Einstein's equation and therefore have Einstein's or higher derivative equation and maintains fluid gravity duality.
When you say fluid, you mean that there is some derivative expansion?
There is some derivative expansion. So this satisfies equations in derivative expansion, and then you can you are taking this horizon entropy current to some structure in that derivative expansion metric. It's a very specific, completely known metric. So depending on what higher derivative corrections we are adding, and you'll take it up there, and then you expand it in terms of those fluid variables that are appearing in this metric. But the process does not use as such, as you said, that this is a fluid metric. The process goes through for any kind of metric, but that will be an entropy current of a fluid metric, and therefore you can complete it non-linearly only if this is a fluid metric. If I think what Ian says, that's what only he expressed. So this is the same thing. So entropy current, and then so the completion and everything is focused. So far process is working. Okay, now let me come. I think I've finished. Okay. So there might be a special choice of mapping. What I mean, the special choice of slicing, which will work. And construction of entropy current, even in the gravity sites of several ambiguities, which might be used to finally get a JV and JI, where all the dependence of mapping functions finally gets cancelled. Like the way, if you use this mapping construction, even for two derivative gravity to begin with, everything will be there. And in the end, you will see everything will get cancelled. And finally, you will get a normal fluid entropy current. All the mapping functions will cancel among themselves. Or maybe a good higher derivative theories are the ones that would, that's very speculative, that would lead to an appropriate fluid entropy current entirely in terms of fluid variables on the boundary. So each of these possibilities need to be explored in detail, and we have left it for the future work. Thank you.
So thank you. We are running a little bit late, so my idea is that let the next talks get over, and then we'll come back to you. You're not escaping. Ask you questions after the session is over.
Okay, so we have a double whammy now. We have two back-to-back talks by Tanay and Hareram on. It's combined two-hour session on black hole complementarity from microstate models. 55 and 5. This is Tanay, by the way. Part 1.
Hi, so I'm Tanay, Hareram is sitting here. So we thought instead of giving two separate talks, we'll do something like the thing Indian musicians do. We'll have Jugalbandi, some back and forth. So let me start the concert. So the talks are based on the pointer doesn't. Based on this older paper in 2020 and a couple of follow-ups which will come out hopefully soon in a couple of months or so. So this is how we've structured the talk. It's basically two parts, so we'll break for coffee or something after part 4. So let me start by a quick motivation. So let me start with black hole complementarity. So this was an idea put out by Susskind a long time ago, that information is both inside and outside an old black hole. By old you mean something after the page time. But no observer can verify both copies, so there's no issue with cloning. So there's no issue with cloning of quantum information. And this is a consequence of the following 4 postulates. The first one is just unitarity of the evaporation process. The second one is that effective field theory is valid at the horizon. The third one is, I think, what's called the fundamental dogma nowadays, that a faraway observer sees the black hole as just a usual system with discrete energy spectrum. And the last one is that there's nothing weird happening at the horizon. There's no drama at the horizon. The infalling observer doesn't feel anything weird as it crosses the horizon. So if you use these 4 postulates, EMPS and before them actually Mathur also argued, using the strong subadditivity, that there's an issue. So if you consider 3 subsystems, so there's some radiation which has been emitted early, there's some radiation which will be emitted now, which is called delayed radiation, and there's the black hole interior. So if you factorize the Hilbert space into these 3 subsystems, you find that the strong subadditivity does not hold if these 4 postulates are valid. Or put in a more simpler way, if let's say some Hawking quanta are emitted now, the Hawking quanta are maximally entangled with a part of the interior. But we expect that the emitted radiation should purify the early radiation. So the emitted radiation is also entangled with the early part. So this late radiation is maximally entangled with both the early and the interior, which is impossible because of monogamy of entanglement. So this leads to the AMPS paradox. So Harlow and Hayden found a kind of loophole or found a way to get around this, and they argued that the complexity of decoding information from the Hawking radiation is exponential in the entropy of the black hole. And so many of these measurements that are involved in these paradoxes, for example, to verify that there are 2 copies of information inside and outside, these measurements cannot be performed even in principle. So I'll describe a more concrete test of complementarity later when we come to information mirroring, where we'll see how this complexity can save us. So this was just a quick recap of what is known about black hole complementarity. So what we are trying to do is create a toy model of a black hole microstate and try and understand these issues, try and understand how the model processes quantum information and see if it's similar to a black hole. So these are some of the questions we want to address. So firstly, how does this principle of complementarity, or these 4 postulates, how do they emerge from a microscopic description, or how can we see from a more microscopic description how information is encoded inside and outside the black hole? We also need a more precise understanding of how information is encoded in the Hawking radiation or in the interior. So you've all, I'm sure, seen the recent progress in the page curve story. So there we know that you can see the page curve from the semi-classical black hole, but we don't precisely know what measurements I need to do in the Hawking radiation to decode the interior. So this is a question we need to understand. And so we ask if there is some microstate model, if we can construct a toy model of a black hole horizon, which is not fully semi-classical, but there is some local semi-classicality, as Hareram will describe. And can we see how complementarity emerges without encountering some of these paradoxes that I mentioned? So I'll now ask Hareram. He'll describe the model for you and some of the checks which show that our model is well behaved indeed.
So, yeah, with all the motivation Tanay has given, we are interested in to understand the underlying mechanism, how information mirroring works in a black hole. So to study that, we propose a phenomenological model and study the dynamics of it. Yeah. No, here's the, yeah. So our model is inspired by the idea of fragmentation, which proposed by Maldacena and Brill. It says that the near horizon geometry of a near extremal black hole can fragment into multiple throats by instantons. And when these like 2 or more ADS2 throats comes together, then a large number of low energy states appear at the boundaries of the instanton moduli space, and when these distances are sub-Planckian. We refer these large number of low energy states as hair. So this is a cartoon of our model. So as you can see, these drum-like structures are the ADS2 throats, and these wavy lines are the gravitational charges or these low energy excitations, which we call as hair. So these are two main ingredients of our model, this ADS2 black hole and this hair charges. So I'm going to explain each of these component in detail. Yeah. So, so this is the JT gravity action. As you can see, the phi here is the dilaton field, chi is the scalar field which is not coupled to phi, and the last term in the action is the Gibbon-Sucking-York boundary term, where if you see this phi equation of motion, this is basically r plus 2 by L square equal to 0, which is says that metric is locally ADS2, and the scalar field simply follow the Klein-Gordon equation, and then the last part, the last term, k is the extrinsic curvature, phi is the boundary value of the dilaton field, and u is the boundary time. Now, the JT gravity has this SL2R symmetry, which has the corresponding other charges are Q. So we represent this Q as 3 component Q0, Q plus and Q minus, which are coming out from this is infinitesimal SL2R transformation of this form, where delta TU is 1 TU and TU square. For usefulness, we define a local thermal time, which is tau of u with this equation 2. And these SL2R charges, you can write in terms of T of u and tau of u back and forth. So I have written in terms of tau of u. So this is the SL2R charges, and you can make the map unique by setting tau at u equal to 0 as 0. So these are some ingredients that the SL2R dot product is defined by equation 6, and the Casimir of the SL2R charges is minus 2 Schwarzian of Schwarzian derivative of this time t, where Schwarzian is this f triple prime, that standard notation. And yeah, this is a useful identity equation 8 we can use. So a small I is the each site, the qi 0 prime is the derivative at each site, its lattice site. Yeah, every throat has its SL2R charges, yes. Yes. This one, right? Yeah, we were working with 2 dimensions, so the boundarily 1 dimension. So it's a we are okay. This is a schematic diagram, but we are studying a chain model with periodic boundary condition. Yes, yes. Each side is an ADS2 black hole. Each side is and they are interacting with this hair-like structures. Yeah, hair-like structures have SL2R charges. Also, these ADS2 throats have SL2R charges, because the ADS2 have this SL2R symmetry. Yeah, yeah, yeah. ADS2, yes, yes, yeah. Yes, yeah. it's an inspiration. Yeah, yeah, yeah.
Okay, the kind of picture that we used to have is that you're putting some kind of quantum dot at each psi table lattice, like I said, like SY table quantum dot. Right? Then this is spherical by. So the idea to put this n raised to floats was that you can put this kind of simulatively also in the amplitude.
Okay. Yes. Yes, yes, yes. Yeah. Yes. Yeah. So yeah, here you have this Q is related with tau of u, right? And I define this tau of u are related with T of u with this. So you can basically write Q0, Q plus, and Q minus in terms of T in principle. Yeah. So basically, you remove this e to the power 2 pi tau I by beta, and the other terms is basically t triple prime by t prime square minus t double prime by t prime q will give you q0. Q plus will give you this tau triple, t triple prime by t prime square minus t double prime square by t prime q. That will give you the q plus, and the third one q minus. No, here I have T of u is tan half. This equation 2 give me the relation between T and tau. Yeah, yeah, yeah. Tau is beta, yeah, yeah. Yeah. Yeah.
This comes from the composition rule of the Schwarzschild. So of course, the usual SL2R of T of u, the fractional linear transformation will become something else on tau.
Yeah.
Yeah, so both these things are implied in SL2R, but the SL2R on tau of u is different from a fractional linear transformation because it's because the relation between T of u and tau of u. So what is fractional linear transformation on T of u would be a different transformation on tau.
Tau of u.
But this simply comes from the composition rule of Schwarzschild.
Yeah, I will come. Yeah. Yeah. Should I proceed? Yeah. So, yeah. So this is the holographic dual of the localized state at each site, which is represented by T of u. That the dual description is an ADS2 black hole with a time-dependent mass m of u and a time-dependent horizon rs of u, and the metric is given by this equation 9, where the ADM mass is m of u is kappa of 1 over rs square u, and we set kappa to be 1 in the following slides. So how to get this m of u, identify m of u from T of u? To do that, we do a gauge preserving diffeomorphism as of equation 11, and the metric maps to form of equation 12, and provided 1 over rs square is minus 2 Schwarzian T of u. So you can forget whatever I have told before, but you can just the taking story of this previous slides, that the SL2R lattice charges Qi of U represent adhes to black hole at the corresponding sites with masses this. Mi of U is minus 2 Schwarzian of T of U, and this T of U represents the dual localized states of these black holes. So this is the second component of our model, which is this, if you remember, this wavy lines, which are SL2R Hare charges. So at each site we have this additionally have quantized SL2R Hare charges, which are propagating basically, and they follow this discrete version of Klein-Gordon equation, which is equation 15. Yeah. Now the next thing is we have to our ingredient, and we want to couple these two ingredient. And before coupling, we need this following requirements, that instead of each site, we know each site have this SL2R symmetry. Instead of having SL2R cross SL2R cross SL2R like n sites, we have global SL2R symmetry. And second thing, we must not violate the causality. That means if we give some shock or put an infilling matter into a particular site, it shouldn't affect the other site instantaneously. And the third point is our total energy should be conserved. So yeah, so this is our equation of motion. This is mi prime is this, and this is the equation of motion. The second is the equation of motion for the Hare charges. If we with this equation of motion, we have a conserved energy of this form equation 17, which we define like this. Sorry? Yeah, okay, this bold Q is the Hare charges, and this other Q is the SL2R charges on the of ADS2. Yeah, yeah. Now with having the equation of motion, we are looking for solution for this equation of motion, and we're looking for a solution which can give us a microstate solution. And we say that the stationary solution are basically the microstate solutions, for which the Mi are time independent, hence the Qis, and the SL2R charges on the throats. And then the Hare Qis are superposition of two components. One is the static part locked in with this SL2R charges of throats, and the monopole part. So I will explain what I mean by locked in and decoupled in the following slides. Yeah. Yeah. No, bold Q are these squiggly lines, like the yes. Hare charges. Yeah. Other side. Yeah. You can see. Like equation. Yeah. The first one, yeah. The second one is the mobile thing, yeah. Yeah. No, also the hairs. Yeah, okay. Without I'll explain. If you add the hair, that will not disturb the background. There will be a radiation part that I refer as the hair. Yeah.
Some part of the hair gets locked to the thing, so they don't give you independently give up in the microspace solution. And some other hair kind of is decouples from the microspace. So that hair, that part of the hair is decouples, so you can say that doesn't contribute to the entropy. The hair don't have to be SL2R. This is just a model you put in the model that the hair are also SL2R.
Yes. Yeah. The equation of motion. Huh? No, we. Yeah, yeah.
No, we're not looking to, I mean, reproduce black hole microstate counting at all. This is somewhere in between.
Yeah.
Yeah,
Is
it's not completely semi-classical, but we also have something
in the middle
more than
phase.
semi-classical.
Yeah.
It's fragmented.
Other microstates actually account for the entropy and so on. Not this. These are not the microstates that actually.
Yeah, we're not
Yes.
trying to account for that.
Yeah.
The definition of a microstate here is simply all possible
Static cell.
There's not a definition of
The
microstate as in standard statistics.
no, no, not in the static. No, 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 in the not the standard sense. Yeah. Yeah. So, so we have this equation of motion 16. Yeah.
Where does this equation come from? Why does this equation have something else?
This equation of motion 16. Yeah, that's what I was telling. Like we put it in by hand. It just conserved if we follow this equation of motion. Yeah.
the sum of the masses of the throats plus the usual kinetic and potential energy. So you want to write down an equation which has a simple form of the total converted energy. And it turns out that this is the simplest thing. And the first equation is actually like a diffusion equation. If you look closely, it is like box cube with some
Diffusing term. Diffusing term.
So you also want something that leads to relaxation. So that is why it is. So the answer to your question is simply that you want to write down the simplest equation that leads to an energy
Conservation.
of the form, which is sum of masses of the throats plus kinetic and potential energy of the hair. And this is sort of the simplest.
And why is this equation related to the throats? So I mean, you have the lattice.
Yeah.
Radius to throats, and you also have the JT gravity action. Is there any relation between the two?
Because the first equation is what is the equation of JT gravity?
First one, mi primes. Yeah.
So the point is this is MIU is relates to a geometry, which is an AS2 cavity geometry with this mass. The time dependent mass and the AS2 throats have a time dependent mass, which is that. But so JT gravity is simply analog of the gold cube, like you can think about the equation. And look at GM by GU, and the equation is JT. Yeah. So what is all cube there? I mean, there are. It's a discrete version. So the right hand side is basically some kind of null matter that is falling inside the rich soul. But this null matter that is going basically a shock here, not really a shock. It is like a very diffuse shock. It's not very important. There's no localized. It's not localized in time, but it's clear over time. That is coming from the through the hair. So basically, the hair is transmitting some kind of null matter falling inside each soul. And this is something that you can write down from an action, but it's a little complicated. So by lighting, you at some point will have a null matter.
Yeah. Yes. Yeah.
What is the physics that one is trying to model here? Or what are you trying to
Yeah, we'll show that. If we start from a microstate and we sock a model, we go to another microstate, and how the information, suppose position of the sock and the time ordering of sock, we can exactly find out by studying the Fourier components of this equation. So that I'll come to later.
No, the final goal is to study information mirroring.
Yeah.
So there's this Hayden Prescott protocol, they just have circuit models with random unitaries. They don't have dynamics at all. Point is to go beyond, to have a dynamical model which does mirroring.
So this is supposed to model the dynamics of things you throw in and how.
This is supposed to model a black hole horizon, and we want to study what happens to quantum information with this model.
Throws in. Yes. Yeah. Yeah.
Yes.
And these cubes contain information about things that you threw.
Yeah. So this the information are basically in this bolt queues. One of the component of the bolt queues which I refer as here. So the information are in that part.
We
site. Yeah. Yeah.
So this is simply some kind of microscale solution.
Yeah. Yeah. So if we follow equation 18 and 19, you can see that the equation of right hand side of equation of mass vanishes, and equation 20 basically says you the right hand side of this qy double prime gets 0. So yeah, so the microstate solution, now we claim that this is the sort of the zero component of this ADS2 charges is Q, which is each site has the same direction, and plus minus is some random and constant that can be anything. Yes. Symmetry, yeah. And this bold QIs are two part. One is this monopole part, which is equation 21, and the second is the locked in part, which is this equation 20.
So now keeping lambda is related to usually what? I mean, if I look at KT,
Uh-huh.
sigma is just arbitrary.
Sigma has the mass dimension 1. Yeah, yeah, and arbitrary. Yeah, yeah. Here, yeah, yeah, yeah. So yeah, this is what I mean by hair oscillation. So on the top of these solutions, if we add a solution of the form equation 22, then like my background solution is not being affected, where this small qy's follow the discrete Klein-Gordon equation. So we claim that the full solution is the previous solution plus this qi radiation. The radiating part, which is the other plus minus component being 0, and the 0 component is qi, and small qi follows this Klein-Gordon equation. Now, if you see this energy equation, the first term is sum over mi, and the restriction mi to be positive definite, it automatically imposed because this energy, this is the energy of the q's, which has to be greater than 0. And the third term can be negative, but it is averaged over all the it can be random and it can be averaged over all the sites, which gives you 0. And if my lambda in the second term, total energy can be positive definite. So that's why we choose lambda to be positive. So these are some additional constraint on SL2 charges. So we want our tau u and its first and second derivative to be continuous. And this imposes constraint on Q, which further leads to says that for all sites, either you have tau prime u, your time has to be tau prime of u has to be positive, or tau prime is negative, and we choose tau prime u to be positive, which gives uniform arrow of time in our model. Yeah. No. This is no. Yeah, see, you see this QI lock has this QIs. So those are randomly chosen. So hence, yeah. Yeah, so we have this nice split of energy that in the hairy microstate we have non-trivially neat split between the interior and exterior components, which is this first part is the like the gradient kind of a thing, which is EQ potential. Second is the monopole part, and third, which is decoupled, and third part is the monopole part. Third part is the radiating part. And this is only happens when there is a microstate solution, not in between. Now after having the solution, we looked into the question that does our black hole model works and talks like does our model works and talks like a black hole? So how do we answer that? So we throw a compact objects like in form of a sock and see what happens. So for our model to be phenomenologically viable, we need to satisfy the following conditions, that we start from a microstate, give a sock, and it do some evolution, and eventually it relaxes to another microstate. The second is whatever energy we inject into the model, that energy should goes towards the increasing of the total mass, and the individual component of the energy, that is this bold Q and other Q, should be independently conjured to good approximations. So this is the sock we are giving in the TEU is which is Fi of U, and other are 0. So when we give the sock, the equation of motion becomes this. There is just additional term in the mi prime, the delta function. Yeah. So you can see the energy plot. This is a 5-side chain model. So if you see this, this is the this is the energy of the mass. This is the total energy. Sorry, this is the total energy, and this is the total energy. This is the energy of the hair. Sorry. Yeah. So you can see when you give the sock, the hair energy doesn't it is conjured, and the total energy whatever is given is get into this mass. Sorry. Initially there is a small oscillation, but eventually they settle up. Initially there are small oscillations on these scales, we can see it, but initially there are small oscillations, and on the end they eventually settle.
So as you increase the number of sites, the change in the hair mass, the hair energy gets tinier at that.
Tinier, yeah.
So
Yeah.
I thought initially, as you said, there is some extent or type configuration.
Mm-hmm.
If I throw a compact object, the probability of going into one side
Yeah.
will be exponentially suppressed to the minus energy of that side. And is that true in this model?
Yeah, we only one side. Yeah, we are talking here only one side. Sorry. Yeah. No. We are just talking in the one side. Yeah. Yeah, this one. Yeah. Yeah, other one side. Yeah. Yeah, that is the amplitude, like the total. That is the amount of energy, and U and U as the moment we are giving the energy. No.
Maybe we could take it as
Maybe. Yeah, maybe. Yeah.
I think it's different. So you say that it gets stuck in a microstate. I thought that, you're right, because they're exponentially suppressed, the number of transpose exponentially large.
Large. Then you can do it.
Phase measure compensates for.
But here I think it is the probability of transition is always transit on the. But the question is whether you can distinguish them. That's a different.
That's the different question. Yeah. Now. Yeah. So this is the energy plot after the sock, And this is the mass plot. As I have said that we have socking only one side, that is the site 1. You can see this green curve suddenly picks a jump, and eventually all the masses relaxes to constant value. And this is the charge plot. So this is the this is important. You can see this is the zeroth component of the Q. So you can see it started with a particular direction, and after the sock, eventually they go to the direction, but that is the same for all sides. The Q, the zeroth component is same for all the sides. Yeah, it has to happen. Yeah, that's a thing that goes to another microstate. Yeah. And this is the Q plus and Q minus plots. In the final microstate, they can be random. So yeah, so Q plus and Q minus are this. Yeah. Yeah. So now I would ask Tanay to introduce about information mirroring. And
Right. So as you were asking, what are we trying to describe with this model? The idea is to, at least to begin with, to try and describe information mirroring. I'll tell you what it is. So this is a picture from Harlow's Jerusalem lectures of a model for information mirroring. The original model was from Hayden and Preskill. So they model a black hole as a random unitary U. There is a diary D. So Alice wants to hide some information from a authoritarian government or something, so she throws it into a black hole and hopes that it gets destroyed. So that's D. So D is entangled with some reference system S, maximally entangled with S. B is some initial state of the black hole, which is maximally entangled with the early radiation E. So there's some radiation which has been emitted, which is entangled with the interior B. And then there is the random unitary U, which evolves the black hole system forward. So Alice throws D into the black hole B, the unitary acts on D tensor B, and you get a different state of the black hole B prime and some new emitted radiation R. So R is the late radiation, E is the early radiation, D was Alice's diary, B was the initial state of the black hole, and B prime is the final state of the black hole, and U is Haar random unitary. So now what happens in such a process? So for this process where D is maximally entangled with S, S is just some reference system which simplifies the argument. So what Hayden and Preskill argued was that S and B prime have zero mutual information. So S and B prime have zero mutual information. That tells you that the information of Alice's diary is not in the interior at all. So it must have been leaked into R tensor E. So S and B prime have zero information, therefore the information of the diary is in R plus E, where E was the early radiation. And the argument is rather simple. This is similar to Page's old argument, which just uses sizes of quantum systems basically. So the integral is just an average over a Haar random unitary U. And the norm inside is the L1 norm, which is like norm of some operator A is trace of square root of A dagger A. So it's a norm of this difference where rho SB prime is the reduced density matrix of this subsystem SB prime. And we subtract out the product state, rho S tensor rho B prime max, where rho B prime max is the maximally entangled state. And what this statement says is that the difference between these two states is upper bounded by the ratio of the sizes of these systems. So now for sufficiently large radiations and sufficiently small diaries, so note that S and D are maximally entangled, so the size of S and the size of D are the same. So as long as Alice's diary is much smaller than the whole radiation that's been emitted, S by R is a small number. So that tells me that rho SB, the reduced density matrix on SB prime, is a product state. So that means S and B prime are factorized and they have no mutual information. So this was the argument which was used to show that if I throw in some diary into a black hole, an old black hole after the page time, the information of the diary is rather quickly leaked out into the radiation. So you can decode D from R tensor E. And this was called information mirroring because just like in a mirror, if you throw a ball at a mirror, the ball is instantaneously reflected back. So the information thrown into a black hole, an old black hole is just quickly reflected back into the radiation. Sorry, thanks. So the time scale involved here, so for a Schwarzschild black hole is just the scrambling time. It's Rs log Rs, where Rs is the radius, the Schwarzschild radius. Right, so but this poses a problem. That's why I've called information mirroring a test for complementarity, because this leads to a cloning paradox. So let's say Alice throws her diary into the black hole. The information of D is leaked into R plus E. Now Bob is sitting there on the top. He has access to both R and E. He uses some decoding operation and gets access to Alice's diary. So Bob can decode Alice's diary from the radiation and then jump into the black hole and then verify that there are two copies of the information. There was one which was thrown in and one which was leaked into the exterior. But since the process is unitary, quantum mechanics, unitarity tells you that there is no cloning. So this poses some tension. But as I mentioned in the introduction, Harlow and Hayden, and this argument has been refined later, they've argued that the time taken to decode this diary from R tensor E will be extremely large. More precisely, it's exponential in the entropy of the black hole. And note that the evaporation process is some polynomial in the entropy. So Bob won't have enough time to decode the Alice's diary before the black hole evaporates away. So these kind of cloning questions, you can't even perform the experiment in principle. So just like I said at the beginning, you had this AMPS paradox. It's way in the back. I have time, let me go back in here. Yeah, so we had this AMPS paradox which had these three subsystems and you had a violation of strong subadditivity. Even such questions can't be asked in principle because the decoding processes take exponential time in the entropy of the black hole. So that was a supposed resolution by Harlow and Hayden. Sorry? Yeah. Sorry. Oh, I went a bit too forward, sorry. Yeah. So then this is just a quick lightning introduction to the Hayden-Presskill protocol, or what's called information mirroring.
Yeah, but what I'm saying that information, this cloning paradox we're talking about is some outgoing Hawking quanta.
Yeah.
Which has nothing to do with the diary itself. The diary that you throw inside,
Mm-hmm.
there is not, information mirroring doesn't lead to cloning.
Information mirroring doesn't lead to cloning.
Well, okay, it's a different kind of thing. So here you may be able to decode that fast, but you can go inside.
Yeah.
Then decoding it back would be harder.
No, but there are two copies, right? There is S, which is maximally entangled with the diary, and if Bob also has access to the same thing.
So in the information mirroring, the argument that you get, the information is like more like quantum teleportation, because the information is being, because what was initially, information was in S and D,
Yeah.
but now the information gets into R, E, and E. That was the argument. But there is no information in the other system.
Right, there's no information in B prime, you mean? Yes, that's right.
Yeah, so the argument that you get simply means it is like a teleportation, more like
Right.
So this itself doesn't create this code.
Yeah.
The cloning paradox is because of the Hawking quanta.
Because of the quanta which is emitted, yes. But that's R and E.
Yeah, but that's unrelated to the mirroring itself.
Yes.
Because the way you said this poses
Ah.
So sorry, just to again, I think the second to last point is not quite correct. I mean, because in the B prime there is no information.
Yeah, exactly. Because B prime has no mutual information with S. So this is like, this is not, B prime has no mutual information with S, so there's no, within the mirroring there is none, but now there'll be, sorry? Yeah, AMPS has the cloning issue. Yeah. Yes. So there's a cloning paradox in AMPS, yeah, that's still there. Yeah. Right. So more importantly, in this protocol, Bob is able to decode Alice's diary just from R and E. So he doesn't need access to B prime or B. So without accessing anything about the interior, you can decode Alice's diary. That is crucial. And the question is, can this toy model that Hareram described, can it mimic this process? Can we decode information about infalling matter without referring to the microstate itself? And can we see precisely which observables do I need to measure to decode Alice's diary? Yeah, so we'll take baby steps. We'll first try to see if classical information can be recovered, and Hareram can describe information mirror. Sorry? Oh yeah, which observers decode Alice's diary? Yes, thanks. Should we stop now at 11? Okay, we started late. Yeah, then yeah.
Anyway, we are going to continue to the yeah. Yeah, fine. Yeah.
No, maybe if we have 15 minutes, we can continue.
Yeah, we can. Okay. Yeah. So as Tanay has explained, now Alice has thrown a diary into this into our model, and you can see Bob observe this radiation part of the cues and decode the information. Now I'll explain how, when Alice throw the diary, at what site she throw the diary, and at what time she throw the diary. Bob can exactly decode that information. Yeah. So this is the equation motion for the small QIs, if you recall. And if you solve this equation of motion, you find the 5 the normal modes for 5 site, which is basically this plus or minus 30 and plus or minus 18 and 0. There are 5 frequencies, and they are doubly degenerated. So there will be 10 normal modes. So and this is exactly matches with when we do the Fourier transform of the QIs. You can see the peak occurs at exactly those values. So the the phase difference between these positive mode frequencies like plus 30 and plus 18, those phase difference is independent of the microstate and encodes the position and time ordering of the sock. So what I mean, this phase difference doesn't matter from what microstate you have taken or what microstate you have gone. It is independent of the microstate. It solely depends upon at what site you are socking and at what time you are socking it. Yeah, if you see we sock at one site, you can see there is a clear symmetry between the phase difference. So this number says the phase difference of the 2 positive frequency modes, and from that and from the symmetry of this phase differences, we can clearly see that the site which is socked, so if there are 2 sites socked, so the question is at what location you are socking and at what time ordering you are socking it. So the location of the sock are basically the extremum of the phases, and the time ordering depends. If they are nearest neighbor, then the smallest phase was socked first, and the largest phase is socked later. But if they are one site apart, then is the other way. The largest phase difference has socked first, and the smallest phase difference has socked later. No, sigma is the model parameter we are setting to be 0.01. So yeah. Yeah, the value of the frequency changes, but the qualitatively the picture remains same. Yeah. So this basically this algorithm I just explained. Yeah. The next step is we add Hawking radiation to our model. Before we haven't added Hawking radiation. Yeah. Sure.
Yeah, what Tanay was saying earlier has actually Tanay has a point. So she was saying that if you throw some data inside, so there is one copy of the information anyway inside, and the information mirroring is happening. So I think he was saying that you are going to reverse argument. If you want to go back and see the other copy of the data, you do it for able to do information mirroring and able to go back and verify the other copy. But that will be very hard to decode now because
Correct, yeah. But anyway, Alice is outside. Im-
The cloning thing was appears in the EMP.
it's not.
I mean, the whole point is that you should be able to decode with a black hole complementary describe. You should be able to decode the information without knowing the initial and final map. Because you should not have an access to like to go because there are two copies of some whole information, so you should not need to access the interior to decode what is coming. So that's what we see.
So, in order to adding Hawking radiation, we couple each of our radius to throats to CFT bath, which are and those CFT baths are not talking to each other, and they have the same central charge, and we follow the process this Almehri and et al. Followed in 2019 paper. And this coupling leads to the equation of motion. This modify the equation of motion like mi prime. We have an additional term which is minus c of mi, and c is the central charge of the CFT, which comes from the conformal anomaly, and it basically controls the rate of evaporation. So what happens if we add the Hawking radiation? You see, the masses can be seen decaying exponentially, and the rate is different for different site. The Q0 of the each site homogenizes very quickly, and depending upon the initial condition, decaying microstate is realized. But Q plus and Q minus, they also homogenize, but on a much longer time scale. So, okay, so Alice's diary can be recovered from the Q0 after this capital Q0 homogenize using the same algorithm as we have done before. And Alice's diary can be recovered from the Q plus minus after this capital Q plus minus homogenizes a later time, the larger time scale. So now the question is, we have seen this after adding Hawking radiation, the masses decay exponentially and essentially independently with a different decay rate. And this Almehri and et al. They have shown also their masses also showing the same behavior. So we essentially have the page curve for each throat according to for their model. And the next question is, what is the full page curve, as the entropy is additive, because here the hair are classical, so there will be no entangled thing. So the full page curve will be sum of the page curve at the each site. Yeah. So yeah, I'd like to stop here, and the next part I will summarize what I have, what we have shown so far, and the motivation for the next thing, like how we can decode information if we couple a classical system to a quantum system, and Tanay will explain those systems. Yeah.
Okay, so let's thank Tanay and Hareram for a very nice talk. And you want to have some questions now? Okay. 20 minutes. Clap once more. People are coming now. Maybe clap once more. Start, yeah. So that will be part 2.
So yeah. So here I will just recap what we have talked in summary last in part 1. Or can you just full screen it? Sorry. Yeah. So this is the recap that we have identified solutions of our model that can be interpreted as microstates of the black hole. We find that the model mimics the relaxation properties of a black hole after shock. That in before shock it was a microstate, and after shock eventually it goes to a microstate. Classical information mirroring can be observed in a model with or without Hawking radiation. And we have a reasonably good phenomenological model of a quantum black hole that gives insight into the origins of a black hole complementarity. So now what next? Sorry?
In this model,
Uh-huh.
how you model the insight? Is there a sense that there is inside and outside in the model?
What do you mean by interior?
But you said you mirror. So
Yeah,
something
yeah.
was in, something was out. What is?
No, the localized
States
themselves thought of as the interior, and then you have part of the hair which is
outside
locked to the interior.
interior.
The interior is the radius to charges basically.
Yeah, these cues.
Question you had do not have any explicit ADH2s as far as I could tell. The mass is coupled to charges. So in terms of the equations you have, are the sides the inside?
We have the split for the energy.
Yeah, this one. Yeah, so this second terms, these energies, those are logged into the interior.
Can you show the screen
Oh, pointer doesn't. This term, sorry. This term. Right. Yeah.
see if I understand the setup? Is the idea that there is one asymptotic region and that fragments into many regions
Yes.
as you go into ADS?
Yeah.
And why are those microstates as opposed to a multi-separate black hole?
Yeah, so
In higher dimensions.
So here we can do higher dimensional version. So there is of course this original throat charges, gravitational charges. Those are sort of in the throat and they become the hair. So they are not part of the interior description. And but of course they can as a component. I mean they cannot clearly split into interior and exterior. Only in microstates they can do. But then the things that fragment. This is something you model as the interior. So you have this other throats. I think you do this sort of. You cannot really treat them from first principles. You simply assume there is a hard degree of freedom, eventually form or crystallize into a lattice. So this gives some kind of. It's not a derivation from first principles. It's just a little bit.
Yeah.
I thought that the reason they are not multicentered is because you are exciting different sides. The dynamic is telling you there are some states as opposed to like different black holes.
Yeah, the point is to have a local. The point is that there is an explicit description of the ADS2 which is not obvious from these equations. So you can have a local semi-classical approximation, if not global. Because of the fragmentation, you don't have global, but you have a local semi-classical approximation. And that's, I think, what Tanay also described, that you can actually do. So in the next part of the talk, when I think Tanay is going to talk about at least have explicit ADS2, you'll see ADS2 more explicit.
So this, sorry, coming back to the
Yeah.
question, so this ball was the,
Sorry.
so that equation was telling what the split was?
This one, right?
Yeah.
Yeah.
So this, so the middle term,
That is the logged in part. Yeah.
locked
The potential.
part continues to it only. So basically your energy splits up into something purely interior and purely exterior, but only in microscale solution, not in between.
And this is the last part is the radiating part, that is the exterior. Yeah. Alpha is this. Here, yeah. Yeah. The scrambling time, right? So here we have this RS. So RS log RS will be the scrambling time, right?
No, he's asking for a model.
Oh, for our model. It is a lambda. For our model, it's lambda. Yeah. Sorry. Yeah.
It's not directly lambda, but yeah, it depends on lambda.
We actually studied this. How it
Yeah, but time is not 1 by lambda or something, but
No.
it depends on lambda.
Yeah.
the question
It also will depend on number of sides.
It's number of sites also.
So we actually did how it increases with lambda. We don't know actually the exact nature. And so this is may not be a maximally chaotic model either, because you might think that if you introduce more randomness by connecting the throats inside, that can give you more randomness. And,
But then lambda will.
so we don't know whether it's maximally chaotic if that is what you're asking. But it's certainly the scrambling time is very small. It's order of assembly time. So it's going from one microstate to another microstate, and that's a really small time. And it increases with the size of the system. Sorry,
Decreases with the size of the system. Yeah.
for certainly large.
Yeah. So yeah, now we have decoupling of all degrees of freedom, which is crucial for the information mirroring in the above story that we have seen. And we have, but here we have only discussed the classical part. So where the hair are classical. So for our next thing, for a better understanding, the hair needs to be quantized, where quantum information mirroring needs to be studied and better. So in the next step, here exactly what we have done, we know exactly the phase difference of this, what observables we are looking classically, that we observe the positive frequency modes and the phase difference between them, and that gives us the information about the classical information about the location of the sock and the time ordering of the sock. And now when we quantize the hair, we know exactly what, or at least we have idea what observable we should look at. So as a baby step, what we are doing now, we couple a classical field to a quantum oscillator and observe how the quantum information is encoded in the system, and that is going to explain by Tanay in the next part. Yeah, thank you.
Right. So as Hareram was saying, we've only discussed classical information mirroring. So we need to actually tell you how quantum information mirroring occurs in this lattice model. But before doing something as complicated as that, I'll describe something much simpler. So we'll take baby steps first. I'll describe a black hole coupled to just a classical harmonic oscillator and a black hole in ADS2. So let me just recap what Hareram already told you about JT gravity. He's shown you the action already before, and these are the equations of motion. The first one tells you that the metric is always locally ADS2. The second one couples the dilaton to the matter field, and it reparameterizes the boundary time. From U, you go to T of U. Since the metric is always locally ADS2, you can the metric I've written on the slide is a solution to these UMs anyway. Where m is the EDM mass of this black hole, and m is just the -2 times the Schwarzian of the reparameterization, as Hareram showed you. So in what Hareram described, there was no bulk matter at all. But now we have, you can keep in the back of your mind the chain model. But for now, I'm just looking at one throat. I just have one ADS2 with a bulk scalar field, which I denote by chi. It's just shocks, but not scalar fields. That only occurs to, okay, fine, I don't. There is null matter, but this is a scalar field. Yeah. So in this case, we have a free scalar field in the bulk with this particular mass, which is holographically dual to an operator O with this scaling dimension. And you can go close to the boundary and expand the bulk scalar. It has some asymptotic expansion which looks like this. But J is the source and O is the response or the expectation value of O. Sorry? No, for numerics. Yeah. So we will, in what follows, I'll choose J of U to be the position of a classical harmonic oscillator. So J of U is just X of U. So the equations of motion for this coupled system are the first two on the slide, and these just follow from the second equation here, the ones with the phi and the T matter. So the first equation is just tells you how the mass changes in terms of some coupling parameter lambda. X is the position, x dot is the derivative of the position of the oscillator. The second equation is just a driven classical oscillator, where the driving is by this dual operator O. Now with this equation of motion, it's easy to check that we have a total conserved energy, which is E, which is just the sum of the mass, the oscillator energy, plus some interaction term, which is lambda times O times X. Now there were questions the last time Ayan gave a talk on this about the large n counting or the order n counting of these parameters. So in this setup, lambda goes as order n, where n is the usual large n parameter. O goes as order n. That will ensure, if you look at the m dot equation, m dot is some order n square object, and the right hand side will also be order n squared. And omega here also has to be order n. Oh, I should have, there's a half m x dot square, there's a mass of the oscillator which I've omitted here. So the mass of the oscillator will also be order m. Yeah, so we can evolve this system together. What I've not shown you is the Klein-Gordon for the bulk scalar. So we have three equations. These equations for the m dot, equations for the oscillator, and the Klein-Gordon for the bulk scalar with the x of u source. We can evolve those three numerically together. Similar, sorry?
So this is basically an oscillator which is damped by the CFT plasma.
This is basically an oscillator which is driven by lambda O, yeah.
So but once you integrate with the CFT plasma, it's like, a pendulum in air. So you should get a damped harmonic oscillator.
Yes.
So basically you get a damped harmonic.
Yeah, as I'll show you.
Thing is provided by this.
By the coupling to the dual, yes, right. So yeah, as you were saying, if you look at the blue curve here, that's the energy of the oscillator. It goes down to 0. So these are just plots of the energy. The red curve is how the mass varies with time. The blue curve, as I said, is the energy of the oscillator, and there's some interaction term, which is lambda O times delta minus 1, which goes to 0. So you can see, as expected, the black hole sucks up all the energy from the oscillator. The black hole, the oscillator just goes to 0, position 0, momentum 0. This is what the dual operator O looks like. It starts off at some value, oscillates with a decreasing amplitude, exponentially decreasing amplitude. And the plot on the right in figure B is just the position and the momentum of the oscillator. It looks like a damped harmonic oscillator. Now we can ask how the initial state is encoded into the late time ring down of the black hole, or how it's correlated in the late time ring down. These are plots for that. So if you look at the mass at late times, you can see it's some oscillating function. It's oscillating about the value 1.5 with a decaying amplitude. So the amplitude on this, the plot C on the y-axis is the amplitude of the ring down.
So the oscillator equation also goes like h square. Is it like some of the scaling lambda and both go as 10?
Mm-hmm.
So that's more like a quantum.
Oh, you mean the second equation? Oh yeah, omega is order n and lambda O is also order n squared, yes. Both are order n squared, that's right, yeah. No, so it's in some sense a large system or.
Yeah, but some leading in somehow 1 by n correction. I mean, I don't know how to explain. I mean, or it's already n square. Or it's the same order.
Same order as m dot.
Takes place, right?
Yeah, yeah, yeah.
In a one loop effect. So I was thinking if this. Yeah. Okay. Maybe I'll ask you later.
Okay.
No, this is simply classical. Everything.
Right now, just yeah.
No, it's classical, but it's the same order at which the back reaction takes place. Right? Yeah, yeah. Because you're artificially taking lambda last. Okay.
Yeah, yeah. Right. Yeah. So you can look at the amplitude and the phase of this ring down. The ring down is an exponential times an exponentially decaying function times an oscillating function. So if you subtract out the decaying part, you get some amplitude and a phase. And you can plot them, and you can see that the amplitude is correlated with the initial position. The phase is correlated with the initial momentum. There are some outliers. That's because of Fourier transforming. There's some noise. You have to do numerical Fourier transforms to extract these guys. So this was just a kind of appetizer with the classical oscillator. Now we can actually couple a quantum oscillator to the black hole in a similar way. So now instead of
So this last thing, is there just a statement that the environment would also, if you look at the energy of the environment and how the energy is deposited,
Mhm.
you can kind of read off.
you can read off the initial state. Yes, exactly.
Yeah, because this is not like a usual polynomial mode ring down,
Hmm.
which is like quite universal. But because here, because if you linearize the system, you will not find any such thing. It comes from a purely nonlinear oscillation. And that is what is responsible for.
That's not, but the point is that eventually it is just governed by what the oscillator is.
Yeah, yeah, exactly.
I can just look at the oscillator and I can calculate how the energy deposited.
Mhm.
Yeah, but the phase is no problem.
But the phase will also be, will be there. Right?
Correlated with the oscillator. Yeah.
Just look at how much energy is lost.
All right. Yeah. So in the classical case, the source was chosen to be the position of the harmonic oscillator. In the quantum case, the most naive or simplest thing you can do is just mean field. I replace x with expectation of x hat, x operator, and that's coupled to O. So the equations are just modified. I put in expectation values wherever I need to. So the equation for m dot just gets expectation values of x and expectation values of x, the dot of the expectation value of x. And the second equation is just the Schrodinger equation for a driven oscillator, where the driving is time dependent in terms of the position. In this case as well, we have a conserved energy which looks the same as before with expectation values put in. Just again to reiterate, this is nothing more than mean field theory. We are not modifying quantum mechanics or doing anything weird. This is just usual mean field theory. Even in GR we do G mu nu is expectation T mu nu. This is nothing more than that.
But this would be the wrong thing to do if you're doing quantum diagram.
Yes, yeah.
So why is it the correct thing to do?
If you were doing,
If you're just doing like a quantum open system,
yeah, yeah,
if you're trying to map the dark harmonic oscillator and
Mhm.
to find the quantum analogy,
yeah.
this is not how you should do it.
Yeah, yeah. In that case, the evolution will. Here you can see it's a Schrodinger evolution. So in the full open system, it will be a.
So you should have a density matrix.
Exactly. So if I quantize the bulk scalar as well, then I'll be able to.
I think the question is that why you are not doing a density matrix. But we can also do it with the density matrix.
But
But there cannot be a state, right?
the evolution is still unitary. He's asking the evolution should be a CPTP map for an open system.
So it can't be, you can't define a state, right? It's a part of the system. In general, you can't define a state.
Yeah. So here the bulk is classical. So it's like a classical quantum system.
Yeah, but for the full evolution, what you're saying, we'll need to quantize the O as well.
So if you quantize the bulk scalar as well, yeah.
Then we'll get a usual CPTP kind of evolution for the.
After you trace out the. This is what we are also.
But what I'm saying is that, if you just do a damped harmonic oscillator, which is a classical system, to correctly quantize it, if you do it this way, for example, it's not clear that, this captures the physics correctly.
That's true.
Mhm.
But here we are doing something semi-classical. Already it captures some kind of physics because there's energy transfer. Like phase damping after all, but it's okay.
Yeah.
But it captures damping even with this because it couples to gravity. That's the crucial one. Because if you couple it to something like a normal field, I don't know whether it will do it. So you have to actually take both quantum fields and couple it to a quantum thing. Then only and after tracing out, you will find the energy transfer, like irreversible energy transfer. But here you find irreversible energy transfer even with this, even with this.
Yeah, but once we quantize the bulk scalar, I think it should all be fine.
Current or some entropy second law in the gravitational system.
No, I think so. If you have a quantum system, but which is coupled to a classical environment,
Mm-hmm.
I think you should. It's not clear to me that you can do these.
You can have something like an entropy increase and loss of information, provided the classical system is like a fluid or something which has an entropy or something.
But isn't that the case here?
That's the case here. That's why it still captures information. That probably is.
So if you have a quantum Brownian particle, let's say which is coupled to classical field, the same you can write down a Schrodinger equation for the field of quantum.
Sorry,
Let's say I have a quantum Brownian particle coupled to a classical field.
but it's not Brown.
No, as an
No, I mean the particle coupled to the field. That's what I mean by Brownian particle.
Okay, suppose your classical part has some stochastic behavior, then it becomes when you average the inter-equation, it will give you, of course, not a.
No, but the stochastic comes out of it emerges, right? Because
So exactly because now, but exactly. So if you have something that is an entropy current, you can then but this is still an inter-equation. It still shows aspects of irreversibility. Okay, there is something interesting here, which I think if you couple a qubit to this thing, you see an explicit irreversibility. But if you couple some quantum harmonic oscillator to this, and the initial input state is in a small subspace, then you don't see irreversibility. So that's interesting that you want to expect. But there is, of course, still an irreversibility because you have some second law in the gravity sector, so you always have some. The final state is always something like a black hole, static black hole. But it captures some aspects, of course. Yeah.
when you write the expectation value here, that's in a state that was. What is that state now?
when I write this, it's just psi, the one below. So it's the instantaneous psi of t.
Right. So, but I'm saying from agency perspective, that is dual to some classical geometry, right? So, I thought that.
No, you mean the expectation x that I have here?
Yeah. So
No,
I'm
no.
saying that just like Logan said, initially g mu nu equal to expectation of q mu nu.
Mm-hmm.
Then that is in a state, but that state will depend on the classical geometry. So I have to choose the answers for a metric,
Yeah.
g naught, then do recursion. Right?
Mhm.
Something like that. Yeah, right? That kind of
But it doesn't depend because it's on the boundary.
Yeah. You have
No, I
this.
know, but that's dual. The state that you are choosing.
No, this state has no dual. It is something that is coupled to a black hole.
Yeah.
Black hole, if you want the dual of the black hole, is like a quantum dot.
This is like SYK coupled to a psi.
So after this back reaction, the state won't change. The psi will change. Right?
This psi will the back reaction is in the lambda O, right?
Right.
Yeah.
So this is a recursion scheme.
It's like a seven of the right
Mhm.
that is set up. Okay.
Yeah, it's similar to what Sukrut described as. Yeah.
Could describe, but the system at the boundary is quantum.
All right. So this it's well known how to solve a driven quantum harmonic oscillator with this kind of a x driving. The solutions are so let's say you start with some input state, which is some arbitrary input state in the 0-1 fog basis. You can also include higher ones, but let me focus on 0-1 subspace to begin with. The solution to the Schrodinger equation is written in the second line, where f0 and f1 are some phases. Psi 0 and psi 1s look like the usual Hermite polynomial eigen functions of the oscillator, but they are shifted by xp and pp. So the solution psi-n and the solution psi-n are just shifted oscillator solutions, where the shift is given by some function xp and pp, where xp and pp obey the classical equations given on the very last line. So the solutions are just shifted oscillator, where the shift is given by solving this classical equation. F's are some phases. The first term in the phase is just the usual energy phase. It's just h bar omega t times n plus half. The second term is an overall phase, so it's really irrelevant. Yeah. Sorry? Yeah, it's the action, but it's just an overall phase. So this is the full solution to the Schrodinger equation. But now we still have to solve this classical problem with we still have to solve for xp and pp. So we solve the last equation together with the first equation, and that solves the full system. So let me show you what the energies look like first before telling you what the final state is. Again, the magenta curve is the total energy we have. It's conserved, so our numerics are reasonable. There's some interaction energy which oscillates in the beginning and then damps out. The energy of the oscillator starts off at some value, decays and settles down to some constant which is non-zero, and the black hole absorbs the energy from the same amount of energy from the oscillator. The main difference obviously here is that the energy of the oscillator doesn't go to zero completely. Mm-hmm. Because of what you were saying, because it's not, it's unitary.
This is an unphysical thing for a damped carbon coupling. You have a constant energy that is being coupled to the
No, it's not quite, because you see, because there is some self-consistency here, that there's a decoupling between the two systems.
Oh, you mean to have a constant energy, but here the coupling switches off dynamically.
Yeah, so that's a,
It's not just a damped oscillator, it's a damped driven oscillator where the driving is switched off dynamically.
so because you have a, because there's a decoupling, the Hamiltonian of the oscillator is simply its own Hamiltonian. So whatever, even it's a time-dependent state, energy is always constant, right? Expectation of H will be constant because H commutes with itself. And that happens because of the decoupling. And the decoupling is very, very crucial to make it sensible.
So this O is the damping coefficient, it just goes to zero dynamically.
So O goes to zero, that's the whole point. If there would be no decoupling, then it would have been strange, right? But the decoupling is something that is happening spontaneously. Quite the dynamics.
So I'm saying that decoupling is also unphysical.
No, that is something we see very generally. Even
For example, in the classical model, you did not have it. Right?
No, even there the O goes to zero.
in classical model, it does happen.
But it damps to zero, the energy damps.
So
Yeah.
remember our original model, we have the air and the microstate. So we had some microstate, we shocked it. And then there was went to another microstate and the air decoupled on its own. So this decoupling is a very, very general phenomenon we have seen in many, many settings, even classical, even very large classical. We have seen this. So decoupling seems to be a very generic phenomenon. This is something that, yeah, but yeah, so now we are trying to also quantize the pulse scalar and see this.
Yeah, once we quantize the bulk scalar, I'm sure everything will be kosher. I don't think there'll be.
So then you think that this state will damp out to zero?
Once we do that, I don't have much intuition. I'm not too sure what will happen. Yeah.
Actually, there are these models that Spenta and Anurag Ghoshal and Gautam Mandan have constructed. With actually, instead of SYP, they actually have real pure spin SYP coupled to something. They integrate that out. They also see decoupling in low layer models, which is purely fully quantum. In some cases, they also see exactly something. You see decoupling.
Yeah, it's a fair comment. We'll have to see once we quantize. Yeah. Right. So here the oscillator goes to some constant energy at the end. So it's clearly not in the ground state, but it's neither is it in some eigenstate. It's in a quantum trajectory which looks like this. It's the same state I wrote here. But here the psi 0 and psi 1s are the same again with some xp and pp. But the xp is, note that the equation has no O on the right hand side. So the final state is of this form where the classical equation is just decoupled, it's just a free oscillator equation. So the solution is on the right, xp is just some superposition of cos and sine with A and B. And we find that the expectation of value of x goes to 0. That's the red curve. So if you just impose that expectation value of x is 0 with the particular initial state I chose, you can solve this equation which says expectation x is 0, and you can obtain what A and B are. So this tells you what the final state is, because I know what xp is and I know what psi 0 and psi 1 is in terms of xp. That's the solution in terms of the Hermites.
It's not really a state, it's like a quantum pattern.
Yeah. It's not an eigenstate of this thing.
Something is like a superposition of the usual coherent state and some excited version.
Right. So yeah, so this was just the energetics of what happens. O, as I was saying, O all dams out to 0 as we've seen before. So this is responsible for the decoupling. So eventually both of the systems decouple, and that's why you have saturations of all of these guys at the end. Again, we can ask a similar question, but now the initial state is some quantum state. You can ask how the information about the initial state is encoded in the late time ring down, or how it's correlated with the late time ring down. Again, we look at the mass, the decay of the mass. You can subtract out the exponentially decaying part and do a Fourier transform and get the amplitude and phase. The frequency is independent of the initial state. It's some universal number. So the amplitude encodes the quantity on the x-axis, which is just expectation p squared plus expectation x squared. The phase encodes this particular ratio of x and p, which is basically just the phase difference in the initial state. That's basically just phi. Now this was just for a pure state. We can start with a mixed initial state of the qubit. So instead of the Schrodinger evolution, we can do a Liouville evolution with the Hamiltonian in the brackets, with this time-dependent Hamiltonian, with the O being time-dependent. If you do the Liouville evolution for some arbitrary mixed state, the same story goes through. The initial state, information about the initial state you can recover from the amplitude and phase. It's a similar function as I've shown you before, modulo outliers. And the decay rate, so as I said, the mass ring down has some exponentially decaying part multiplied with the oscillating part. The decay rate encodes one of the coefficients of the density matrix. So even for a mixed state, you have these 3 pieces of information, and that exactly encodes the 3 pieces of information in the initial state. Yeah, so now this was just for a qubit subspace. So this was just for a initial state in the 0, 1 subspace. You can add a ket2, ket3 and so on. This logic goes through, this evolution is true. You just have psi 0 plus psi 1 plus psi 2 and so on up to psi n, how many ever you like. But all of the information about the initial state won't be recoverable from the ring down, because the ring down has only 3 parameters. It has the exponent, amplitude and the phase. The frequency is universal. There could be subleading modes, yeah. There could be subleading modes which are numerically suppressed or something. So it's not clear what happens in those, if you include higher terms from the Fock basis here.
But that is the same comment also appears on the boundary, because in the boundary we started with the qubit, and that got encoded into a quantum trajectory, right? And
Yeah.
you can recover the initial qubit from the final quantum trajectory. But if the boundary system is also very, like you start with many superposition of many excited states, that's not guaranteed.
Yeah.
So the same comment that you made in the bulk circuit,
Mm-hmm.
that's why sufficiently small.
Yeah. That's why we chose a qubit subspace to begin.
The main point is that you have two properties of the
Yeah. So we have information encoded, like the initial state is correlated with the late time ring down of the mass. Right. So this was the story with the quantum oscillator coupled to a qubit. I'll put this together with the initial part of the talk, the first part which had this microstate model. I'll do that towards the end. But before I go there, let me tell you a little bit about what Toshali was supposed to speak tomorrow. But unfortunately, she's unwell. So let me at least tell you what more we can do using this setup. So real-time correlation functions are important for a lot of interesting stuff. You want to find out observables in out-of-equilibrium dynamics and study how these systems behave. And there are proposals to compute these out-of-equilibrium correlation functions holographically. So what Ayan, Avik and Toshali have done is extended this prescription of Liu and Glorioso and Crossley to compute out-of-time correlation functions in a particular setup. This was a recent paper. So following this horizon cap prescription, we can apply it to this setup, this same setup here, and compute correlation functions in the dual theory of some operators during this whole dynamical process. So that's something which is ongoing, but what we have found is we've managed to extract an effective temperature for this process. Now this plot is not for a black hole coupled to an oscillator, this is for a black hole coupled to a spin half. But we find an effective temperature for such a situation, and this effective temperature can be extracted from the horizon curve prescription rather simply. Toshali was supposed to give a whole talk on this, but I just managed to squeeze this in. So the effective temperature starts off at the initial temperature of the black hole before it couples to the qubit, and then it decays to the final temperature, which is what we find here. We can actually compute correlation functions 2-point or n-point from like you doing the holographic dual of the Schwinger-Keldysh. That's something in progress. Okay, then I can come to open questions and conclude and put this story of the oscillator plus black hole together with the chain model. So let me put this together. So we had described in the first part this microstate model with or without Hawking radiation, and we had a notion of classical information mirroring. The question was, how do we mirror quantum information? So before we quantized the hair or did anything more complicated, we wanted to study a simpler system, which is just one throat coupled to a quantum system, and gain some insights about how quantum systems are encoded into a JT gravity throat. How information got copied or correlated into the black hole mass. So having done that, we can now proceed to study a model like this. Let's say we have 3 sites. Each of these blobs are again the red blobs are the ADS2 throats. Let's say you couple 2 of these ADS2 throats to some qubits. The purple ones are qubits. You might choose to entangle them. You might choose to entangle the 2 magenta blobs with each other. That might lead to something interesting happening. We can include Hawking radiation as well in this setup and study how the initial state of these qubits, or how the initial state of these qubits is encoded in the Hawking radiation and or the hair, and hopefully have a quantum version of the mirroring algorithm that Hareram talked about. So this is where we are heading now, putting all of these things together. Yeah. Initial state of the qubits also. Yes. Yeah.
But there will be some observables which do mirroring and some observables which are responsible for decoding the state.
Right.
Which is the complicated part.
Yes, yeah. So this should hopefully shed some light on how that separation occurs. As we saw in the model, the phases encoded the mirroring part and the amplitudes encoded the interior somehow. So there should be some quantum observables which will encode something similar here. There's some set of forthcoming work which I can just mention. We need to try to quantize the bulk scalar and actually study how the full CPTP evolution works. I think that should get rid of most of the issues with this kind of expectation value story. We can also have bulk fermions instead of a scalar, and this might lead to insights into some strange metal models that Hareram, Ayan and others are working on. We can also do something like I showed here, couple multiple throats via entangled qubits, or have like a 2-sided black hole and couple each of the boundaries with an entangled pair, and maybe do something like a quantum teleportation protocol. These are all things that we are looking at. That concludes our talk. Thanks.
Okay, so we have time for questions. So maybe Tanay, I can ask a question. So in the second part, you had quantum matter, but black hole was classical, right? There was no Hawking effect in the. So your quasi-normal modes.
The black hole was classical. The bulk matter was also classical.
And there was
just had a quantum
qubit
thing
in
at
the boundary.
Yeah.
So how do you couple the two? Like the first part had quantum microstates coupled and classical information.
Yes.
And now you have a qubit and a classical black hole with no Hawking effect.
Yeah.
So I missed the last picture. How do you combine the two together? Or
Here? No. So in the
very final. Like
this is the cartoon thing.
Yeah.
So in the first part we had the information thrown in was some classical locations or time ordering of shocks, but now we have actual quantum information, which is initial states of these qubits.
Yes.
And then we can do a similar study of how like by quantizing the bulk scalar as well, we can study how the initial state is encoded in the bulk scalar or otherwise, or even in the Hawking radiation.
So instead of small q's, you will have like a qubit now.
Yeah, yeah, yeah. Yeah, it is still locally semi-classical, it's just ADS2, but we have some more structure at the horizon. The black hole is, yes. Yes, yes.
But there is back reaction.
It's back reacting, but it's classical. It's not quantum gravity.
Okay, any other questions? Yeah.
Just in this basic geometry, in this fragmented geometry that you computed, a two-point function, just a two-point function, a real-time two-point function.
Oh, in the fragmented case?
Yes.
No, I don't think so.
Yeah, that would be an excellent thing to
Yeah, yeah, yeah.
So that would be telling us, so what Tanay described was this, how the information is encoded into this black hole ring down. But that's physically not encoding into a state, so some kind of algebra, right? Wave-time algebra. So the question is still open, like how you decode it. For a single throat, we see this if you compute this non-equilibrium correlation functions and some fluctuation dissipation like relation, which is this effective temperature. So from there you can decode. Then the question is, more generally, how you can decode. I think we will look into exactly those kind of correlation functions, out of equilibrium correlation functions, but now between distinct throats. So that would be important to understand. So because okay, of course, after we understand this, we can also go to the Hawking radiation, but that will be even more complicated.
Yeah.
So we don't know exactly how to decode the interior, the initial state of the full system, not only these qubits, but of the full system. But for that, you exactly want to compute those kind of things that you're asking.
From the intuition that you guys probably have at this point, do you think such a two-point function will behave in an unusual way? That it decays very, very slowly?
So
Is that
here
possible?
in this example, of course, the two-point functions go from one thermal equilibrium to another thermal equilibrium. So the horizon gap we cannot do it every time, but at least now we figured out how to do this in this context where your system goes from one thermal equilibrium to another. So there you find the effective temperature actually goes from initial to final
Yeah, that's
value. And in between, of course, it encodes a fluctuation dissipation relation between the commutator and the throat. So that's what it is. So in general, we don't have an intuition like how this thing.
But this is for a single black hole coupled to qubit,
Yeah, yeah.
not for the fragmented.
This is not for the fragmented case.
There, I think it will be
You can repeat, do a similar calculation there. But we are yet to complete the actual correlation function. Yeah.
yeah, as long as it goes from, I think what if you're asking, like you start from an initial state, arbitrary initial state without horizon, and you go to a final state. We don't know actually how the horizon cap formulation can even be formulated. So in general, it's very hard to even to set up a horizon cap formulation. So we do not know how to do this actually. If you start from a very complicated initial state. But the good thing about, at least in a simplified picture, is that all these black holes have some kind of fixed mass. So in that case, we can answer this question because that is kind of a microstate model, that you have this fixed constant state.
Okay, any other questions?
Do you have any thoughts about deriving your model from some top-down string theory considerations?
Deriving it from something that seems rather hard. I don't have anything in iron.
There was this talk by strings which so it seems like when you have some Parseval pictures in the brain kind of setup, there are these NS5 brains and D5 brains. When they intersect, they open up areas to theories. But that's precisely when the perturbative string theory is very hard. So there is, I don't know whether we can derive it. It's simply a guess at this moment.
Yeah.
But on the defensive side is that at least it's a guess that you can actually simulate in the laboratory. So at least you can, because you can think of like mirroring this with a spectacle. So that was the motivation also for looking for this. So that's the next best thing you can do. If you cannot derive it, try to do it in a way that you can check in the laboratory.
But with the microstate geometers, you do not have an APS, so you haven't got APS to it. So it looks like PKS2, but it's not. So
goals of QoS at the same time. So that way you can also produce that. So this is what we were thinking of also of doing, but it becomes, I mean, it's become very difficult to study. Like it's not impossible to study, it becomes more complex. So those you also have in mind, but probably that will capture most of what.
Okay, any other questions? If not, then let's thank Tanay and Hareram. So I resume when? 32. We have a poster session, so there will be a lot of interesting posters, and we will have a pizza and a lot of Indian snacks like kathi rolls and all, or some other stuff. Uh, so I invite you to the poster session from 6 to 7, and just in the same place. And the others, which I'll make a more detailed announcement later. There will be an excursion for the half day tomorrow, and there will be 3 options for you. You don't have to pay anything for the car, but I will have some suggestions for restaurants. So you have to book it yourself. Like if you put a group, you can, as a group, you can book it. You have to reserve. I think better to reserve and go. So I'll have some suggestions for restaurants also along this trip. So there'll be 3 options tomorrow, and so you can choose one of them. So more details on that later. Okay.
Can anyone hear me? Oh, yes. So thank you very much for the invitation to be here and to speak here. I'm really delighted to be in India again, and for the first time scientifically in Chennai. And thank you very much to the organizers for the wonderful conference and for the great hospitality. So this is work in collaboration with my postdoc, with my graduate student, Bowen Chen, who is still out on the postdoc market, so maybe you should hire him, as well as these other people. And so the talk is about, like this whole conference has holography in the title, so it's about holographic duality. This slide just gets us all on the same page. It's a duality between a conformal field theory in one fewer dimension and an anti-de Sitter space, a theory with gravity with such boundary conditions in one higher dimension. So it's interesting that there is an additional direction which is not present in the CFT, which emerges in some way. Basically, it emerges from different scales in the CFT. But we would like to understand how the various geometric concepts that exist in ADS, what their origin is in CFT terms. And answers tend to typically involve information theoretic quantities on the CFT side. And so we will be looking for an answer to one such question, which is kind of basic in general relativity, which is what it means to transform, to parallel transport some object, such as Foucault's pendulum, maybe, along a given curve in this geometric background, which is produced by holographic theory. So the first ingredient that I'll be using is subregion duality. So that's a statement that not only does the CFT on the boundary reproduce the bulk spacetime or give you equivalent information to learn all about the spacetime, but if you limit your knowledge to some spatial subregion of the CFT, then in fact you can reconstruct something about some specialized, we can reconstruct all perturbative physics in a subregion of the ADS, of the emergence of the bulk ADS geometry. So it's not an all-to-all duality, it's a subregion to subregion duality as well. And the relevant object is an entanglement wedge. it's probably important to say here that an entanglement wedge is something which is dual to a, well, first of all, physics in an entanglement wedge, so the subregion of the bulk geometry is reconstructible from from a reduced density operator in the CFT. That's the proper object that encodes the partial information in the spatial region. And that thing is really a property not just of a spatial region, but a whole causal diamond in the CFT. Because if I change this region A to some other, to a region drawn differently, but which begins and ends in the same corners of the same diamond, then I haven't really changed the information. I just presented it in a different basis given by the time evolution from the one, from the A drawing to some other drawing here. And so I've reduced density matrix in the CFT and the entanglement wedge in ADS are really properties of whole causal diamonds in the CFT. So I'm guessing most people in this room have seen this 100 times, so let me skip ahead. The next thing we will need is modular Hamiltonians. And so I said that there is a subregion of ADS, which is dual to a subregion in the CFT, to a reduced density matrix in the CFT. Now we define an object called the modular Hamiltonian, which is minus the logarithm of this reduced density matrix. So that's some imaginary Hamiltonian that we concoct in order to say that the reduced density operator is thermal with respect to that Hamiltonian. And those Hamiltonians, the modular Hamiltonian defined this way, that's a CFT object which has a profound significance in the information theoretic inquiry into the CFT. But it also has a specific interpretation in the bulk ADS space, which is that it generates boosts that are orthogonal to the surface where the entanglement wedge ends. And this is called the RT surface, or Ryuta-Kayanagi surface. That's the deepest surface in the bulk that is drawn in this picture. And so the modular Hamiltonian generates boosts orthogonal to that surface if I'm close enough to the surface. So far away from that, it doesn't have that interpretation and becomes non-local, but close enough to the surface, that is its geometric action. So I'll be using that fact a lot in the rest of the talk. So the first thing that is perhaps less standard than what I've said so far, which will be important in this talk, is the concept of modular parallel transport, which is something that my collaborators and I formulated 3.5 years ago now, which is we look at a single subregion in the CFT, which has its own entanglement wedge and its own modular Hamiltonian. And then we look at another one, which is infinitesimally separated from it. So going from here to here is just drawing two copies of an entanglement wedge for two different causal diamonds in the CFT. Yes, and so each of these has its own, like I said, entanglement wedge. It has its own modular Hamiltonian, and modular parallel transport gives us a canonical mapping geometrically in the bulk. It gives us a canonical mapping from a neighborhood of one of these RT surfaces to the other RT surface, or in more CFT terms, it gives us a canonical way to map one modular Hamiltonian to another modular Hamiltonian by conjugation. If you imagine that I consider not one and another, so not two, but a whole sequence of regions in the CFT, each with a modular Hamiltonian, then that really gives me, well, a sequence of modular Hamiltonians like that. Nothing stops me from calling it a time-dependent set of Hamiltonians. They are modular Hamiltonians or entanglement Hamiltonians in this case. And many of you will have studied the problem of constructing Berry phases, which is something that we associate with a time-dependent Hamiltonian. So in this case, a setup where we have a family of regions in the CFT, each with a modular Hamiltonian of its own, also allows us to define a Berry phase. Now we would call it a modular Berry phase because it's associated not to the dynamical, but to a modular Hamiltonian. Yeah. Sorry, what's that? Yeah, it was. I didn't say it, but I even, that was the, they are referenced on the previous slide. So, so yes, yeah, that's. So what we need JLMS for the upper statement here. So it seems like the I can't really point the pointer here, but we need the JLMS for the upper statement. We need to turn this object, which is a purely CFT like operator statement, into a geometric statement there, and that's where JLMS matters. Okay, so so this picture is obviously really busy. So I would like to simplify it in all future diagrams, at least for the next several slides. So let's just limit to a scenario where all of these regions, which I will vary, and I will consider a bunch of modular Hamiltonians. Imagine that all of those regions are drawn from a single spatial slice of the CFT. And I will also imagine that the bulk geometry is static. So I have a well-defined static time slice through the bulk. So I don't have to worry about time dependence. I can just study this problem at equal time, which is what I draw here, this equal time slice. So from now on, my drawings are going to be happening on this equal time slice. And here is, here are 3 pictures of an equal time slice. I have 2 regions in each case, the red region and the orange region, that corresponds to these orange and red regions on the boundary from the previous slide. And modular parallel transport is supposed to give me a canonical mapping from a neighborhood of one RT surface to another. So here I have 3 different such mappings from a neighborhood of an RT surface to another. And so these sets of arrows tell you where each point on the RT surface would map to another point on an RT surface. So as a CFT statement, each of these mappings is generated by an operator valued 1 form. I call it a 1 form with a little d lambda because I imagine that the regions are separated infinitesimally. So it makes sense to talk about differentials in this context. So it's generated by an operator valued form d lambda, which satisfies this equation. So basically, I'm looking for some object that if I used it as if it was a Hamiltonian, and so don't think about this Hamiltonian as a Hamiltonian. Think about it as your favorite operator, forgetting that it's a Hamiltonian. Now, what is a Hamiltonian that you would have to have such that the Heisenberg map of this Hamiltonian would give you this appropriate variation of this operator? So we're looking for a Hamiltonian that gives us an appropriate Heisenberg picture variation of the modular Hamiltonian. I will not be calling this object V a Hamiltonian anymore. So these were just words to explain the equation, but let me quickly erase those words. We're just looking for some V d lambda, which gives me a connection which satisfies this equation. So that's an operator valued 1 form, and that's why I called it a connection. And yeah. Oh well, so these are differentials. So there's the reason why I have a differential form here is that this dh is an operator valued differential form. I could call it dh d lambda times d lambda, right? The left hand side is a 1 form because of this. Oh no, it's not. No, it's well. This thing is supposed to generate holonomies. So one thing which I will not primarily talk about in this talk, but one thing that one can study is the holonomies of this modular parallel transport. Those holonomies are there because this V d lambda is not an exact form. Yeah. Yeah, so that thing prevents it from being a 1 form, which is important actually.
So can I turn it around and say, so you're saying that any such V d lambda, if such exists, such that it can be related in this way, that can be understood as some interpretation. I mean, so whether you start from the right hand side or from the, or you can also
Well, so right now I'm trying to describe what modular.
Something similar. Why the left-hand side is big closed? Because it has to be from the right-hand side. You're imposing something stronger. It's exact up to zero. Why is it closed? Why is it closed?
Oh, I've never encountered this question, and let me see why you say this. So well, let me even see what the question means. So so you say that if I just ignore zero modes, so if I work modular zero modes, then the right hand side is yeah, you get a yeah. So I think that so in this problem, the modding out by the zero modes is the sole reason why we have a why this this VD lambda produces non-trivial holonomies, and the holonomies are precisely valued in the zero modes. So so in other words, if you want to detect that the left-hand side is not exact, you would compute a holonomy of this VD lambda, like do a path-ordered exponential of VD lambda. You would find that that thing is valued precisely in the zero modes. So if you ignore zero modes, then you will get zero, and you would conclude that it's exact in the space of where you modded out zero modes. So as every transport problem, there is an underlying bundle. That in this case, the fibers of that bundle are precisely the zero modes that we are modding out by. So the abstraction for this thing to being exact is precisely valued in these things that you are dropping. Am I answering the question? So that's kind of so at the geometric level, this is obvious from the geometric statement. And so actually let me just put down the next part of the thing. So what are the zero modes? Zero modes are things that commute with the modular Hamiltonian. So that means that these are operators that if I conjugate by them the modular Hamiltonian, I still get the same modular Hamiltonian. This modular Hamiltonian has a property that it fixes the RT surface. So in particular, a conclusion, it's an if, but not an only if statement. But one conclusion of the fact that I have this is that they must preserve the RT surface themselves. So the only thing that they can do is as geometrically, is to generate diffeomorphisms that map the RT surface to itself. Okay, so now imagine that you did some kind of closed integral of this VD lambda connection. At each step you are, what this means is that you have a family of RT surfaces, and at each step you're mapping that RT surface to the next one, and to the next one, and to the next one. If it's a closed loop, then eventually you have mapped your RT surface back to itself. But it doesn't mean that you have generated the identity. You could have generated an overall shift or some kind of, anyway, you could have generated a non-trivial diffeomorphism of the RT surface onto itself. But what's that? That's exactly a zero mode. So this is a geometric argument for why this transport problem has holonomies that are valued in this space. Did I answer your questions? For Ayan and Kostis, both of you? So these arrows make sense in the neighborhood of the RT surface. So here we're looking at only statements that are geometric in the neighborhood of the RT surface. And so it's true that to talk about this problem properly, we have to select the piece of the problem which has a geometric action from the piece which is non-geometric and acts far away from the RT surface. There is I don't have slides on this, but at this point it's well understood how to do it. The first statement is that the geometric things are generated by what's called the modular scrambling modes. These are things that have a particular commutation relation with the modular Hamiltonian. And then under some more general settings, you can read a very recent paper by Lampros Lampro and Jan de Boer and Daniel Jafferis from just before Christmas, from like 2 weeks ago, where they explain, where they study this problem in a lot of detail. So I don't have slides on it, but that problem is under control. So when I draw arrows and talk about geometric interpretation of these objects, I always mean it in the neighborhood of the RT surface, and that means that I have separated the problem into a geometric component and a non-geometric component, and I'm skipping the part about how that separation is done, but the references I just told you tell you how to do it. This is a commutator of operators in the CFT. I will have some equations later for pure ADS. Pure ADS is a little cheating because everything follows from conformal symmetry. The problem is that there are not many examples where we know modular Hamiltonians exactly, so it's hard to do explicit computations with any specific modular Hamiltonian, except in cases where it's fixed by symmetry. So that's why my example is pure ADS. So we can talk about what happens in more robust circumstances after the talk, probably not online during the presentation. Yeah, this equation wouldn't change very much because, I mean, their commutation relations are the same. So H mods, zero modes are the same as rho zero modes, and yeah. Huh? If we're in the ADS free context, then yes. Well, is there a yeah. Oh, well, so lambda is just some parameter we invent to parameterize a family of regions. Now, we don't have to be in the vacuum for these equations to hold, I claim. So in the vacuum, it's easy to write down what this transformation has to do, because the modular Hamiltonians are fixed by conformal symmetry. But there is nothing sacrosanct about the vacuum in the sense that, I mean, we can't compute it explicitly, but there exist these modular at least the two-sided modular Hamiltonians always exist. So nothing stops you from taking a derivative, a differential of this type, and solving this equation. And there will be some family of VD lambda solutions. And the statement is that each of those families, they will do some non-local mass far away from the RT surfaces, but close enough to the RT surfaces, they will allow me to define some kind of arrows like this. Far away, they're doing something else, and no one wants to make any statement about that. But near the RT surfaces, they're making, they're doing geometric mappings of this type. It's an operator that has a specific. It's an operator in the CFT which has a specific action on these reduced density on these specific reduced density matrices. So if you give me a different global state, then the set of density matrices will be different, and so then the V will be different. So V is a property of the state. Yeah. Oh, thank you. Okay. So here I drew 3 examples of these V's. But we want to, which is what I say here. But we want to select one because we want to find that we're defining some kind of transport problem. I mentioned this. It's not on the slides, but I mentioned it in response to Kostis's question that we have an underlying bundle where the fibers are zero modes, and as on any fiber bundle, parallel transport is a map from one fiber to another, where you know if you start at one point in the fiber, you know where to go in the other fiber. So we need to, these fibers correspond to the ambiguity between how to draw these arrows, at least close enough to the RT surface. So solving a transport problem or defining a connection on this bundle means choosing a particular set of arrows out of these options. And so this is the choice we make. We want this VD lambda, which itself is zero mode free. So being zero mode free means that I am doing no transformation, which by itself is an RT preserving diffeomorphism. And it also is not supposed to be doing boosts orthogonal to the RT surface. That's also an RT preserving operation. So we want a VD lambda which doesn't have any of that. And imposing this condition, I just want to say to explain, maybe it sounds random. So just to give you a sense that this is not a random thing, it's exactly equivalent to this condition that you might want to impose if you're studying the Berry phase problem. So setting this condition is equivalent to defining parallel transport in the case of Berry phases. Okay, so we make this choice, and that choice corresponds to, of these three options, graphically it corresponds to this set of arrows. You can understand this because there is a point here where the two geodesics intersect, and at that point the arrows have no reason to go anywhere, because if they did, they would be going sideways along the RT surface, but that would be a zero mode. So being zero mode free means that in the neighborhood of this point, we want to be precisely doing a rotation about that bulk point. And so this statement gives us a handle on some kind of bulk locality when I have two RT surfaces that are intersecting one another. And this is our starting point for tackling the problem of parallel transport in the bulk. So that's how I will get started on trying to describe parallel transport in the bulk. Are there any more questions about this point? So what is bulk parallel transport now? So let's take stock of what we have. Yeah. 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 Well, I'm just saying that if I will want to study the problem. What operators generate bulk parallel transport from a point to a point? To even get started talking about it, I have to have some way of specifying which points I'm talking about. Yes, and I'm saying this is my handle about it. It's the point which is fixed by the a point in the bulk will be a point which is fixed by modular parallel transport between two geodesics that happen to intersect at that point.
So if I are not zero mode free, then
Yeah.
it could freely change under the each one's
Yeah, if it was so this is the zero mode free answer. So what would happen if I added some zero mode? I would start shifting this thing. So necessarily I wouldn't have a rotation but a glide along this surface. Or in the orthogonal directions that I'm suppressing, you would have some extra boost. Okay. So let's take stock of what we have for bulk parallel transport. We have a notion of parallel transport for whole surfaces. So I just want to be clear that we have defined the notion of parallel transport not for points, but for whole surfaces. And what we would like to now construct is the actual bulk parallel transport along curves. So this is like what we have studied in GR classes. And if anyone needs motivation about it, let me just say that the Riemann tensor is really a commutator of such parallel transport generators when you write it in this form for coordinate vector fields. And so if you in case anybody in this room was not certain that it's a question with strong motivation to study what bulk parallel transport is, then maybe this equation will convince you. So let's try to do it. And because I felt like giving a, I thought it would be nice and refreshing to make it a challenging environment for everybody. So here's a test. So here's the simplest setting. I'm on an equal time slice of pure ADS3, and I'm studying the simplest possible curve along which I want to do parallel transport, which is a z equals constant slice in these standard Poincaré coordinates. So my question is, what operator generates ddx in this context? So what does it mean to do bulk parallel transport along this in this direction from the CFT point of view? And so first try, is it this operator? Everybody has learned that ddx, or maybe minus ddx, depending on your conventions, is something that is doing x translations, right? So is this the answer, or is it not the answer? Shall we make a vote? Who thinks that this is the correct answer? Who thinks it is not the correct answer? Okay, who thinks neither of those things? All right, so I guess, so anyway, so I guess the answer is, so for the vote, I've given away the answer because I wrote first try. Clearly it tells you that there was going to be a second try. So, so that is not the answer, but let's try to understand why it's not the answer. So suppose that I made the x direction compact, which I could, and I just followed this, I just did my bulk parallel transport all the way coming back to where I started. If this was the answer, L minus 1, then I would compute the path ordered exponential. I don't need to path order it anymore. It would just be the exponential of L minus 1 times some number, which is the circumference of my compact x direction. So I would just get a transformation, which is translate all the way around the compactified circle and come back where you started from. The holonomy of that would be trivial. But that's not what is supposed to happen here, because we all know that these slices have some non-zero extrinsic curvature. And if I follow a curve which has non-zero extrinsic curvature, surely I'm going to generate some transformation. We know this transformation as the Foucault pendulum effect, because that's the experiment we do when we look at Foucault's pendulum, right? And so that clearly is not the right answer. Is that clear for everyone? Okay, so what is the correct answer? So I wrote it for you, and this is the form that it takes. And so I don't expect you to just look at it and say, wow, of course I knew that. But the problem that we're trying to solve here is to find a principled route to this holographic answer. I underlined holographic here because I want this to be the answer to be given in boundary terms as boundary operators. And I say asymptotically ADS-free geometries. The word asymptotically is supposed to tell me that the answer I give you is not supposed to work just in pure ADS, but in any geometry that could arrive in ADS-free CFT2 correspondence. Any questions about the problem I've posed? No questions. So before I leave this slide, well, when I say because L0 is x ddx in some, I mean, when I choose how I label L0, L1, and L minus 1 in terms of diffeomorphisms, I'm choosing an x equals 0 point, because L0 fixes one finite point. So that's why the x has to be there. But I'm not breaking it. The choice of what I call L0 breaks that. Yeah. Any questions? Or so you can check that if I do what do I have to do? If I map an L0, L1, L minus 1 basis to another one by conjugation by a simple shift, this answer will transform to itself appropriately with axis scaled. I mean, with axis shifted like they should be. But I mean, yeah, yeah. Right. All right. So let's study it. Well, the vector is so if I have a coordinate vector. No, so here I'm trying to say what is ddx in the bulk. In other words, if I carry a test arrow here, then how do I know that this arrow is going to process in some way as I carry it using parallel transport in the bulk? Is there some operator that I could apply to tell me how a test object that I'm carrying here would transform? And if I Well, that was the argument about the trivial holonomies. If it was this L minus 1, then I would compute a holonomy around the closed x direction, and I would find that the holonomy is trivial. But if I carried a little Foucault's pendulum here and I traveled around, it would change its direction. So it would have a non-trivial holonomy. So that can't be the answer. Huh? Sorry, this one? I mean, I computed it before doing the slides, so that is the answer. Well, that's what the talk is about. I'm trying to tell you. Okay, this slide, let me explain what the purpose of this slide is. The purpose of this slide is to say this problem is not trivial. Because if the problem was trivial, then this would be the answer, but it isn't. Okay, so. I am asking a holography question. I want to. Yeah. So you teach it good. You teach it in the GR, and now, but you know that L plus 1, L0, and L minus 1 act as isometries in ADS. So do you know how to find an appropriate combination of L0, L1, and L minus 1, which would coincide with the action of the parallel propagator along this curve in the bulk? And the answer is it's this one. Yeah. Well, mostly what I said is that the modular parallel transport is supposed to, I'm supposed to find the part which is zero mode free. This part that I'm ignoring the zero modes is just a statement that I can never derive a zero mode from a commutator with H mod. So this one is kind of mandated by the left-hand side being a commutator. This part is really the non-trivial part. That's the one that selects this as opposed to this or that option. Yeah. Yeah. So I have so in my next slide is taxonomy of transport. I want to separate various types of transport. So far I gave you my toolkit, and I'm going to tell you how to solve it. This slide is about what the problem actually is, and then we'll be solving it next. So the previous transport problem is not the answer to this question, but it is a stepping stone towards the answer. But before I get there, so there is something else that is useful on this slide, which is this map. So whatever it is that we're doing when we're doing parallel transport, notice that we have seen something similar on these previous slides, which is this kind of sliding motion. That sliding motion for RT surfaces which are just tangent to my curve, they are not modular parallel transport. They're not even the bulk parallel transport, but it is this trivial answer that most of us would have given if we hadn't thought about it. And so at least we have some candle on this problem. In addition to modular parallel transport, we have one more tool. One more tool is that we have some intuition about this answer, and what this answer is doing is just rigidly sliding those geodesics alongside like those arrows are doing. So we're going to use those two facts together to arrive at what bulk parallel transport should be. Both modular parallel transport, which is not this, and this matching is what we will use. And those things are collected together on the next slide, which is the taxonomy of transport. So we're going to have three things here. The first one is the naive answer, which is what I wrote for you here. And that just does this. Let's give it a name. I'm going to call it sliding without rolling. If you imagine that you had some object, like a box, then you would just be pushing that box. There would be no rolling going on. Yes? That's what this thing is doing. If you see what I mean, like, here's a test arrow with some test vector. That vector would just slide along like this if I did this. Here's a second object, which is modular parallel transport. So modular parallel transport, we already know what it does. We discussed it. It has this form in the neighborhood of RT surfaces. I'm going to call it, it is an intersection about, it is a rotation about intersection points. And for this reason, we can call it rolling without slipping. If you imagine that these geodesics were wheels, then you would just be literally rolling this wheel down that line is what they're doing. And then we have the third thing, which is the thing we're looking for. And if you see what the holonomy of that thing wants to be, like the extrinsic curvature of this curve wants to turn any initial vector that I have like this to slide more this way. That's the action of bulk parallel transport if you compute it. And so the question is, what is it? But our tool for answering this question is going to be these two things. Yeah. No. So the answer that I gave before was an explicit answer, but this thing will turn out to involve some modular Hamiltonians of these tangent entanglement wedges. So you will arrive at this answer by doing some transformation on modular Hamiltonians, and that's why this answer will end up being an information theoretic answer at its core. That's the explicit form, but it's reflecting some properties of modular Hamiltonians of these tangent entanglement wedges. Huh? Huh? You wouldn't do it. If you chose it, then you would be describing a different curve. So, sure. I imagine that I have some. So, how do we relate the curve to the boundary? I'm going to relate it by choosing entanglement wedges which are just tangent to the curve. Yeah, that's the way in which those two languages talk to each other. Otherwise, how am I specifying the curve? If the curve is differentiable, then I don't have any choices. There's only one set of tangent RT surfaces that there is in fact some set of choices that are given by something called the null vector alignment condition. Please allow me to skip that complication. There's obviously not enough time to talk about that, but we can talk about what extra freedom I have here relative to what I drew for you. But at the level of what's here, there's no freedom. It's just this. So, shall I? All right. So we need some to talk geometrically about this problem. We need some nomenclature. So whatever generates this, we have previously called VD lambda, the operator valued one form that does this. Whatever does this, I'm going to call it ZD lambda, or because I'm in India, I'm going to call it ZD lambda, and this one I'm going to call AD lambda. And the interesting thing to notice is that AD lambda is actually the sum of these two one forms. So think about it. If you want to slide without rolling along a curve, then but your curve has extrinsic curvature, what you can do is always follow the tangent line infinitesimally. That's your bulk parallel transport. But then at some point you have to turn. If you keep going, you're going to lose your curve, yes? You turn by what amount? You turn precisely by this amount, which is the angle between neighboring tangent geodesics, also known as the extrinsic curvature one form. And that's done by modular parallel transport. So if you combine the motion of following the curve and doing modular parallel transport, following your tangent and then doing modular parallel transport, you will actually end up sliding without rolling. Can you see that? And so our handle on this problem is that we have some understanding of, first of all, we fully understand this, that's modular parallel transport. We also have some understanding of that, at least at the level of the L-1 problem for this, everyone would be able to give this answer. So we know this, and we sort of know that. That's how we're going to know that. This is the plan. Yeah. That one was random and useless for these purposes. Okay. So yes, so this is the summary of what we have: sliding without rolling, modular parallel transport, and bulk parallel transport. Here I remind you of the equation for modular parallel transport, which is this equation. Well, it turns out that this one is selected by an equation which has exactly the same form as this, except the role of H mod is given by V. And now I'm looking for this other object. So, well, there's an extra minus sign, which is sort of convention dependent. So you can, so why is that true? And for some of you, maybe you will say, oh, if it worked like this for this problem, it probably should work the same for that problem. But I imagine that that's not a good answer for many of you, only for some. So here is an explanation. The explanation is that suppose that I wanted to find so how would I find this z d lambda in this problem? One thing you can say is that z d lambda is the form that allows me to continue going along this formula, using this formula, to continue going doing sliding without rolling. So that means that I do a rotation performed by this, then I do z, and then I do another rotation. That in turn means that z is the form that relates two different centers of rotation. If I conjugated one center of rotation by the integral of z, and then if that z is properly chosen, then it should be true that it should commute with the other center of with the rotation at the other point. And so you see z should be chosen in such a way that one rotation center and another rotation center, these are 2 points on the curve, that those two rotations, they come to commute if I conjugate one of them by the integral of z. So that's the kind of the equation that you would want to write down to find z, to maintain sliding without rolling. Yeah, I'm just literally saying that in this thing. And so this equation is actually the first order truncation in little d lambdas of that equation. And so that's where it comes from. This is an explanation for how we got there. And so this finds for us the form z d lambda, which shifts the centers of rotation for modular parallel transport, and that shift is exactly the bulk parallel transport that we wanted to find. So here's a summary of what we have said so far. This basically gives the answer to the problem I set out to solve. First, if you give me a given curve, I'm going to find tangent RT surfaces. So that goes back to an earlier question. Like that's how we relate a curve to boundary data, through tangent geodesics to the curve. Then we solve this equation, and then we still have an ambiguity in how to choose z d lambda by terms that commute with v. So we want the z d lambda to be precisely valued in 0 modes of h mod. This is the solution now. So remember that for the modular parallel transport here, we had an ambiguity in v, and we fixed it by saying that v is 0 mode free. Now we're choosing this by saying that z is actually entirely composed of h mod 0 modes. And why is that? Uh-huh.
So here you get still some kind of a freedom, and you're fixing it in. Is there
Sorry, are you?
Equivalent of this freedom? Like you do in the Debajyoti.
Sorry, are you asking me what if I chose a connection which is not metric compatible? Is that the question? In the bulk? Yeah, okay. So I am just doing the metric this is for the Levi-Civita connection, and that.
But a priori, is this seems to be coming out like a magic? You choose these this way, if the ambiguity is this way, you get the Debajyoti.
The Levi-Civita choice is the thing that tells me that so it came from the fact that modular parallel transport is a rotation about a point, okay? But I said that was enough to maintain the notion of parallel transport. So I could, if I just remember to turn with my curve by the amount given by its extrinsic curvature. If I chose a different connection from the Levi-Civita connection, then, roughly speaking, you can think of it as a choice of spin connection. That would be like saying, I'm going to do what the Levi-Civita connection does for me, but I want to make additional turns as I'm doing parallel transport. Those additional turns would be related also to modular parallel transport, but you would just multiply it with some different coefficient here. So roughly speaking, if you wanted a different connection, you would have to say, set the coefficient of v to be different here. but that's yeah. So the choice of the Levi-Civita connection is a choice that is related to this because we are using metric compatibility by basically by saying that the connection is related to modular parallel transport. I don't have a better answer to this question. But anyway, if you have a different connection in mind, you can change this. You can change this prescription and get a different answer. There is not a problem. In some sense, sliding without rolling is a choice. This is a choice of connection which generates free holonomies. You can do that one, and that's the answer. So yeah, actually that's a good answer to your question. So if I do bulk parallel transport with the Levi-Civita connection, this is the one that does the job. Here is a different connection. Take a connection which happens to have trivial holonomies along my particular curve. Well, that's this one. So what's the difference between them? I added VD lambda. If you made any other choice, you would add different multiples of VD lambda to get that connection instead. The bulk connection with the bulk parallel transport for Levi-Civita happens to set the coefficient of this V to 0. Okay. So let me just explain why the answer has to be valued in 0 modes of H mod. And the answer is that locally at the surface, we have to be following the tangent locally at the curve, we have to be following tangents to the curve if we're doing bulk parallel transport. But that means sliding along an RT surface, and that's a 0 mode. So the ZD lambda has to be a 0 mode, otherwise this construction wouldn't make sense. So that's why we're choosing that option to fix the ambiguity in Z here. Okay, so I have 10 more minutes, and I guess I can sketch what happens when I'm not on an equal time slice, because so far I've assumed that I am on an equal time slice. So yeah. Yeah, right. That's right. But now we wanted to have a commutator with V. Yeah. Yeah. So okay. So now let's what happens when I'm off a static slice. So far we have covered a situation which is like this. But now imagine that I want to do parallel transport along some random curve like this. So I'm going to also choose tangent geodesics to it, like here. Each of them, think of this as an RT surface for some region. So here are the regions. Each of them has a causal diamond. So here are the causal diamonds. And at this point, the picture got really busy. So let me erase all of those causal diamonds except one. So that's what I have here. And the statement, how are we going to go about it? So for a curve that doesn't live on an equal time slice, there is a new ingredient, which is that the curve doesn't just have extrinsic curvature, it also has torsion. And torsion means that even if it lives on some plane for a while, it can jump off the plane, and the precession of that plane is what torsion is about. So I'm going to draw two local planes like this one, which is this one. They're called osculating planes in textbooks. And those osculating planes are going to have some angle between them. Because we're in 2+1 bulk dimensions, this angle is not an ordinary angle, but a hyperbolic angle. And this hyperbolic angle happens to be generated by H mod, because H mod generates boosts orthogonal to the RT surface. And those two osculating planes, one thing that they have in common is that they both have to contain this orange geodesic. That doesn't really come out on this picture, but it's a fact. So the fact that they both have to contain the orange geodesic, the middle geodesic in this picture, means that the two osculating planes, the angle between them is actually a hyperbolic angle, which is precisely generated by the H mod for this middle orange region. So that gives me, so here's a picture of what I just described, but in a more idealized settings. I have these three little regions, three little geodesic segments. Each pair finds for me one osculating plane, and we're looking for an angle between them, but that angle between them is going to be generated by that H mod. And so it turns out that this ZD lambda, which we found on previous slides, in this context isn't bulk parallel transport, but it's bulk parallel transport plus the torsion. And so if I want to bulk parallel transport, I have to remove by hand the piece which is proportional to H. And this is easy to do. And so this is what we do to find bulk parallel transport when we're off an equal time slice. Are there any questions about that? So I'm not writing equations for it, but this is the machinery by which we would find it. The next question is, what happens when I consider not a curve like this, but a curve like this, which goes vertically, and that means time. And so this doesn't select any modular Hamiltonians at all. Yes? But, or does it? So imagine that there is a particle which is traveling along this RT surface, and think of this particle as having a mass, and think of this mass as sourcing a little Schwarzschild solution, or let's say a BTZ solution if we're in ADS free. And so now we would say that the CFT, there is an issue of whether this mass is really small or large, because we would like this black hole to be thermodynamically stable. So I said small, but let me take it back. Imagine that this is actually a heavy particle, so it produces a large thermodynamically stable black hole in ADS. Then there is, in fact, a modular Hamiltonian which is related to this state, which is the dynamical Hamiltonian for the whole theory. And so this way of thinking about time-like curves, where I promote a massive particle moving along a time-like curve to a massive black hole, and then I take the dynamical Hamiltonian to be a relevant modular Hamiltonian and try to derive bulk time from that, was championed in this paper by Daniel Jafferis and Lampros Lamprou, and this is where I stole this picture from. This picture is supposed to be the same as this picture here. And so this is the innovation of that paper. Treat a particle moving along a world line as a black hole. The modular Hamiltonian is a dynamical Hamiltonian. If I have some non-trivial background, then I would take the ordinary Hamiltonian for the CFT and just conjugate it by an operator that creates the background. This is what would create a black hole in some non-trivial background. Well, so I have to imagine for what subsystem. So the whole CFT is now in a thermal state. So the dynamical Hamiltonian becomes the modular Hamiltonian. Then the distinction goes away anymore. Yeah. So so what they said in that paper is, if you want to study the transport along time-like curves, who is doing the transport? It's some particle, and if it's moving in a time-like direction, then it has some positive but not zero mass. Then treat that mass seriously and imagine that this particle is sourcing some Schwarzschild solution, ignoring issues of thermodynamic stability, because if I took this seriously, then it would lead me to very small black holes. But if ignoring that issue, it just means we have to replace the particle with a black hole, and that's what I'm saying here. And so this is in principle a way of extending the analysis from previous slides to transport along time-like curves. And there is a conceptual problem here, which is, can we really construct the space of such modular Hamiltonians in boundary terms? Because it's easy to say, oh, here's a Hamiltonian that generates, which is appropriate for a black hole in an otherwise empty space. But for moving along a time-like geodesic in some complicated non-static geometry with various stars and objects and back reaction, well, I would really have to know the bulk to talk about to know how to conjugate this Hamiltonian to generate the Hamiltonian relevant to that setup. And the question is, are we still doing boundary, or are we actually doing bulk physics at this point? So that's a conceptual problem for this, which in the paper we discuss other problems, but this is the biggest conceptual challenge for extending the analysis to time-like transport. And here I have a slide about how this thing gives me a handle on the Vielbein and the spin connection in ADS. So we mentioned this naive answer, which was sliding without rolling, which gave me this connection. And I said that one way to tell that this is not bulk parallel transport is that it has trivial holonomies. So this is a flat connection. Or I defined it for this specific curve, but it can be extended to a flat connection everywhere. So if you give me a specific bulk curve, I can also traverse it backwards, so not in this direction, but in that direction. And that gives me a different flat connection, which is not just minus that one. In fact, one of these components gets an extra minus sign, but the other one doesn't. If I think about the connection which does sliding without rolling in one direction versus in the other direction. So does this resemble anything for you? When I have an A, which is a rotational thing plus a translational thing, and an A bar, which is a rotational thing minus a translational thing. Does it look like something? And so this is actually analogous to the Chern-Simons connections in pure ADS gravity. And these equations are just like these equations. And so if you work at it, then you can get a kind of a boundary representation of what the Vielbein and the spin connection are by taking even and odd combinations of these connections. And so that's all I had to say. There is some list of future directions for anyone who is interested in extending this story. Thank you very much. Yeah. You mean in higher dimensions?
Yeah, no, I mean your point 3 about the Japanese construction. Why was that case not a special case of the previous example that you?
Yeah, so that's explained in this slide. So here, when I have a space-like curve, I can always extend any tangent to it, and that tangent reaches the boundary. And that where it reaches the boundary selects for you a region. And now I say, oh, I have a modular Hamiltonian for that region. Here I can't extend this in any way because it doesn't go to the boundary.
But in that case also, I could have just looked at like a sequence of RT surfaces which are only moving in time, right? Is that not?
But they wouldn't be tangent, right? To this curve. They would just be intersecting that curve.
Like the turning point, the tangent to that will be like, I mean, I'm just saying that you just look at the slides which are not getting deformed.
The fact that these would not be tangent makes it a completely different problem. And so that's...
I'm saying this is like a world line of that family of surfaces.
Which one? This one?
Yeah, like if I just look at RT surfaces, like one parameter family in time.
No. If I take a family in time, then what I would do is this, and this would generate, in pure ADS3, it would generate an ADS2 subspace of ADS3. It wouldn't generate a curve. Oh, yeah, I don't have anything to say about it, but let me just make a declaration. I'm very interested in this subject.
Yeah, maybe I have a question. Since you translated everything in terms of CFD language, can you just, if you implement this with CFD, did you get something that makes sense?
Well, so I mean, let me just say that this is the answer for this equal time slice in pure ADS, and and you can write down an answer which is more complicated, but it's still there for an arbitrary curve that does anything you want in the.
But example where it doesn't have the geometric bulk.
Without the geometric bulk.
But you already.
Oh yeah. Oh yeah. So I have a. Yeah. So actually, it doesn't. The truth is that it doesn't make sense away from the. So let me see which slide is best. So I told you that there was one thing that I'm not telling you about, and that thing is actually crucial to the answer to this question. So let's talk about this. So you want to solve this equation. This equation will generally not have exact solutions. So what you have to do, and I didn't talk about it, is to project this equation onto zero modes of the modular Hamiltonian. And then you have a solution, and that projection. Oh no, and there is one more thing. This V here, in general, is a complicated mess, but the complication arises from what happens far away from the RT surface. If I look at just the neighborhood of the RT surface, those geometric objects are given by the scrambling modes, which I mentioned but not on the slides. So if you limit the problem to setting V only to be valued in the scrambling modes, and put a projector onto P0, onto those zero modes of the modular Hamiltonian, then this equation makes sense. Without it, it doesn't have solutions. So what's the problem in non-holographic theories? You can't make that separation between scrambling modes and other modes. And so I can't do that thing. And that basically means that I can't think of modular parallel transport as a rotation in any sense. So that's the thing that makes it break.
Yeah, it's. Am I loud enough, or do I need this actually? Oh, okay, okay. I see. Yeah, so I want to thank the organizers, like everybody. I mean, it's amazing that I used to see many of you at least maybe once a year, but now I'm seeing you after so many years. So yeah, thanks for organizing this in-person conference and of course this opportunity. So yeah, I'm going to speak about some recent progress on excited state modular Hamiltonians. And I apologize to anyone who has actually heard me talk about this stuff before. I have some new things to add to that. And of course, there are also some new things that I'll have to kind of skip over in view of time. Okay. This work is based on some papers I wrote with Kabat, Lifshitz, and Fu Kiwen, and some ongoing work with them and with some students at Indore. Okay, and of course, please stop me at any point of time if you have any questions. All right, so Bartek really did set me up properly with discussing all these modular Hamiltonians and density matrices. So I'll be brief. As my title suggests, we'll deal with aspects of density matrices and modular Hamiltonians in field theory. I'll not say much about or maybe anything about holography. I mean the CFT that I'll deal with. I'll deal with some basically conformal field theories, but I think the results that we have to discuss also holds for field theory in general, but we'll see. We'll again talk about modular Hamiltonians as the title suggests. We'll talk about modular Hamiltonians in excited states. We'll excite them in a particular way. But I'll also talk about actually sub-region modular Hamiltonians, which I also have it here. So if you have some factorized Hilbert space, let's say you have some subregion, some region A, it's union of A union A bar. Then, if the Hilbert space is factorized over those two regions, then you can define, let's say I have defined some pure state psi, and then I can partial trace over one of the subregions to write down the density matrix of the other subregion. So rho A's are usually defined that way, and the modular Hamiltonian is defined correspondingly. For rho A, I have HA, for rho A bar, I have HA bar, and so on. But in fact, a better defined quantity in field theory, because it's typically you don't find factorized Hilbert spaces. A better defined quantity is actually extended modular Hamiltonian. So you define something, there is some Tomita construction, I don't want to get into the detail of that, but the better defined operator is not actually the density matrix, but this modular operator delta. And if you take the log of that minus log of that, you get this extended modular Hamiltonian, which I'll denote by H with some uppercase left right arrow. But if the theory is then factorized, if it is factorized into two regions, and if you can define rho A and rho A bar, in terms of those rho A and rho A bar, you can define delta like that. So delta will be rho A tensor rho A bar inverse.
And as a result, the modular Hamiltonian will be HA minus HA bar, if it is factorized. So the last two equations in the final equation only holds for factorized case. So we'll compute, so we'll mostly have in mind computing this extended modular Hamiltonians, but because we will have in mind that in field theory, you cannot always divide a region into two subregions and get factorized Hilbert spaces, but we'll also talk about the subregion modular Hamiltonians, and we'll see that even though it's in general not possible, you can still work with subregion modular Hamiltonians and rho A's and still find out something new about this extended modular Hamiltonians, which tells you something interesting thing about cases where the Hilbert spaces are not factorized. So, well, it will make sense in a moment. Okay, so and also not only we'll talk about H, we'll talk about H for states which are obtained by perturbing the vacuum states by some unitary operator G. So in particular, the excited state psi that I'll have in mind is some unitary operator U acting on the vacuum state. And as I said, I'll mostly talk about conformal field theories for computational ease. And this unitary operator will take the form of something like e to the minus I epsilon G, where G is some Hermitian operator. And that operator is obtained by integrating some Hermitian operator O with some support function f of x, where supported over some slice sigma, which is in general some space-like or null hypersurfaces. Okay. Okay.
So I think you can also define the modular Hamiltonian even if your state is, even if rho is not factorizable. You simply have to take the partial trace and define rho A. And
No, absolutely you can, but it's not. I think it doesn't give you a state which are normalizable and so on. So there are various maybe technical, if you are very, perfectionist, maybe you will not be happy with those operations. But as I said, I will be talking about H's and rho A's. But the point of view that I'll have is that even though I am working with H's and rho A's, if I am careful, I can actually pinpoint some extra features that these operators H's and rho A's have that show up in extended modular Hamiltonian. That comes up due to the fact that it's a field theory and it's not always factorizable. So hopefully it will be clear when I go ahead. Okay. So yeah, you can do that, and we have always done that, right? I mean, this Ruta-Kanagi computation, let's say in the holographic context, we have always, without any problem or hesitation, we have always worked with that. So there are extra problems involving gauge theories, but I'll not be talking about that. Okay, like factorizability issues for gauge theories, but I won't talk about that. Okay, so this will be the setup, and our framework will be it's mostly a conformal field theory for computational purposes, but we hope the results will go through for other field theories as well, for a particular reason that I'll mention, in some arbitrary dimensions D, and we'll compute, so this vacuum state had some modular Hamiltonian H. So now with this perturbation, I can expand the change in the modular Hamiltonian H in order by order in epsilon. And our main goal will be to, or for the most part, it will be to find out this change of modular Hamiltonian to first order in epsilon. Okay. Although I will also talk about situations where I consider higher order in epsilon corrections. In some cases I will, in some cases I'll just state the results but not show you the full calculations. Okay. And for the most part, the region that will take the subregion A, that will be Rindler half space, which is formed from some half space from 0 to infinity.
Since the geometry looks kind of like a local geometry, doesn't it just change the entanglement? But we expect it to not change the entanglement structure of the state at all, right? Because it looks like local.
I am am a bit confused about that. I will have something to say about entanglement as well. So let's just wait and we'll come to that point, okay? Yeah.
So the unit there is an exponential on a local thing, but then the exponential itself will have always applied at different locations. So won't they change the percentage?
Well, I was imagining that this, suppose I did some sort of lattice regularization of this kind of thing, then the pools would communicate at different points at different values of x. So I would be able to write the symmetry as a product of symmetries at each value. If I did some lattice regularization.
I think in that case you are right, but precisely for the non-discreteness there might be some effects. Yeah, exactly. Not really, no. We just took it to be some function. So, well, I will take, as we'll see, maybe, for some computational purposes, at some point I'll take f of x to be a constant function. But that's not necessary, really. So, it will actually work for all. I mean, we'll have a formula for the excited state modular Hamiltonian in terms of f and its derivatives and so on. So, we'll not specify what f is.
So even if the entanglement doesn't change, the modular Hamiltonian can change.
Sure, sure.
Yeah.
In that case, I don't expect this to change in a sort of trivial way, just conjugated by the corresponding local.
Yeah, exactly. So, yeah, and the point is that for the non-discreteness, that won't happen. So, yeah, as I said, this shows up in an interesting way in delta HA. And we will provide a general form of this delta H for when this operator O is some conformal primary, once again for computational, is Jn, whereby Jn I mean some operator with some so-called modular weight n. By modular weight I simply mean that if you, for example, take Rindler half space and modular conjugate your Jn of x by the corresponding modular Hamiltonian of the vacuum state, which is simply a boost generator modulo some 2 pi. Then under this transformation, so Jn when it goes to Jn of s under H naught, which is the vacuum modular Hamiltonian, it goes to this value. So it basically counts the number of x plus minus number of x minus indices in J. Okay. Yeah, so there are some earlier works on this. They are mostly they are correct and but mostly very formal. So these are a very incomplete list of references which discussed modular Hamiltonians in excited states in case of shape deformations and so on. But I guess what was not very clear, at least to me, from these papers were exactly disentangling those formal results and finding out these contributions that are coming up for field theory cases. Okay. All right, so these are the naive expectations. So if you had a slice which can be subdivided into A union A bar, it will imply that the perturbations that you are putting it also divides itself into GA plus GA bar. Okay, and since GA and GA bar commutes, as Onkar mentioned, the unitary transformation also factors like so. And then as a result, you will indeed expect that your density matrices of each of the subregions, it transforms by that unitary operator. So rho A and rho A bar will transform correspondingly with help of this UA and UA bar. And as a result, this modular operator delta that I talked about, delta naught simply means the modular operator of the vacuum state. That transforms by unitary operator and correspondingly the extended modular Hamiltonian. So the first order change will be simply this commutator piece, which I'll actually call the commutator piece from now on. Okay. But this is, as I said, this is only true for factorized systems and doesn't strictly hold for field theories. And there is an explicit, which I'll call an endpoint contribution, which are surface separating A and A bar, that comes up in delta H, and delta H therefore deviates from delta H commutator to delta H commutator plus some endpoint contribution. So this endpoint is basically, so if you think of a one-dimensional spatial slice, so it will be the point which separates A and A bar. Okay, and heuristically you can think that in continuous system you don't know to which subregion you assign this point to. It could be a part of A, is it part of A bar? You don't know. So in some sense this point is very special, and we'll see that that's why it deviates from this naive expectation of delta H being delta H commutator. So here are the results. I'm just showing you now, and the rest of the talk will be trying to derive some of these results. So we'll see that the endpoint contribution will vanish for operators with which you are perturbing if they have modular weights -1, 0, and 1. And if you have, we have only studied modular weights which are integer. So if they are integer greater than equal to 2, 2, 3, 4, and so on. So for example, n equals to 2 will be basically stress tensor. Let's say some t++ perturbation. And then the corresponding change in the excited state modular Hamiltonian, this delta H, to first order will be that commutator term plus an endpoint piece, delta H endpoint, which takes that form. Okay, that it is basically the operator with which you perturb and its descendants integrated over the x plus horizon. Okay, so x plus is like t plus x, it's the right moving horizon, x minus will be the other one. Yeah, and you also get these various derivatives of this support function. So it's a bit of complicated expression, and the theta is, I'll have a picture I think in the next slide. Theta is the theta is the kind of a parameter which makes it spatial. So if theta equals to 0, it will be a null slice. If theta equal to 1, it will be a constant time slice, and having some non-zero theta will mean it's some slice which is between the constant time slice and in the space like light cone region. And the simplest example of this correction delta H endpoint is obtained if n is 2. So if you perturb your state by stress tensor, we'll spend a lot of time with that because it's the simplest example. In that case, this delta H endpoint becomes this average null energy operator. So this operator that I wrote there, dx plus t plus plus x plus. And f0 is basically the value of the support function at the endpoint. Okay. And also up top I want to discuss one property of the endpoint term, which is the new term that I'm advertising, being the system being non-discrete or continuous, is that to first order you can use the fact that modular Hamiltonian or extended modular Hamiltonian annihilates the state. So H extended of a state psi has the property that H acting on that psi gives you 0. This is related to this modular automorphism property, so called. And if you expand that expression to first order in epsilon in our example, then it actually shows that delta H endpoints an identity that comes out, that this delta H endpoint must annihilate the vacuum state. And indeed, the light ray operator, for example, this NX operator that I mentioned for stress tensor perturbation, it does annihilate the vacuum state. And in fact, you can show that all of these for a generic Jn perturbation, you have this ugly looking term for delta H endpoint that also annihilates the vacuum state. There was this paper by Kravchuk, Simmons, Duffin who did it for k equal to 0. So only light ray operator involving dx plus jn. But you can very easily generalize that result, and you can show that the endpoint contributions, indeed annihilate the vacuum state. Okay. And same goes for the descendants of these, because they also appear in, so del minus to the L Jn for non-zero L, they will also have this same property. Okay. So here's the outline of the talk. I will mostly spend time on CFT vacuum perturbed by stress tensor because it's the simplest example. We have derived the corresponding endpoint contribution in 4 different ways. One by simply conformal transformation, and in 2 different ways by something that I am calling general operator method. I'll mention what I mean by that, of course, when I discuss that, and also using path integral methods. But for time purpose, I'll only show the conformal transformation way and the general operator methods way. But I'll probably briefly mention something about the path integral method as well. But you can actually use the conformal transformation method to find out the endpoint contribution at any order in epsilon, and also you can use path integral method and the general operator method to find out at least up to second order. You can find out for stress tensor perturbation, you can find out the resulting delta H. Yeah, by last 2 I mean general operator method and path integral method. In conformal transformation method, you can go at any order. Yeah, but conformal transformation method is very particular to stress tensor perturbation. So when we'll do it for other perturbations, we have to resort to other methods. And in those other methods, we can only do it up to order epsilon square, not more. So we only have, like, for higher modular weight operators, we can only do it 2 ways. So let's take a pause here and let me ask you if, no, I mean, in principle, what we have to do is very clear, but the computation gets really technical. Yeah. So, yeah, for example, in path integral method, when you want to go beyond second order, it's a mess. I mean, there is no, yeah. Anyway. Okay, any other questions about the setup of the problem? I'll be skipping probably many slides. I don't know how it goes, but I guess I'm hoping that at the end of the day, the ideas will be clear. Any questions? Like what we are aiming for, and okay. So if not, let's just start with the simplest case where you have a CFT2 vacuum perturbed by stress tensor. And we know, I mean, it's one of the typical examples that we use everywhere. The vacuum modular Hamiltonian for any subregion going from U to V is known, and it looks like that. And if you do a conformal transformation, you choose, so you do a conformal local conformal transformation from Z to G of Z, and you choose G of Z properly. So if you choose, for example, G of Z being Z plus some epsilon F of Z, then it actually becomes corresponds to or becomes equivalent to perturbing your state by this operator G that we introduced before. Okay. So it's very simple. You just start from the top equation, you do the conformal transformation, you get the second equation, and then if you want to find out an order epsilon contribution, you just expand G of Z up to first order in epsilon. If you want to go for higher order, you have to find out what is the order epsilon squared term. So for example, in order epsilon square, you will have epsilon square by 2 ff prime and so on, and epsilon cube and so on. So you can continue doing that. Okay. And then if you do that, you get that result. So I am only writing the order epsilon piece. I have subtracted out the vacuum piece. And you see the first line. The first line, in fact, is the commutator contribution that you would naively expect. So it is minus I epsilon G comma H naught. But the second line, you see, it depends on the support function F supported on U and V, which were the endpoint of these subregions. So if there were no support of those perturbations at those endpoints, you could still factorize and then the corresponding delta H would just be the commutator piece, and those FU FV terms will go away. Okay, so this, yes. Yeah, it is such that, so you get this NX operator for delta H extended. So for delta H, you will get kind of what we are calling half NX operator. It goes from 0 to infinity, but the same dx plus t plus plus. And for the other one, it will go from 0 to minus 0 to minus infinity or something. So that when you subtract that, you get minus infinity to infinity.
So both of them kind of half share the.
Yes, exactly. Yeah, yeah, yeah.
But is it obvious why they should half share? I mean, why should we?
I guess one way to realize that is, or understand that is by realizing that you can get delta HA bar from delta HA by doing a CPT transformation. So what we will do later on, for example, for other operator perturbation is compute delta HA and then so for the examples that I have in mind where going from A to A bar is actually doing CPT, only then I can use that argument for Rindler half spaces. But yeah, otherwise I cannot. So it's very difficult to find excited state modular Hamiltonian given an arbitrary state to begin with. Yeah, we'll see how CPT helps us, for example, in writing down the problem as well. Okay, so yeah, so it was not needed, but I did it anyway. So we took f of x. This is a very particular example where f of x is taken to be, the support function is taken to be a constant function over the endpoint. So that middle point where the crosshair is, it's the x equals to 0 point. So 0 to infinity is your Rindler half space. And then I took f function from going across the endpoint. So it's straddling the endpoint that way. And then for particularly in the Rindler limit, so you put u equals to 0 and v equals to infinity, you get that from the previous slide's expression, and then when you take a b to 0, so you zoom in on the endpoint, you get your endpoint contribution, the NX operator. So in general for UV subregion, the second line there is the delta H endpoint, but for Rindler subregion, this is it boils down to the NX operator. And obviously you see that if you naively took A and B to 0 to begin with, then you might have thought that okay, f just vanishes at the endpoint, then all the expressions will just go to 0. So well, yeah, you just have to take the limits at the end to see that NX operators come. Yes.
Like the very first equation.
Yes.
So that was not computed assuming factorization. I mean, I don't know. H0 UV was it computed assuming partial tracing or something?
Yeah, I think. Yeah, I think all the derivations I know actually comes from. I don't think so, because it's not that. So in fact we will also work with, I mean it's a fascinating thing that I can actually work and talk about delta HA in some sense. But if I am careful at what is going on near the endpoint, I can still find out this extra contribution.
Yeah, but actually my question was that if I look at say the second equation, was it computed by using HA minus HA bar or without that?
Yeah, for my purposes I will consider H UV naught that I have, that is the correct expression.
Yeah, but the derivation assume factorization. Their derivation.
Their derivation, yes, but yeah, there are also some field theory derivation, but I think that also, yeah, but I don't know, does anybody have some? Yeah, exactly. So It's also some combination of conformal generators, so I guess it's.
So, I mean, but the contact term, from what I understood, that the extra term you got
Mhm.
when you do the perturbation
Mhm.
shows you there's no factor in it, right? I mean, you have to be careful.
Yes, you have to be careful, and only when the excited
Right.
state perturbation that you have had no support at the endpoint, only then
Exactly.
it goes like
But
the way it
looks like
does.
as you're saying that this formula from which you got the contact term could have been derived by assuming factors. I mean, maybe I'm not. No, this derivation will be assumed as a summary term is generated by a symmetry. Of course, you are raising all the laws. This is like very, yeah, this is, sorry, kind of, yeah, this is purely follows from symmetry.
Yeah, for CFT2 it's really.
Okay. But the question is whether you really assume factorization as a, okay.
Yeah, I mean there are definitely derivations which assumes factorization, but yeah, as you said and you said, it's more general than that. They also give this answer. Yeah, yeah. I mean for Rindler, for sure H0 is the boost generator. For example, that follows from here. You take U's going to 0 V to infinity, you get the boost operator, and that is I mean, it does not it is true even for in general, right? I mean Bizognanu-Wichmann theorem. So yeah. All right, so a brief digression. So you can actually find out endpoint effects at higher orders as well. So at any order in epsilon, so the epsilon to the n order term, the corresponding commutator contribution will be these n nested commutators of H0 with the perturbation G. But the endpoint contribution actually will turn out to depend on the endpoint effect of the conformal transformation at that order. So as I said, this G of Z, this Z to G of Z conformal transformation that you did, you can order by order expand it. So let's call them this G superscript NZ. You know this, so corresponding HS will be like Z, FZ and so on. And then you can find out what is the order by order endpoint contributions at various orders in epsilon. So we did that, and it turns out, so I'm very quickly going over these slides, but the interesting thing is that it turns out.
So why can't there be contribution with the sort of like partly this, like some of the support is here and some of the support is the other end?
No, in U to V case that is indeed the case, right? It depends on FU and FV. But so from here onwards I took the Rindler limits and I am only considering the endpoint at x equals to 0.
Why can't you get from this FB times FU?
That will come at higher orders. Indeed. No, they come at higher orders. There are cross terms, yes. Yeah. In fact, that is clear from here. So let me just say, so the interesting thing about stress tensor perturbation in particular is that the endpoint contributions can also be written cleverly in terms of commutators. Okay, but commutators with some operators which I have called this E1, E2 and so on, and E1, E2 they look like this. Okay, so you see E1 was our usual NX operator, E2 has F0, F prime 0, and E3 has some coefficients which are like that, and if you do it for non-Rindler case, it will correspond to those cross terms, FUFV, FUFV square and so on. In general, these ENs, they take the form of minus I, G superscript N0, which were the conformal transformation at the endpoint with the NX operator. So it just so happens is that for stress tensor perturbation, although there is this endpoint contribution, it is also possible to write that endpoint contribution in terms of a unitary transformation. And actually, so the sum over all the endpoint contributions at all orders, if you sum it over, then it becomes minus 2 pi G0, which is this conformal transformation at the endpoint U, and it's a unitary transformation of the NX operator. Okay, and I have some comments about entanglement entropy. As I said, I am myself a bit confused about this. So I want to take the point of view of this paper, JLMS, and paper by Kabat and Lifshitz back from in 2017. So the point of view is that if I do this calculation of modular Hamiltonian on the plane, so in the z plane, so t minus x, t plus x, and so on. So I have some expression of modular Hamiltonian that I showed you before, and then you go to the corresponding Rindler patch given by chi rho coordinates. So it is the Rindler patch that only parameterizes the corresponding causal diamond of the boundary subregion. Then you can write down this modular Hamiltonian in these eta coordinates in Rindler patches, and that HA eta will be your original modular Hamiltonian HA in the plane plus some area by 4G, where this area term comes from the Schwarzian, from this conformal transformation. So I guess the interpretation was that this HZ is the bulk modular Hamiltonian, and the classical piece of HA eta is area by 4G. So what we can do is we can now find a similar correction to the modular Hamiltonian on the plane by going to the excited state and then go to the Rindler and find out corrections to these area terms. Because you see, in the plane the problem was that if I take the expectation value of the modular Hamiltonian, which gives you the entanglement entropy, that's basically 1 point function of the stress tensor, which gives you 0. So that's why we found it easier to actually go to the Rindler and then read off the expectation value of the modular Hamiltonian in Rindler, so HA eta as the area by 4G term. Okay. It was a bit quick, I think, but we can come to that later, or if there are any questions, I'm happy to answer. Okay. But that's just one slide I have on entanglement entropy. Yeah. Sorry, yes. This is because of lack of time. I quickly went over. Yeah. So there will be some Schwarzian piece, but if it were holographic, then I would talk about some area term. It was just to, kind of motivate that HA eta's expectation value gives me the entanglement entropy, if it were holographic theories. This slide is a bit detached from the other ones. Yeah. But I don't need to go to holographic CFTs. Yeah. Okay. So now we can talk about this derivation of delta H via general operator method. And so you can start with, so this method will be working for all types of perturbations, all types of excitations, for all those Jn operators. Okay. So you can start with a Schmidt decomposed form of the vacuum state, and then you excite that corresponding rho a 0 and rho a bar 0. So here again, so please try to understand this point. So once again, I am working with a Schmidt decomposed form of the vacuum state. I am working with rho a 0 and rho a bar 0, which I should not have done. Okay, I advocated that no, I should not do it, but I am doing it anyway. But the point of view is again that even if I do that, but then if I am careful about near endpoint region, then I should get back what I should actually get for the excited state. Okay. So yeah, so I have some rho a 0, rho a bar 0, which I can also do for the excited state psi for those perturbations. And if I assume my excitations also factors into GA tensor GA bar, then I can write down the corresponding delta rho's, and they take that form. Well, it's generalizable to the superpositions of them as well. But I can write down this delta rho a in a much simpler form by taking, which is also only true or possible for Rindler half spaces, by doing a modular conjugations on GA bar. Okay. So what is the setup I have? I have some vacuum state on some A union A bar region. I excited that state, I went to the psi state, And I went to the excited state by assuming that the perturbation I have, G, has the form GA tensor GA bar. Okay. And then I am taking this GA bar piece, I am modular conjugating it with J, J being the CPT operator, CPT transformation, so that GA bar tilde is an operator for the A region. Okay, so I want to write down this delta rho A, which is expressible only in terms of operators that act on the A region. So GA and GA bar tilde. Yeah. So and that is actually the final expression. And there is in fact a nice way to generalize it. In fact, to any order epsilon to the n, the corresponding change in the density matrix for the region A looks like that. So it's a nested commutator, and at the center of it you have rho A 0 to the half, GA bar tilde to the n, rho A 0 to the half, comma GA. So you see that if GA bar were identity, so if it were only a perturbation on the A region, then it would simply be a commutator. So rho A 0 will simply evolve like we should expect it to at order epsilon to the n. And this formula already tells you that you should get something which is beyond the commutator contribution. Okay. So our next goal is simple, and by the way, there is also a way to compute this delta rho A from path integral method. So I don't have the figure here, but you can think of constructing the state as inserting e to the I epsilon GA on the right in the Euclidean tau greater than, those of you who are familiar with this path integral way of constructing states. So you insert some e to the I epsilon GA operator on the upper half, tau greater than 0 part of the tau equal to 0 slice. You rotate it by pi, you insert e to the I GA bar tilde, and then you go to the lower half of the side coming from the ket. So you insert another e to the minus I GA bar tilde, you rotate by again a pi transformation, and you insert again a e to the I epsilon GA. So sorry, this was very quick, I did not want to startle you, but if you understood it, then that is one way of deriving delta rho A as well. So once you have found delta rho A, there is a nice formula by Sarosian-Ugajin which you have used to find out delta H. So it basically, the derivation can be done quite simply, but I will not go through the derivations, but this formula basically tells you that because H plus delta H is minus log of rho plus delta rho, so it tells you that given delta rho, there is this nice ds over 1 plus cos over log s blah blah blah. With that you can find out the delta H piece. So our goal will be to use that delta rho, plug it in there and find out delta H. Okay. So well, so that's what we did. So that's the formula. So it's basically coming from combining that delta rho plugged in into that formula. Okay. So in terms of, if you write this expression in terms of the modular float operator, so O at some modular time S is given by, you know, that quantity modular float by rho A 0 to the those factors, then the final expression boils down to that. Okay. GS minus I pi is given, it's a very simple formula. And then our goal will be to evaluate the right hand side and find out what is delta H for a given GA. Okay. Any questions so far? Yeah, I don't have much time left, but any questions? Okay. Yeah. Right, right, indeed. So in twirled page map, it's a, for those of you who do not know, it comes up in at least the one I am familiar with, is papers by Pennington and Swingle and others. It came up in the context of bulk reconstruction. So it basically gave you a formula for bulk operator instead of boundary operator, and the kernel that appears in their relation is basically this this formula that they have in the Sarosian-Ugajin. Okay. And it's a very interesting question, like then whether the bulk reconstruction has something to do with this excited state modular Hamiltonian and so on. Well, I think it's entirely possible that, and we know there is a reason why that happens, but we still have to figure that out. Like, I mean, as you might know that there is a bulk reconstruction technique using modular Hamiltonians, much the way Bartek discussed. So you have two intersecting modular Hamiltonians for the holographic theories, of course. And then you find out the eigenmode which satisfies the eigenmode equations for both H's if there are two intersecting modular Hamiltonians. So it would be interesting to see that what happens when we go to the excited state, whether that's why somehow these Bates map have that delta H or not. Okay. We'll discuss it later. Okay, so right, right. Mm-hmm.
So that this reconstruction, this actually makes sure that the errors, you can correct for all the errors of it. And of course, in the code you only correct it very approximately, but
yeah, no, I want to look into that problem. I have that in mind. I just don't have a final answer. Yes. Yeah. Okay. So imaginary, yeah. It is well defined. At least we have, went up to rho to the minus half, which is imaginary s, up to the value I think pi it will turn out to be. So from Wheaton's review, I know that up to that point it is still okay. Beyond that, it goes outside of some analyticity window. So all I'm saying in that slide is that, of course, the first equation is obtained by substituting that delta rho into that formula, and I just simplified the first equation by using this definition that is there in the second equation. So all those you see those GA bar tilde S, that is obtained because I have some rho A0 to the IS by 2 pi on the right. I'll introduce some rho A0 to the minus IS by 2 pi and plus IS by 2 pi in between, and then I will combine that, and I will also be able to write GA S minus I pi. Okay, so just a rewriting. But the point is that while doing the rewriting, as you said, there is this modular flow. So in that formula, delta to the IS by 2 pi, the S is real. But I have to also go to imaginary S because there is this S minus I pi. But up to that much modular flow is okay. So it kind of saturates, this formula kind of saturates the analyticity bound, it turns out. Okay, so I will be skipping slides, but don't worry. I hope, okay. So basically, I'll just discuss how we have computed it. This is our main formula. These are our perturbations. So our G is, so this is the best way to proceed. You have found out there are other ways as well, but I'll only discuss this. G is GA plus GA bar, but I have to be careful about near endpoint region. Okay, GA is that, so it's on some special blue slice parameterized by theta. GA bar is that, so the perturbation actually straddles the endpoint over this blue region, you can write down your delta HA. Then using that formula, the first equation is basically the equation I had before, and the second equation is basically rewriting of the first equation by taking going to some parameter W, which is e to the minus s. Okay. So to be very careful, what we have actually done is to consider delta HA inside the correlation function with some another operator. Let's call it some spectator operator J and Y, and we have studied this delta HA J and Y correlator. Okay, so that will, because it's very difficult to actually work with the operators. So then you will encounter correlators like that, GAS plus minus I pi plus GA bar tilde S with JNY. And you can study its analyticity structure and you will be able to do these integrals. And while doing these integrals, then you will hope that from those integral results I can again strip off J and Y and find out what is delta Ej and hopefully come up with these operator expressions. Okay. So, okay. So, very quickly, so if you compute these correlators GS plus minus I pi plus GA bar tilde S J and Y, you can find out that at very early and late modular times, so S going to plus infinity or minus infinity, so W going to 0 to infinity, they are actually well behaved only if you keep those GA bar tilde terms added to GA, S plus minus I pi. So even if you see, if you look at the first equation, it looks like GA bar tilde cancels. But the point is that if you just cancel them out and worked with GAS minus I pi minus GS plus I pi, then these correlators will actually not have a good early and late time modular time limits. So to us, this kind of hints to the fact that I cannot get rid of GA bars, and whenever computing the correlators, I have to keep them together. So it's kind of a hint, I mean, sign for us that it's it tells us that I should not just cancel them out and treat them as if it is separable Hilbert space. So okay, so and also I have this imaginary modular flows given by S plus minus I pi. So we'll regulate them by going to some S plus minus IR, where R goes from 0 to pi. And we'll consider these correlation functions, and then we'll study how those correlation functions go as we take R from 0 to pi. Okay. Oh, okay, great. Okay, so so there are various regularization that we are using. So first of all, I kept those GA bar tildes to keep these correlation functions well behaved at late and early times. Then I introduced those IRs to make sure that as I write down these correlators for a generic R, where R is somewhere between 0 to pi, and then take R equal to pi, then I have a nice cancellation at of these divergences at minus infinity and infinity, or at W values 0 and infinity. So to begin with, you see I have taken 0 plus and infinity minus because at these points they diverge, but then those divergences do not cancel for a generic value of R, but when you keep these terms as well and then you take R to pi, then at these two limits they actually do converge. So that is the kind of steps in which we have to take the limits. Okay. So what will happen basically is that when you study these correlation functions, you will see that depending on the location of the spectator operator Y, which you have taken to be located in the left region. So you see if this is the x plus x minus, then this is some space-like slice, and we are computing this delta HA here, and we have taken the spectator operator here. Okay. So we have taken it to be in a place where Y plus is negative and Y minus is positive. So this is x plus and this is x minus. So it's in this quadrant. So depending on that location, I'll get various branch cards where these correlation functions have divergences, because these are field theory correlation functions. And the main reason we took CFTs is so that I can write down these correlation functions and study them explicitly. So these various branch cards will appear in the W plane, and they will rotate as R goes from 0 to pi, and accordingly, you have to deform the contour. And at the end of the day, when R is pi, then that will be the contour structure. Just trust me on that. And basically, that is the integral that you have to do. Okay. So let me consider some special cases. Okay, is the idea clear? What we are doing, how we are regularizing, and so on? Okay. So, so some special cases. suppose the perturbation is just on A region. Yeah. So the perturbation does not go from minus B to A, but rather B is also negative. So it goes from somewhere in the A region to somewhere else in the A region. Then the branch cuts will look like that. Okay, so there won't be branch cuts on the left side in the W plane. And in that case, you can actually deform the contour to only circle this -1 pole, which is coming from the Sarosi-Ugajin formula from this basically ds over 1 plus cos hyperbolic s, which gives you this W plus 1 square. So there is a pole at W equals to -1. And as a result, you can just take this contour to encircle that pole, and you will see that that gives you a delta HA, which is the commutator piece. Okay. So this is expected that if the perturbation were solely on the A region, you only get the commutator piece as the change at order epsilon. However, if the entire perturbation is on the A bar region, so both A and B is so B is positive, so minus B is negative, but A is also negative. Then all the cuts are here, and the contours will not encircle any cuts, and they will integrate to 0, which again is expected because delta HA is not then modified, right? Because the perturbation is only in the A bar region. And then comes the most difficult case where the perturbation straddles the endpoint. And how much time do I have?
5 minutes. Should include questions.
Yes, yes. So so in this case, actually, you have to be a bit careful in doing these branch cut prescriptions, and at the end of the day, you can find out that near x plus equal to 0, these correlation functions will have a delta to the k singularities. You can do some numerics. These are technical parts, so I mean, okay, it's all right to skip, I guess, for now. And then you can actually find out, the final result, which we advertised before. Okay, so I can come back to this later on if you are interested in knowing the technical details, but from now on, I just want to go to future directions, just say a few things and take questions. So of course, we have many questions. These are some probably questions that I found interesting is what about then gauge theories? There is also a non-factorizability issues there. One other thing that we are very confused about is what about perturbations over a causal diamond? So we took only spatial perturbations, so supports over spatial functions, and if there are some time-like support, then there are some issues. So we need to straighten that out as well. What about similar contributions in related quantities like relative modular Hamiltonian and so on, relative modular operator and etc. So that has not been, I think, studied yet. We have some results on that. What about higher order contributions for other perturbations? As I said that we could only do up to second order using path integral methods and these operator methods that I showed at the end. It definitely has to do with some algebraic properties of the QFT, this recent surge in work in type 1, type 3 von Neumann algebras and so on. So whether there is a kind of von Neumann algebraic way of deriving these endpoint contributions. And last but not least, we actually became interested in this topic from the holographic side, because as I was telling you that we were trying to understand modular Hamiltonian way of constructing local bulk operators, and we wanted to ask ourselves, okay, what if we can do similar methods and try to find out bulk operators in excited states, and then we needed to know excited state modular Hamiltonian. So hopefully using our results we can also apply it to holography. Okay, thanks a lot.
So if you look at the boundary CFT approach to entanglement, for example, related, but what so-called Catholic belief, the boundary
I don't think I know the answer to that, but I'll think about it.
Okay.
Yeah, yeah.
In much of your discussion, it seems like you were two-dimensional CFD.
Yeah, even if I went to d-dimensions, I was thinking other dimensions with spectators and only the perturbation are only in that 2D. Yeah. But I mean, you can, in that setup at least we can still write down and the correlation functions and actually work with all these.
Do you think generalizes from the thing, kind of general perturbation and three-dimensional CFD?
Yeah, that would be, so far we have not done that, but we hope to do that definitely. That would be an immediate generalization. I mean, it's in principle doable because I know those correlation functions. It's just a complicated calculation.
Any other questions? Okay. Thank you again.
One announcement, you can put up your posters during the break. Hareram is finished.
And what about the pizza?
Pizza should be coming.
In the same place? We have a
Yes, pizza, yes.
session officially from 16 to 17.
Yeah, just outside.
Yeah, now we have a break, right?
We have a break.
We have a break.
No, but new people arrived, so we should announce it. We have a pizza and poster session after the last talk of the day from 6 to 7 p.m. where we have not only pizzas but other stuff. Don't have my
And the pointer is this?
It's not working.
Oh, that's
we
not
have a
working.
display.
So it's just this.
You just change the slide only.
Okay, thank you.
Okay, let's start the last session. We have to have Onkar and Sarkar, and he will tell us about canonical implications and the quantum external shock.
Thank you so much. I hope you can all hear me. Great. Okay. Thank you so much to the organizers for organizing this wonderful workshop and for giving me the opportunity to speak here. So I want to tell you about some work we've been doing with a student of mine, Vivek Singh, at TIFR. And so hopefully the paper is going to appear soon at some point. Okay. So it's about what is called a canonical purification and some subtleties involving quantum extremality in holographic theories. So hopefully the words will become clear as we go along. But let's to start with, let's start with something simple. So consider, let's say a finite dimensional situation where we have some bipartition of the Hilbert space in terms of what I'm going to call left and right, so H left tensor H right. And let's say we have some state psi which lives in this bipartite Hilbert space. And for such states, I can always do what is called a Schmidt decomposition, which is to say that I can write the state as a sum, as shown in this equation, where you have some set of numbers, some set of real numbers, Pn's, which you can think of as the eigenvalues of the reduced density matrix on either side. And then there are eigenstates, which I'm calling chi's sub n for the right side and chi tilde sub n for the left side. So these are, of course, different between the left and the right. But you could think of these as one sort of choice, if you like, of the eigenstates of the reduced density matrix on the right and the left, respectively. And as I said, the eigenvalues, of course, are common to both the density matrices, but the eigenstates are not. Okay? Yeah. So, for example, they're the same dimension, and all the PNs are non-zero. Yeah. Right. Now. Yeah. That's correct. Exactly. That's right. So on the other hand, suppose we were only given access to one party, let's say we are given only access to the left party, then of course you only that means that you only have access to the reduced density matrix on the left side, and then in that situation you can try to purify the density matrix and write down a pure state in a somewhat canonical way. So this is called the canonical purification. So what you do is you basically, keep the same sort of eigenstates, if you like, on the left, but on the right, on the other side, you just sort of introduce a fictitious system, which I'm going to call L star, and essentially it has the same set of eigenstates on the other side, on the L star system. There is a slight subtlety with this. There's a anti-unit. You have to put an anti-unitary operator, which I'm calling theta here, which sort of you can think of as CPT, right? You sort of CPT reflect the left system into the L star system, but modulo that, it's basically taking two copies of L and putting them together into a pure state. Okay, so this should be contrasted against the original state psi, which had some chi n's on the right. So these chi n's were something different, but since we don't have access to the right, the best we can do, or one purification that you could do, which is canonical in a certain sense, is you just take two copies of chi tildes, okay, and you retain, of course, the same set of eigenvalues. Okay, so this is called the canonical purification of psi with respect to the left side, let's say, and you might see, or one thing to note is that the psi star, the canonical purification, in some sense resembles the thermophile double state, right? It's the thermophile double state is the canonical purification of the thermal density matrix, and you could think of psi star in a sense as the simplest purification that you can write down if you only had access to the density matrix on one side. Okay, it's not the same as the original state, of course, but that's okay. This is sort of the simplest purification. Now, since these two states, psi and psi star, are purifications of the same density matrix on the left, okay, they must be related to each other by a unitary transformation only acting on the right factor. Okay, so I'm going to call this unitary transformation curly R, and for the lack of a better word, I'm going to call it the reflection operator. So you can think of this reflection operator R as quantifying, how hard or how complex is it to reconstruct the state psi from the canonical purification, or only given access to information on one side, how hard is it to construct the original state psi? And you should note that, of course, this reflection operator goes sort of beyond just entanglement in quantifying properties of the state, because both psi and psi star have the same entanglement structure, okay, or the entanglement spectrum is the same. Now, why should we study the reflection operator? Yes. Oh, no, it's psi. So it maps from psi n on the right to psi tilde on the left. It has this particular form, yes. So if you like, if written this way, it looks kind of diagonal, yeah. That's correct. That's correct. Yeah. So I'll come to the phases in a little bit, but no. So there's no other ambiguity, because psi star is you give me psi, and psi star is uniquely defined, right? Yeah, that's right. Yeah, no more. There's no more ambiguity than that. That's right. Yes. Yeah, so I'm going to assume that, yeah. It need not be the case. In that case, the R here, the reflection operator, is not a unitary operator. It's some projection. It projects onto the relevant subspace. Yes. Yeah.
arbitrary duality.
Yeah, yeah.
And that means that basically that this purification you're working with doesn't have that thermophile double-like structure, but pretty much an arbitrary purification. But in your star, you're narrowing down the problem to those thermophile double-like.
The purifications I'm working with are thermophile double-like. That's correct. Yes, yes. But the R is a more general. The R is a more general unitary operator, though. Reflection operator, of course, is more general. But you're right. The purifications I'm working with are special. That's why it's canonical. Otherwise, it would not be canonical. Yeah. You had a comment?
There's no loss of generality in what you've done.
Yeah, yeah. So far, it's just completely done. Yes. Okay. So, any other comments or questions? Okay, great. Yes. Other way? Which other way you're talking about? Oh, yeah, yeah. R dagger in this case. So, yeah, it's the difference between R and R dagger. If it was not maximally mixed, it was not a full rank state, then there would be a difference, because then you have to say which is the higher dimensional Hilbert space and so on. But here, there's no difference. It's just, yeah. Well, not particularly. I did not have that in mind. Here, I'm just working with full rank states. Yes, yes, yes. Any other questions or comments? Okay, so I was just explaining why one might be interested in studying these kind of reflection operators and canonical purifications, because it sounds kind of abstract. Yes, yeah. That's because, so let me go back one step. So here, so if I had just put the same chi's tildes on the other side, there would be this phase ambiguity would come and be an issue, right? Because depending on what phase you chose. That's right, exactly. So that gets rid of the phase ambiguity also, yes. Yeah, that's right. So in that case, you don't have to worry about that, yes. So in situations where the density matrix commutes with the CPT operator, you don't have to worry about this, yes. Okay, so why would I be interested in studying the reflection operator at all, or more generally the canonical purification? Well, so let me give you a series of motivations for why you might be interested in this question. So one of the motivation comes from this nice work of Harlow, where he argues, based basically on the Ryuta-Kainagi formula, that the ADS-CFT map from bulk to boundary has the structure of a quantum error correcting code. Okay, so one of the things that Harlow shows in his paper is that the map from some bulk state I to the boundary CFT takes this form, where this operator U appearing here is some unitary operator which acts on the boundary subregion A, and what we have in mind here is that this I is some physical degree of freedom which lives inside the entanglement wedge of A. Okay, if the physical degree of freedom in the bulk lives in the entanglement wedge of A, then the bulk to boundary map takes this form, where this U sub A is some unitary operator acting on the boundary subregion A, and in particular, you can think of this U sub A as being sort of the reconstruction operator. That's the thing you can use to reconstruct the information in the entanglement wedge. And one way to think about this U sub A is in terms of the reflection operator. So what you could do is you could define a state capital psi, which is just this sort of maximally entangled combination of your code subspace with some reference degree of freedom. So this I reference is just some reference Hilbert space that you introduce by hand. It has the same dimension as the code subspace. And then it's easy to check, and I'm not showing the details here because this is just sort of broad motivation, but it's easy to check that for this particular state psi, this U that appears in Harlow's theorem is basically the reflection operator with respect to the reference union A bar system in the setup. Sorry?
How does the unitary become anti-unitary?
Anti-unit. Where did I say that?
The reflection operator.
No. So the reflection operator is just a unitary operator which acts on.
Oh, yeah.
Yeah. It's the thing that maps the psi to psi star. Yeah. Yeah. Yeah.
So the next thing that is set to the next slide.
Yes. Yes.
This reflection becomes. So this observation is also made in the West Coast model, right? Like
The West Coast model.
This degrees of freedom is living at the end of the line.
Okay.
And then they are maximally coupling the eyes to the CFT degrees of freedom.
Okay.
And I think they make a similar reconstruction, sort of.
Well, okay. So in the West Coast model, they use they use the SPETS map to do the bulk reconstruction. Maybe you're suggesting that you could also use this kind of technology to do. Okay, yeah, possibly. I haven't really thought about that, but yeah, possibly. Yeah. Right. So I was just trying to motivate the fact that some of the ingredients which appear inside Harlow's theorem are related to the reflection operator. Okay. So from that point of view, the reflection operator is kind of natural to think about because it sort of goes into trying to formulate ADS-CFT as a quantum error correcting code. Okay. So that's one motivation why you might want to study this quantity. Yes. Yes, I think so. Yes, I think that's yes.
Why should all this quantum error correcting code will have the Harlow structure?
Well, error correcting codes with the kind of complementary recovery that Harlow's code has. Yeah. So with a certain kind of structure that you might want to build in will then be rewritable in terms of reflection operators. Yes. Yes.
Complementary recovery is a very strong requirement. Typically, you only require recovery, you do not require complementary recovery.
Well, okay, we can discuss that, but all right. Actually, this doesn't even require complementary recovery. What I said, I think, just requires recovery. So. Yeah.
But the fact that you get a Harlow-type structure after reflection.
No, I think that just requires recovery. At least this structure, the part I've used here, is just recovery. It's recovery under erasure of A bar. That's all that it uses. Yeah. All right. So a second motivation for why you might want to study the reflection operator is that recently there has been some interesting work on new kinds of measures of entanglement called one such measure, for example, is the thing called reflected entropy. And this reflected entropy, which was defined in this paper by Datta and Faulkner, is defined in terms of the canonical purification. Okay, so the way you define it is that if you give me a mixed two-party state rho AB, then what you do is you first construct the canonical purification of rho AB. Let's call that state psi star of AB, A star, B star. It's a purification, so it now has 4 parties in it, A, B, and A star, B star. And then you compute the entanglement entropy of A and A star in this canonically purified state. Okay, and this reflected entropy has some very nice geometric interpretation in ADS-CFT in terms of the entanglement wedge cross section and so on. There's a very beautiful story there. So, for that reasons, you might be interested in studying the canonical purification. Okay, and one last piece of motivation that I'll leave you with is that in a recent paper by Engelhardt and Folkstad, they argued that if you have an evaporating black hole past its page time, then the canonical purification of that state actually has in its bulk dual a connected ER equals EPR type wormhole. Okay, so the evaporating black hole by itself, of course, doesn't have such an ER equals EPR wormhole in it, but to see the geometrization of entanglement in that context, what you have to do is you have to go to the canonical purification of the evaporating black hole with respect to the black hole side. Okay? Yes? No, in the Lorentzian geometry. Yeah, that's what I mean by ER equals EPR wormhole. Yeah, exactly. That's right. Right. So in a sense, the reflection operator in this context is what is responsible for geometrizing the entanglement in an evaporating black hole. Okay. So from that point of view as well, it sounds interesting and something that we ought to study. Okay. So that's all the motivation that I'll give. So the rest of the talk will be about trying to study the reflection operator and relatedly the canonical purification in a holographic context. So in a very nice, so there's a very nice prescription for what the bulk dual of the canonical purification is due to Engelhardt and Wall. So let me just briefly review what their prescription is. So the idea is as follows. You know, in a canonical purification, what you do is you just take the one side, let's say the left side, and you kind of double it, right? You double it, and you throw away all information of the right side. You just double left, and that's what the canonical purification is. So what Engelhardt and Wall said was that let's do the same thing on the gravity side, right? You take the entanglement wedge of the left side, and instead of like having the entanglement wedge of the right side on the other side, you sort of erase that and you duplicate the entanglement wedge of the left side up to a CPT transformation, and then you glue them together at the quantum extremal surface, or if you like the extremal surface, the Ryuta-Kainagi surface in the classical case. Okay, so this gives you some part of the geometry. But importantly, this geometry has a Cauchy slice running through it, which I have denoted here with a blue line. So then they say, well, you have some part of the geometry, you have Cauchy data, you can evolve it using Einstein's equations and generate the full geometry. Okay, so that is the Engelhardt-Wall prescription for what is the bulk dual to the canonical purification of a state, of a holographic state. Now, there is, of course, one thing you should do when you glue together pieces of space-time in general relativity is that you should check to make sure that they satisfy the junction conditions, right? So Einstein, for the resulting geometries to satisfy Einstein's equations, the gluing must satisfy the Israel junction conditions. Yeah. Yeah, this is true in all dimensions. Yes. Yeah, so exactly. So that's going to be, so the next comment is about that. So what you can show in all dimensions is that the Israel junction conditions for this type of gluing is trivially satisfied when the gluing surface has 0 expansions. Okay, so the null expansions of the surface, as long as those are 0, then the Israel junction conditions are trivially satisfied. And in the situation where this quantum extremal surface is actually classically extremal, namely it's just a minimal surface or an extremal area surface, this is true. Okay, so in the HRT setup, for example, this is true, and so the gluing conditions are satisfied. The Israel junction conditions are satisfied, so this geometry will satisfy Einstein's equations. Period. Okay, end of discussion. Yeah. Yes, that's right. That's right. If you take one wedge of the, yeah, exactly, you're right. If you take one wedge, one side, and you reflect it in this way and glue it together at the bifurcation point, then you get the full eternal black hole. That's right. Without the interior, but then you evolve. Yeah, so you get this kind of picture, and then the claim is you evolve it using Einstein's equations to generate the full geometry. Yeah. Yes. Yes. Uh-huh. Excitations? Okay. Mm-hmm. Okay. Yeah. That's right. So you lose all that information, and the new geometry will just will look like 2 copies of L glued together at the quantum extremal surface. Yeah, it's because the constraint comes if you go through the constraint equations, they're very localized at the gluing surface, the HRT surface, so the surface where you're doing the gluing. So what's happening deep in the right-hand side region is not going to affect the constraint equations.
But EH, but what I was asking that
Yeah.
H star is Kibe just formed because HR now, right? Like I mean, I don't know exactly. Right, because I could have some very high degrees of freedom in the arbitrary.
Yes.
So the dimension, normally the dimension of the L star inverse state is
Uh-huh.
less than 7. Like I have to make sure that doesn't happen.
Well, this is a purely gravity construction. Yeah.
In general, I was asking.
In general, you mean if you had a setup where you had a lower dimensional CFT entangled with a higher dimensional? Yeah. Yeah. Okay. Yeah. Okay. Boundary conditions at you mean asymptotic boundaries, right? But those are included here. Right, but the wedge has the asymptotic boundary. Right. Well, I mean, in this is the kind of setup we have in mind is that so yeah, good point. So it will determine the geometry till you hit some caustics or something like that. I mean, the kind of thing that yeah. Yeah. Yes. That's correct. So that at that point you'll have some caustics or something like that, and then I agree. I completely agree. Yes. Yes.
Suppose you take an internal macrogeometry.
Yes.
And then you put perturbations on both sides.
Okay.
And we will not get anything like a bifurcation.
Why?
Generally, like we can produce traversable wormholes because you put some negative.
You mean you're going to destroy the isometry of the bulk? Yeah. Sure. Okay. Sure.
So in that case, suppose I take only the left half. Is it understood how this? Because okay, now if I look at the full geometry, it's like a pure state. It's model of some pure state because you are explicitly putting some perturbations on both sides. So now, so if I just take the left half, the right half is not the canonical purification of the left.
Correct. Yes.
Is something different from this.
Yes.
Because there is no bifurcation point in the original.
That's right. So what that means is that whatever is the reflection, it's the reflection operator which is adding these perturbations to your original undeformed geometry. That's how I would think about it.
If you take a homotopy double and you add perturbations on both sides,
yes.
You get a pure state.
Yes.
But then the right hand side is not the canonical purification. Or just to add perturbations into one side.
Right.
The right hand side will not be the canonical purification.
That's true, but that doesn't have to be true.
Doesn't have to.
Yeah, that's true. Yeah. Yeah, so canonical purification is a different state from the original state that you start with. In particular, it's related to the original state by a one-sided geometry operator. Yeah. Okay, good. So I was describing that in the Engelhardt wall setup, at least if the quantum extremal surface is classically extremal, there are no issues because the Israel junction conditions are sort of trivially satisfied. Okay. But there is a subtlety which comes up when the quantum extremal surface is actually quantum, namely that if a quantum extremal surface is not classically extremal, it satisfies the second equation here, namely that the expansions are not zero, but they are given by the first derivatives or shape derivatives of the bulk entanglement entropy. Okay, so that's how a quantum extremal surface is defined. It extremizes the generalized entropy in the bulk, not just the area term. So in a situation where the bulk term is important, or in a situation where the QES is not classically extremal, the Israel junction conditions are not trivially satisfied, but what they imply is that there has to be a delta function contribution to the bulk stress tensor, the stress tensor of the bulk matter, in the bulk dual to the canonically purified state, with this particular coefficient of the delta function. The coefficient is entirely determined by this first derivative of the bulk entropy. Okay, so this is the fact that the bulk matter stress tensor has to have this specific shock, this sort of shock, a delta function contribution in it, in the bulk dual to the canonically purified state, is just a prediction of Einstein's equations. Okay, You just do Engelhardt. If you push through the Engelhardt wall prescription in this setup, and you demand Einstein's equations be satisfied in the bulk, then this is a natural sort of outcome of that. So what we are going to aim to do in this talk is we are going to try and understand where this shock contribution comes from a boundary CFT point of view. Okay, so this was a completely GR argument, and we want to understand just from the CFT point of view, if I do this canonical purification and compute the bulk stress tensor, why does it have, or does it have this precise shock or not? Yes. Right. Okay, so the Engelhardt wall prescription is that you do it at the QES, and I mean I guess the intuition behind that is that the entire entanglement wedge contained inside the domain of dependence of the let's say right hand side is reconstructible from the right, so the full density matrix on the right should go all the way up to the QES and so on. That's the intuition, I guess. Now, I think you're right. If you, my impression is that if you included finite n corrections, I mean, not finite n, but the kind of thing that one talks about where one includes perturbative G-Newton corrections to all orders, then that could potentially smooth out the singularity. That's my vague understanding of this. That's not been checked or shown whether including these finite n corrections actually smooths out the shock or not, but that's what I would expect to happen. Perturbative corrections in G-Newton to all orders presumably smoothen out the shock. But okay, that's not something that I know for sure. Yeah. Good. So as I was saying, our goal in this work was to understand where this shock contribution, which sort of is a prediction of general relativity, where that comes from a boundary CFT point of view. And just one comment about that is that since the shock is a prediction of the Einstein's equation from the bulk point of view, then you could interpret this as sort of seeing the emergence of Einstein's equations in the bulk from the perspective of the boundary entanglement structure, but in a context where quantum corrections are important. Okay, that's a sort of side remark. Okay, so let's get down to the details. So what I'm going to do is, for the next few slides, I'm going to just try and okay. So one thing I should say is that the setup in which we are going to try and establish this is a perturbative setup where we work around some known state and we sort of deform it away from that state and try to see the emergence of this bulk shock. So to that effect, what I'm going to try and do is I'm going to try and, in the next few slides, establish this sort of perturbation theory. Okay. Okay. So let's say that you have some one parameter family of states psi lambda. This parameter lambda, although at this point is not required to be, but you should think of this lambda as being some small parameter. It's the perturbative parameter in which you're going to deform the state. So let's say you have some one parameter family of states psi lambda, and at any given value of lambda, of course, you can construct the reduced density matrices on the left and the right, and correspondingly, there are the modular Hamiltonians for these reduced density matrices, which I'm going to call k left and k right as functions of lambda. And just as a reminder, the modular Hamiltonian is just minus the log of the density matrix. Okay, so at any given value of lambda, you can of course define these eigenstates, these modular eigenstates, which are some choice of eigenstates for the right modular Hamiltonian and the left modular Hamiltonian. And the ENs, of course, are sort of the eigenvalues of the density matrix. And as a quick reminder, the reflection operator can be written in terms of these eigenstates in this particular way. All right. So in order to do this perturbation theory, what I'm going to do is, I want to understand if I change lambda a little bit, then how does the reflection operator change? Or how does the canonical purification change? So that's more or less easy to work out. If you assume non-degeneracy of the, as you were saying, the non-degeneracy of the eigenvalues, then the change in the eigenstate, let's say on the right-hand side, is satisfies a more or less simple equation, a standard equation. And in this slide, what I've done is I've just rewritten that equation in a slightly different way. So I've exponentiated the denominator, the En minus Em. I've exponentiated that using a Schwinger parameter. And then in the second line, the last line rather, I've sort of added an infinite term. I've basically introduced a regulator, the exponential of minus epsilon t. That's a regulator. Okay, it allows me to add and subtract the m equals n term, the term where the two eigenvalues coincide, and write this whole sum as a combination of two terms. One, with the second term here, which is proportional to 1 over epsilon, is sort of diagonal, okay, because it's proportional to chi n again, whereas the first term is not diagonal. It has a non-trivial operator acting on chi n. And the reason for doing this will become clear in a little bit, so just hold on to that. If you're worried that the second term is divergent, then you shouldn't be, because actually there is no that's supposed to cancel out the divergence coming from the first term. So really this term there's no divergence in this equation. It's just written in a particular way to make it convenient for later processing. Okay. So what we've accomplished so far is that we've written the change, this derivative of the eigenstates chi n and chi n tilde in terms of these objects, these curly AR and the curly ALs, which are just these things. Okay, this is just another way to write curly AR and curly AL. They're just, we've just rewritten the derivative of these eigenstates in terms of these objects, curly AR and curly AL. And maybe this sort of reminds one of these modular Berry connections that Bartek was talking about earlier in the day. So these are, if you like, modular Berry connections. And one way to think about why it's a connection. Yes, sorry, I should have said that. The small AR and the small a left is the diagonal part, this last term which I extracted out, and everything else I've written out explicitly. The reason for doing this is that this diagonal part just drops out of the calculation which I'm interested in. So this is the reason for writing it in this way. Right. So this capital curly AR and capital curly AL are these modular Berry connections that Bartek was talking about. And one way to think about why it's a connection is that if instead of talking about psi, if I had considered a state psi prime, which was some one-sided unitary acting on psi, okay, then it's a very simple calculation to check. You can go back and check from these definitions that the way these curly AL and curly AR transform is in this way. So if the unitary only acted on the right system, then the curly AL simply remains unchanged, whereas the curly AR transforms like a gauge, has a transformation which is like a gauge transformation. So you can think of these curly A's as connection one forms for local unitary transformations. So local unitaries on L times local unitaries on R. Okay, in that sense they are connection one forms. Okay, and following Bartek, I guess we can call them modular Berry connections. Okay, so now once you have access to these modular Berry connections, you can of course work out how the reflection operator changes, or you can write down a flow equation for the reflection operator, because the reflection operator was written in terms of these eigenstates on the left and the right. And you can formally solve these flow equations in terms of these modular Berry connections. Okay, so that's at least formally you can do that. But so what we are going to try and do to be concrete is we are going to work around the thermophile double state. So in the thermophile double state, everything is clean and well established because, well, first of all, we know that the state is its own canonical purification, as you or someone was asking, and secondly, in the holographic context, the quantum extremal surface is classically extremal. So there are no issues with shocks or anything like that. So in the thermophile double state, everything is great. So what we are going to do is we are going to take the thermophile double state and perturb around it. Okay, we are going to without matter. Yeah, that's right. Just like pure gravity. Yeah, eternal black hole with no matter. Yeah, that's right. So then what we are going to do is we are going to perturb around the thermophile double state by introducing a deformation which makes the quantum extremal surface non-classically extremal. Okay, so that it needs to have a shock in the canonical purification. All right. Adding matter, yes, in a specific way that I'll explain. Yeah. Right. So the kind of perturbations that I'm going to consider in this talk are sort of one parameter family of deformations of the thermophile double state, where we turn on a source for some operator O in the Euclidean path integral. Okay, so we all know that the thermophile double state is constructed in the language of Euclidean path integrals by doing a Euclidean path integral over some Euclidean time of length beta over 2. You can deform away from that by adding a source in the Euclidean path integral. The source I'm going to call j of tau, and O is some as yet unspecified operator in the dual CFT. So this new path integral now constructs for you some deformed state, some state which is a deformation of the thermophile double state, and I'm going to call that psi lambda. So that's my deformed state. If you recall from these various formulas, these modular Berry connections were explicitly given in terms of the modular Hamiltonian and its derivatives, right? So d by d lambda of the, once you know d by d lambda of the modular Hamiltonian, you know the modular Berry connection up to these diagonal parts, which as I said, don't actually contribute. Now, thankfully for these deformations, these kind of Euclidean path integral deformations, the change in the modular Hamiltonian, or the derivative of the modular Hamiltonian, is known or can be worked out in a simple way. And this is the formula that you get. This formula, or versions of it, also appeared in the talk that Debajyoti gave earlier. So I hope that you remember it. So since you have access to the change in the modular Hamiltonian in this in these Euclidean path integral deformation in this context, in the context of Euclidean path integral states, you can explicitly work out. Oh, I should have said, if there are questions about where this formula comes from, so the idea is that, if you have a matrix rho and you want to work out how the log of that matrix changes, then you have to be a bit careful because rho and d by d lambda of rho may not commute with each other. So you have to use BCH to compute this particular derivative, and then you can resum the BCH expansion to derive this integral formula for the derivative of the log of the density matrix. I don't want to go into the details, but I just wanted to sort of flash one slide to tell you where this formula comes from. Okay, but at any rate, once you know the change in the modular Hamiltonian, or the d by d lambda of the modular Hamiltonian, you can work out this modular Berry connection. Okay, you can come up with a more or less pretty explicit formula for the change in the for the modular Berry connection, which may also be useful in other contexts. But so the whole aim now will be to use this this modular Berry connection in this perturbative context to see where this this shock comes from in the bulk canonically purified state. Okay. Now, as I was saying, so far all of this has sort of focused on this reflection operator, But of course, once you know the reflection operator, you can also compute the canonically purified state, because the canonically purified state is just the reflection operator acting on the original state psi. Okay. So here's where the question of what operator to turn on comes in. So it turns out that you have to turn on an operator O in such a way that it's able to source the bulk stress tensor at linear order in lambda. Okay, this turns out to be a requirement because we are only working to first order in perturbation theory. If at first order in perturbation theory the operator doesn't source the bulk stress tensor, then we wouldn't be able to see this effect. Okay, so we need to turn on an operator which sources the bulk stress tensor to leading order in lambda. And one way to do this, for example, is to take O to be some double trace operator, okay, or multi-trace operator in general. So that can be done. But this is just a comment about what kind of O's you might want to choose. And so now, once you have you've established that, then basically the idea is to go ahead and compute, take this canonically purified state psi star, and evaluate the 1-point function of the bulk stress tensor in that state psi star. Okay, so here I'm doing it, in general. You could do it in more generality. You could take the bulk operator to be anything else if you want. So I'm calling it phi over here. But at the end of the day, we want to take phi to be the bulk stress tensor, and more specifically, we want to take this bulk stress tensor and take its limit where it sort of approaches the quantum extremal surface. Okay, in this case from one side. Right, so that's the calculation that we are after. We are interested in computing this particular bulk 1-point function. Now, so the first order change in the 1-point function in the bulk is very easy to compute. You just take d by d lambda of this equation, and you pull down 3 terms. The d by d lambda can either hit the reflection operators on the 2 sides of phi here, or it can hit the state, because remember the state itself is lambda dependent. So in all, this 1-point function has 3 contributions. There are 2 contributions coming from these modular Berry connections, and then there is one final contribution coming from the change in the state. But what I'm doing here is I'm taking this operator to approach the quantum extremal surface from the right. And so this last term here, the last term in this equation, sort of picks out the change in this 1-point function coming from the change in the entanglement wedge on the right side, okay, in the original geometry. So this kind of a contribution should not exist in the canonically purified state, because the canonical purification by definition sort of throws away the right and duplicates the left. So what we are going to see is that this last term actually gets cancelled out by a piece of the first term, which is good, because that means that you're at least on the right track, which is to say that the canonical purification knows nothing about the right system. And then the second term sort of replaces it by the change in the entanglement wedge of the left up to a CPT conjugate. Okay, so that's the expected behavior. In more detail, the way that happens is that for example, if you look at one of these terms, let's say the first one, then you simply take this first term and you plug in the explicit formula that you have for your modular Berry connection. You can take this commutator. Now, in this expression, there's a commutator. In the diagonal part of the modular Berry connection drops out of this commutator, because you can put the commutator onto the density matrix, and so that's why the diagonal part drops out. This is the whole reason for writing the modular Berry connection in this way. So the only term that matters is this other term, this off diagonal part. And then you can take this commutator and rewrite. You can do some contour manipulations to rewrite this in the form of the following contour. So the whole term becomes the sum of these 2 blue contours, the one on the top and the one on the bottom. Okay, and then it's sort of tempting to complete this contour, and so there's a pole in this contour integral coming from this overall function, this the overall function, the 1 minus e to the minus s plus I tau. There's a pole in the integral coming from there. So it's kind of tempting to complete the contour and just pick out the pole. If you do that, what happens is that you just sort of you reproduce this minus of this last term. So I was telling you how the last term needs to be cancelled out. So the pole in the first term basically cancels out the last term. You get minus of delta of phi coming from the right. So this is as expected. You should have expected that all the dependence on the right entanglement wedge cancels out, and that's what happens. A similar pole contribution from the second term here, the left star term, gives you the change in the operator 1-point function coming from the left entanglement wedge, okay, which is the right thing because in the canonical purification you've sort of doubled the left side, so that's what you should have expected. But so far there is no sign of the shock. That was the main thing that we were after. So it turns out that the shock actually comes from these vertical contours at infinity. So in completing this contour integral, you have to include these dashed lines which are off at infinity at s equals plus or minus infinity. The modular time equals plus or minus infinity. You might have thought that those are small and actually exponentially suppressed, and that is almost true. But it turns out that if you're careful, then you can see that the shock comes from there. So the way to see that is the following. So naively, so let's look at the contribution from this vertical contour at minus infinity, which I've written out here as I minus. Okay. So this integral looks like it vanishes because first of all there is in the denominator there's an e to the lambda. Lambda is going off to infinity. So it looks like there's exponential suppression from there. But secondly also, there's a lambda in the stress tensor. So you're computing the bulk stress tensor 1-point function. The lambda in the exponentials surrounding that are sort of boosting the stress tensor off to infinity, right? So because the bulk stress tensor is getting boosted off to infinity, there's going to be this correlation function is going to be exponentially suppressed in lambda, okay? So naively it looks like this contribution is just going to die off as exponentially in lambda. There is a caveat though, which is that because the stress tensor has this particular index structure, you get an e to the 2s enhancement from the index structure of the stress tensor, okay? And so what happens is that when the location of the bulk stress tensor, so let's say x plus, is greater than 0, then it is true that this operator just gets boosted off to infinity, and then the whole I minus contribution goes to 0 exponentially. On the other hand, when x plus is, so that was what happens when x plus is greater than 0. When x plus is 0, this operator doesn't get boosted off because note that the way this modular flow acts on the bulk operator is that it sends x plus to x plus times e to the s. Okay, so when x plus is 0, it's not getting boosted away to infinity, but on the other hand, you're getting this e to the 2s enhancement. Okay, that gives you a divergence. So when x plus is not 0, the correlator is exponentially decaying. When x plus is 0, you're getting a divergence from this exponential boost. And so now it's just a matter of checking whether this is a delta function divergence, which you can easily do by sort of integrating this correlator in a tiny neighborhood of x plus from, let's say, 0 to epsilon. And you can it's a simple matter to show that indeed that integral is finite. Sure, I'm almost done. So it's an easy matter to show that integral is finite and gives you the this particular coefficient, namely the d by dx plus of the bulk entanglement entropy as the coefficient of the shock. Okay, so that was where we wanted to get. What this calculation shows is it's basically a first principle CFT calculation, which establishes the fact that the stress tensor 1-point function in the bulk dual to the canonical purification has a stress tensor shock, which then is consistent with the fact that the Engelhardt wall prescription together with Einstein's equations predicted this, right? So that prediction can be verified from the CFT point of view in this particular way. It's a delta function shock in X plus, yes, if that's what you mean. Yes. The extremal surface is in this notation, it's x plus equals x minus equals 0.
Okay, so it touches the extremal.
Yes. Yes. Yes, you get a factor of 2, which I wasn't I wasn't keeping track of factors of 2, but yes, you get a factor of 2 from there. Yeah. That has to do with the fact that even in the Engelhardt-Wall prescription, there's a factor of 2 because you have the entanglement wedge and its CPT image. So if you keep track of how the expansion adds up, you get a factor of 2. All right, so just to summarize, so what we've done in this talk is we've studied this reflection operator, and particularly in a perturbative context. I've tried to argue and convince you that the reflection operator goes beyond standard entanglement measures, and it's an interesting thing to study. For a one-parameter family of states psi lambda, we've tried to come up with a flow equation for this reflection operator, and we've used this flow equation in a perturbative setting to try and derive this quantum extremal shock, which was a prediction of general relativity in the Engelhardt-Wall construction. And just as a final comment, I think that our arguments should also generalize away from lambda 0, namely to the finite lambda case, not just to first order in lambda, but to finite order in lambda perturbation theory, up to some mild assumptions about locality of modular flow close to the entanglement cut and so on, but I'm not going to discuss those presently. So I'll stop there. Thank you. Yeah.
So like just thinking about a quantum mechanics.
Yeah.
And in principle, if you add these things like Hareram, how would it be affected in this conversation? It's not like finite lambda, it's not like you go to Hareram.
No, that's not that.
Yeah.
So I think at least perturbatively in G Newton, that equation is exact. So did you mean G Newton perturbation?
Yeah. I thought that was the H bar. That was leading on the H bar.
Yes, but that. Yeah, this equation is expected to be exact in G Newton perturbation.
Right. But it's like subleading H bar.
The second term? Yes. It's subleading in G Newton. No, that's it. That's for so this is exactly for those are alpha.
So would this mean that then your computation will have to be also all the entire loop distribution should be advanced?
That's right. So in the stress tensor 1-point function, all the higher loop contributions should reorganize themselves into this form. Into the in other words, the coefficients should all repackage to give you this one particular shape derivative of the bulk entropy. That's
that's how it's yes.
So just I mean, I thought that you could get high derivative correction from also from H bar, right? Just from high correction. So that doesn't. I don't know. I'm just asking. Like, then you continue generalizing.
no, at least not in GR. I mean,
I think it's right. I think there are high derivative corrections occurring on the state groups,
right,
which should correspond to gravity groups.
Yeah.
This would correct the concept.
No, but at least the general expectation I thought was that the entropy there's this G Newton renormalization story where the divergence is sort of renormalized G Newton, and then the bulk and the entanglement entropy from the quantum perspective just has this huge
but that is non-renormalized. It's more than the G Newton renormalization. You will produce higher. Let's say if you do Q gravity, you get this peroxide protein.
Okay, I'm not sure whether there are in addition, like maybe there are other parameters.
Yeah, I mean, just for the strict perturbation theory, we know, let's say, after 4 is one correction.
Okay, yeah, okay. So, okay, maybe, yeah, maybe. I'm not sure.
Yeah, very short. Is there a way from CFT to construct this, if you do it in the eternal black hole?
Yes.
Of course, you get a different qualification. But now in this case, the QS, okay, yeah, so you still have the same QS on this side, I guess, but of course, there's some misaligned QS on the other side. Would you be able to?
There's always one QE. There's only one QE.
Oh, so there's always a one QS, right? Okay, because they're two-sided and they have to. Yeah, but I was confused because in the case when you have the shocks, you often see there is no bias. So this is the way you have to.
Reversible one.
So right. So I was just thinking, like, is there some way to understand it from the CFT point of view in the, like this other purification that you have? For example, this what you have in internal.
I'm not sure I fully understood your question, but the shocks which come in the traversable, if you had the gouge Paris wall kind of, is that what you meant?
Yeah.
Okay, so that's a different kind of, that's a different kind of shock, right? That yeah,
maybe the
that's
state is
because
not
you
fully
said,
pure, so it may not have only one single. You can have two not conditioned.
okay, possible. Yeah, okay. If you're considering mixed states, maybe. We
But
haven't.
I don't know about that, whether it happens in the gouge first or scenario.
No, not that. But I mean, maybe if you consider mixed states, you can have. Okay.
No, I'm just trying to say that can you see some aspects of like other geometries like purified sets, like eternal blackboard geometries in this other purification?
Well, I mean, the canonical purification is particular. It's not like you can expect to see something novel coming up in the bulk because it's a particular specific purification of one side of the state. So, yeah. Maybe you're asking whether you can define other types of
purification from this in this technique.
Okay. Yeah, I
Yeah. So if you had a gauge field in the bulk, you would expect the junction conditions to also give some charge here.
That's
a state with charge.
Right.
Let's say the charge is a lot of
Right.
Do you see that how that would come out of this kind of analysis?
You're asking whether one expects like a shock, a charge shock or something. Yeah, interesting question. Yeah, I haven't.
But you have a gauge field, how would you define the second term?
Yeah, but then there are issues with how to define it. But there are people who have come up with ways to define entropy in the present term, right? You construct this extended Hilbert space, and there are ways to do it. It's not a completely lost case. Yeah, but interesting question.